will be a Starfreelancer. Learn new skills. Set your goals. Increase your skills. Browse over 100 plus videos and ebooks. Jump to starfreelancer.eu.
So as I mentioned in the previous video, we're going to read in the directions.txt file that we've written. And it's a very similar process to reading the locations, but the difference is I'm going to actually introduce a buffered reader. Now, a buffered reader reads text from the input stream and buffers the characters into a character array. So for our example, we're going to still create a file reader, but we're going to use it as an input stream for the buffered reader to use. Now, reading chunks of data from a stream such as a file is more efficient than reading just a few characters at a time. And the reason for that is because things like the overhead of seeking to the correct track and sector on on your disk drive are significant. So it actually takes a while to find the correct place on the disk drive to read from. And if you have to do that many times because only a few bytes are being read at a time, then the seek times for this really do add up. So consequently, buffered readers can be a lot more streamlined to, faster in other words, and more efficient. Now you can actually specify the size of the buffer, but the default is 8K bytes, and that's enough really for most purposes. Now our files here are both smaller than 8K, so what that means is the entire contents of the file will be read into the buffer in a single read and be available from there for the scanner to use it as it needs more data. So let's go ahead and look at implementing that now. So I've already read in the locations, as you can see here, starting on line 48. So we're actually starting on lines 46 to be precise. So let's go ahead and, as I mentioned, read the directions in. So I'm going to actually put that in its own try block. So I'm going to come right down here and actually add it into a separate try block. And bearing in mind, we are going to change this to a try with resources later. So let's start with that. So we're going to try. So just put a note here that we're going to now read the exits. Let's maybe scroll up a bit so we've got a bit of space for the typing. And we're going to start with a try. We're going to start with scanner. Scanner equals new scanner, new buffered reader, and new file reader, directions.txt, which of course is the name of the file that we use to store our directions /exits in. I'm going to accept those imports, or import, that's only the one, and we're going to set our delimiter, so scanner dot use delimiter, we're going to set that to a comma again. Then we're going to start our loop, so we're going to do a while scanner dot has next line. So we're going to just continue going through the entire file and read the location. So location equals scanner dot next int. Then we need to get the direction. String direction equals scanner dot next. And then we need to get the destination, so that's going to be a string. Before we do that, actually, we need to actually skip. So scanner.skip, scanner.next delimiter, and of course we're doing that to go to the next. Delimiter, not next delimiter. Delimiter. We're doing that to go to the next comma because we've obviously read in the first one, which is the location, and then we're going to read in the direction. And I should have actually had a delimiter there as well, because obviously each piece of data, if you recall looking at directions.txt, we've got them separated by commas. So consequently, of course, we need to use that line scanner.delimiter to skip for each one of those. So I've got the location I'm reading on line 67, I'm skipping the direction that I'm skipping, and then the last one is going to be the destination. So string dest is equal to scanner.next line. So we're going to read just to the end of the line now because that's really the only data there. And then let's create an integer destination, and we're going to use integer.parse int dest, so we're actually just converting it to an integer because ultimately that's what it is going to be used for. Then we're going to just print them out, so let's do that. So it's going to be location plus a colon and a space plus direction plus colon and a space plus the destination. Let's build a location object. So location equals locations.get lock. So we get the locations that are on file for that. or the location, basically the location, and then we need to add an exit to it. So we can do location dot add exit, and direction. The exit can have a direction and the destination. So we're building up the destination object, and we haven't written that code yet for add exit, so that it's normal to expect there's an error there, and we need to catch our errors, or catch a potential error, which is IO exception E, and we'll just do an E dot print stack trace. And I obviously need to put another bracket in there, so I'm at the wrong level there. So that's fixed the catch up, and I'll just move the catch back to 1. Delete that. And E dot print stack trace. Then we're also going to add a finally. And the finally is going to be just close the scanner if it's open, if it's not null. So scanner is not equal to null, scanner dot close. So what we're doing here is that the file reader is passed to the buffered readers constructor. This is on, I'm talking about line 64. Then the buffered reader itself is passed to the scanner's constructor. And once again, just want to point out the classes are designed to be used in this way, and closing the scanner will actually close the buffered reader. And that's of course because it implements the closable interface that we talked about in the last video. So we can check the buffered reader's close method if we want to. And have a look for close. So we can see that it calls the close method, and it calls the close method of the reader. And if we just have a look at that, you can see in is actually a private reader in. So basically, again, what it's doing is it's implementing the closable interface, and therefore that close is automatically going to be called for the buffered reader. And if we just go up and have a look at the buffered reader, you can see that it's an abstract class, and it implements readable and closable. So again, for that reason, it's going to basically be auto-closed once the processing's been completed for it. So again, closing that down and just looking at the code we've just written, we're basically going through and one field at a time extracting that field from the scanner, because obviously we used commas as delimiters, as I mentioned earlier in this video. So to read it back, we tell the scanner that it needs to use that comma as a delimiter, so of course it knows when to stop reading each piece of information. Now most of the body of the while loop is taken up in getting the integer string and the integer data from each line of the buffer, and reading data into numerical values from a text file can be problematic. And I had to read the final number as a string using the next line method. This is the code on line 71, because there's no comma delimiter to tell the scanner to stop reading an int, because that's really at the end of that particular line. And in fact, the scanner may not be the best way to parse this data. The thing to remember with scanners is they can be notoriously difficult to use, and it really can take some trial and error to get one to behave properly with a particular data set. Now in this example, we've had to skip over the delimiter when reading strings, as otherwise the delimiter is included in the string. And you can see I skipped it on line 68 and line 70. And the other thing is we've got an error when trying to call the location object's add exit method. And that's because we actually removed the method when trying to make the class immutable in previous videos. So let's add the add exit method back to the location class. But we're going to make a change there just to protect ourselves. So I'm going to come down here into location. We're going to add it. We're going to add it as protected, so that it's only available to classes in our package, and of course subclasses of location as well. So it's going to be protected void add exit, and it's going to accept the string for the direction and an integer for the location. And all it will do is put exits.put, so add it to our map and direction location. So it's a very simple method. Okay, so that's that added back. So if we go back now, that error should disappear on line 75, and we're good to go. So before I change anything else, let's actually run the program to make sure it works. So let's have a look at it. And you can see we've got our comments that, if you recall in the code, I actually added some output on line 49 to say we've imported the various locations. We've got the location number and the actual descriptions. And we've also got our location, our exits data as well. So that seems to have read that in and be working okay, which is good. So we've done that, but let's actually go now and run the code from the main class so we can actually run the program to make sure it still actually runs and works. So we'll do that. We can actually just move around to different locations in our game. Okay, so standing at the end of the road. So let's go north again. Go south again, go east, go west, and let's try and go east again, and let's try and go, say, north. Can it go in that direction? Let's quit. That seems to be working very well, which is fantastic. And obviously you can see that the code at the top there was actually printing out the locations data that was coming through when it was imported. So we can see that it's actually being read successfully from both the locations.txt file as well as the directions.txt file. Now another way to parse this data is to read it line by line, and then we could actually use the string class split method to get each part of the line into a string array. It's then quite simple to parse the values that really should be integers. So let's actually look at another way of doing that. So I'm going to close this down and go back to locations. And I'm going to comment out the code that we actually had in there. So comment out this code up until that destination line there. We'll comment that out. And we'll do something using the string.split. So the way to do that would be string input equals scanner.next line. That's read the entire line this time rather than reading sort of one of three fields, which we've done on lines 67 to 72, which I commented out now. So I've read basically the entire line. And then we can do string data is equal to input.split. And then we use our delimiter character, which was a comma, and that creates a string array, which has now got each one of the fields from that line in there for us. And now what we can do is we can put input for the location. We can say it's integer.parseInt, and we'll say it's the first array element. Then string direction is equal to data1, because we're keeping that in a string format. Then int for the destination, that's going to be equal to integer.parseInt. That's going to be data2, the third part of the array. Then these lines here, on lines 79 through 81, they're unchanged because they're still taking the same variable names and being processed. So just run this to make sure that it works again and we can still run our game. So that's still working, which is good. So that code there is probably a bit easier to understand and also can be easier to implement when we're dealing with data that's separated in some way. So at this point, you might be thinking that we're back where we started and we actually had more code than we had before. So what is the actual advantage? Well, with the small number of locations that we have at the moment, the advantage is not really obvious. But I've actually, in the next video, I've got a download for you in the resources section of the video, and we're going to use those files instead because they've got a lot more locations. And as a result, you'll sort of see the advantages, when you're dealing with larger text files. So let's end the video here now, and in the next one, we'll go ahead and look at implementing that data so that we can actually run the game with more locations. See you in the next video. So in the last video, we added the code to actually read in the directions, the exits in other words, but there's a fair amount of code here still, and I asked the question, what's the advantage? What have we actually done here? And, with the small number of locations that we have at the moment, the advantage of this code compared to just sort of hard coding the locations is not really obvious. But there's actually a downloaded file called gamedata.zip that's in the resources section of this video. So download that, and we're going to use those files instead, and you'll see that it gets a little bit easier when we've got lots of locations. So let's actually have a look at that. So I'm going to swing over to a folder where I've already got this downloaded. So again, you can get this from the resources section of this video. Unzip it. And you can see in the folder now there's going to be two files, directions_big and locations_big. So what I'm going to do is go back to my project, and I'm going to just right click it, reveal in Finder. And I'm going to go into my input to output folder, which is the project name that I've assigned for this one. And I'm going to actually just copy these files. These are the ones that basically are from the unzipped game data file, and I'm going to paste them into there. And I'm going to go back to my project, and they should appear as they have in the left-hand side. Now what we're going to do, instead of renaming the existing files, I'm going to actually change the references on lines 43 and 64 to use the new names. So it's going to be obviously directions_big and locations_big. So I'm going to change those names and use these files. Big directions_big. And now we've done that, and let's just have a look at some of them. So let's look at locations underscore big. You can see we've actually got a lot of locations now, and this is basically the entire locations for the entire game. So it's actually obviously quite a few there. And likewise for directions underscore big, there's now going to be a lot more entries. It's a significant amount of entries there. So let's just close some of these files down. And then we'll give this a run again to make sure it's still working. So let's run it. And you can see our input seems to have worked because we've got a lot of location data on the screen there and a lot of imported locations. Significant amount there. So let's go down to the bottom and we'll just try running a few locations. So these are getting hard to read now because of these locations. So let's actually just change the run window. I'm going to change it so it's down the bottom. So I'm going to move that to bottom. We'll be able to see that a little bit better now. There we go. And just to check, let's go south. And let's go north. That seems to be working okay. Okay, so quit out of that. Now, this is again the locations from the original Colossal Cave adventure game, and that actually had a random element so that you don't end up stuck in a forest, which is actually quite easy to do with this version. And we also haven't got any items, such as the key, so you can't actually get into the caves at the moment. We can cheat a bit though by setting the starting location to say location 64, for example. We can actually sort of move to a different area. So let's just look at doing that. We're going to go back to main. Close the run window down for now. So what we can do here is on line 29, instead of the location being 1, let's actually comment that out and temporarily put it to location equals 64, which is an entirely different location. And that should start us off in a more complex junction. So let's just do that to see that it's actually working. At a complex junction, a low hands and knees passage from the north joins a higher crawl from the east, etc. So we should now be able to just do a bit of wandering. So let's just go east. Might help if I type in the right window. So east. We go east again. Here at wit's end. Go east again. And basically that's a good way to get lost. But anyway, you can see it seems to be working and that's good. So if we open up the big locations and directions files again, so directions big, locations big, I'll just close this run window down. Can you imagine actually, typing all that code in to initialize this manually into your class instead of actually reading it into a file? So you can see that this is obviously going to be far more efficient when you've got lots of data to read that data in using some code rather than trying to type it directly into our Java files that we did initially before we actually got into this input-output section. And these files, by the way, were actually extracted from the Fortran source from the original Colossal Cave game. You might be wondering, why are these descriptions all in uppercase? Well, that's because most of the terminals at the time, and we're talking the early 1970s then, they couldn't actually display lowercase characters, believe it or not. But as I mentioned earlier, there's actually a random element to the game, and we haven't implemented that yet. And if you get to a secret canyon, the description does not necessarily mean that you're in the same bit of it each time. So in other words, the available exits can change. But getting back to our code, we've now seen a simple way to write data to a file and to read it back again. And in the process, we looked at the finally block to ensure that the cleanup code is executed, even if an exception is thrown. And we also chained objects together. Just go back and have a look at some of this code when I'm talking about it. We can see a reference of chaining there on line 64. So we also chained these objects together, as I mentioned, to allow a scanner to read from a buffered reader that uses a stream to get its data. And I also covered the try with resources method that became available with Java 7 and that resulted in much cleaner code, and we saw an example of that. Now, I haven't used that in the example that reads the data back in, mainly because it's important to understand how to perform I/O with older Java versions when you have to maintain legacy code, and that will happen quite a bit. But also, the second reason for doing that secret evil plan was it makes for a good challenge for you to do it. So the code to read the data back is a bit cluttered, catching exceptions, and we don't actually do anything with those exceptions, but unfortunately our options are a little bit limited here. Now, when we had code in our main method, we could just specify that the method throws the exceptions and remove the catch block. Now that approach can't be taken with a static initialization block. And the reason is that the static initialization block, they're actually executed when the class is loaded. So in other words, there's no way for any of our code anywhere to catch any exceptions that are thrown. Now you can throw unchecked exceptions in an initialization block, but not checked ones. Unchecked exceptions, if you remember, don't have to be caught, but checked exceptions must be. But with that said, we can rewrite the code to use the Java 7 try with resources to make it a bit tidier. And in the next video, I'm going to set you a bit of a challenge on to get you to do just that. So stick around and I'll see you in the next video, and we'll have a challenge for you to undertake for this code. See you there. So as I mentioned in the last video, it's time for a challenge. And the challenge is to rewrite the static initialization block that you can see on screen now using the try with resources that we've talked about and discussed in this section instead of the try finally code that we've actually got in here in place now. So pause the video and go away and convert this static initialization block into using try with resources instead of try finally. And when you're ready to come back and check my solution, start the video. So pause the video now. Okay, so how did you get on? Hopefully you got the try with resources working. Let's go through now and get this set up. So what we need to do first is we're obviously in locations.java and we're in the static initialization block. I'm going to delete this first line. We no longer need that anymore. And instead what we're going to do is put the code in the try block. So we're going to come up here, try, then we're going to set up the scanner in the brackets. Scanner equals new scanner, new file reader, locations underscore big.txt, like so, and you can delete that line now because we've effectively done that on the previous line. And we come down to coming down to catch IO exception, we're going to leave that in place, but we're going to delete the finally block now because, of course, the close now happens automatically with the scanner, as we've talked about in previous videos. So that's that. That's the first one. Then the next time, we're going to read the exits. We need to do a similar initialization. So we come up to the start here, scanner equals new scanner. This one's a new buffered reader. I guess we could have just copied the line below. New buffered reader, then it's new file reader, and its directions underscore big.txt. So delete the next line now. Then again down to the finally. We're going to delete the finally because that's no longer needed. No longer needed because it's automatically closed. So we just run this to confirm that it still works. Let's go, say, north, south, west, and quit. So that's working okay. So that's the challenge. But just before I finish the video, you may have noticed that we actually stopped needing a scanner to read the exits when I changed the code to read a line at a time and split it. So removing the scanner is actually quite easy. So what we can do is come up here to line 57 and get rid of the scanner altogether. And instead make that buffered reader files equal to new buffered reader, then get rid of one of the brackets, get rid of the scanner because of course we're no longer using that. And we're going to set up a string, so we've got string input. We can change the while now to be while input equals dir file dot read line not equal to null. And we can delete the string input now because that's now been changed on line 59. And again, I just wanted to say this isn't part of the challenge, so this is just an optional extra step that I'm just showing you at the end of the video. So don't think that you've missed out and I haven't told you how to do something with the challenge. This was just an extra section, given that we weren't really using the scanner anymore, it made sense to actually remove that. So now that I've done that, we could have actually done that at the same time as I stopped using the scanner for parsing the data, but the buffered reader class close method throws an unchecked exception, so I would have had to have caught that in the finally block as well, so that's the reason why I didn't do that any earlier. But now that we've actually converted to the try with resources, it's a simple change to make. Alright, so that's actually it. That's the challenge over. Oh, actually, before I go, let's just run it to make sure that it still does work. Obviously very important. And let's try up, down, we'll go west, up, and quit. That seems to be working fine. Okay, this time I'll see you in the next video. So in the previous videos in this section of the course, we looked at reading and writing data using character streams. To write out the data, we used the file writer class, and to read it back in again, we created file reader objects. We then discussed the idea of buffering the stream so that large chunks of the data are read into memory by buffered reader. Now this prevents excessive access to disk because the data is only read from the disk when the buffer is empty. Otherwise the file reader continues to take data from the memory buffer, so it's much more optimized compared to just sort of reading a character at a time. Now you can also buffer data when it's written to disk, and not surprisingly this makes use of a buffered writer class. The concept is the same. The file writer puts data into the buffer and the data is only written to disk when the buffer is full. Now once again this prevents writing small amounts of data to the disk, which is very efficient because the disk drive generally speaking is much slower than your computer can process, so your computer application is going to be slowed down waiting for that disk drive to write data. So by doing it this way, using a buffered writer, data is written in sizable chunks rather than sort of a character at a time. Now I didn't actually use a buffered writer in the previous example, and I only used a buffer reader to write the directions file. The data from the locations file was read from disk line by line, and that resulted in many accesses to the locations.txt file. So in the next few videos, I'm going to cover byte streams, which write binary data rather than character data to the streams. And it would make sense though to have an efficient program to modify. So I'm going to start off with a challenge. So first I'm going to remove all the commented out code to help tidy things up. So we've got a good basis to start with. So let's start just commenting some of this stuff out. So I'll go to locations, and remember that in the locations Java file just above the static initialization block we had this code here. So let's just delete that to clean things up a little bit. And just scrolling down, we also had this code in here when reading the exits. Let's just delete that as well, just to make things like a little bit cleaner. And we've also got this code down here, which we can also remove. And that was our initial code to have directions, locations, and exits before we decided to start writing that to a file. So I'll delete that as well. Okay, so that's looking a little bit better. Okay, so here is the challenge. So I'm just going to make that a little bit bigger so we can see what this is all about. And there's two parts to this challenge. So part one, we want to modify the program so that it uses a buffered reader to read in the locations data. So we run the program to test it before moving on to part two. So that's part one of our challenge. Now part two, we want to then modify the main method of the locations class so that it uses a buffered writer to write the data. So open the locations.txt and directions.txt files to check that the data has been written successfully. That would be your way to make sure that using the buffered writer that it does work. And you'll then need to make another change to the program to allow for the quit exits before using the newly created files. And just as a hint here, you may want to change the 3 instances of HashMap to a linked HashMap in the location class and 1 instance in the locations class so that you can compare files more easily. And the reasoning for the 0 quit is that when the data was originally written to the files, it's been hard-coded in the locations class and there were no location zeros because this is added by the location class constructor. But now that we're writing the contents of the class to the directions.txt file, the 0 locations will also be saved, and that's why a change will be needed to allow for this. And this is that part here that I'm talking about, the 0 quit exits before using the newly created files. Alright, so that's your challenge. Go away and see if you can figure that out now for this code. And once you've had a go at it and you think you're ready to see what we've come up with, come back and we'll go through that code. So pause the video now. Okay, so how did you get on? Hopefully you managed to get it working or gave it a pretty good go. So let's go back now and get this working. So part 1, and just as a recap, part 1 was to modify the program so that it uses a buffered reader to read in the locations data, and we're going to make that change and then we're just going to run to make sure things are working before we move on to part 2 of the challenge. So to implement the first part, we really just need to make a relatively simple change in the static initialization block in the locations.java file. So where we've got this try scanner equals new scanner, the new file reader, we really just need to change file reader to a buffered reader. But we put the new buffered reader in here, so new buffered reader, and then we put the new file reader in there, then we add another bracket. So that's really all we need to do. So we now just have just changed it, so we've added the new buffered reader, which still takes the file reader as input, but now the data will be read using the buffered reader, which is obviously more optimized to read in chunks rather than reading a character at a time. So let's go back to main. We'll just run this to make sure that it still works. And there's a location, so we can try topping up, down, east, west, west, east, west again, northeast, north, and quit. So that seems to be working all right now. So let's move on to part 2 of the challenge. So part 2, we want to modify the main method of the locations class so that it uses a buffered writer to write the data. And then we want to check the locations text and txt and directions.txt files to check that the data has been written successfully. And then as I mentioned, we need to make these changes to allow for the 0, the quit exits before using the newly created files. Okay, so how do we go about that? Well, let's look at location. Now at the moment you can see that we're using a map. Our definitions for map for exits, for example, here on line 12, and you can see that we're using, for the exits, ultimately we're using a hash map. So for part 2, it's going to be really useful, I think, to compare the newly written files with the big locations and directions files. And to that end, it would be really useful and helpful if the data was written out in the same order as we read it in. Now, although this is not really necessary for populating our locations and exits map, it will make comparing the files a lot easier. Now, at the moment, we're using hash maps, as you can see on the screen there, and they have no guaranteed ordering of their keys. And that's why in the hint, I sort of mentioned a linked hash map and suggesting that you use those. And the reason for that is the ordering will be the order that the keys were added to the map instead of just hash map, which is, again, no guaranteed ordering of their keys. So to achieve that, it's relatively simple still. We come back here where we've got this code if exits is not equal to null. So we change this .exits equals new, and we change that to a linked hash map. Linked hash map. And we'll do the same for the next line as well. And then going down to the getter, instead of returning a new hash map, we want to return a new linked hash map there as well. So that's really the only change we need to make in location, but we also have to go back to locations.java. So let's go and have a look in there. And we need to make a change in there as well to use a linked hash map. So at the moment you can see here on line 12, we're using a hash map. So let's change that to a linked hash map. And now within the main for the locations class, we need to make some changes in here as well, but they are fairly simple as well. So the change we need to make here is we're going to create a buffered writer. So buffered writer, and we'll call that one lock file, is equal to new buffered writer, and that's going to be new file writer within that as the input. We need to add a bracket to make it valid. Then for the next line, we want to do the same thing as well. We're going to put buffered writer, and we'll call that dir file equals new, and it's going to be buffered writer, and it's going to be new file writer again, and we need to add another bracket. And that should be all we need to do. All the other code there is going to be the same as what it was before. We don't really need to make any other changes. So we want to run this program, making sure we're running the main within locations. So let's just do that. Run locations.main. Okay, so that's finished. And then what we want to do is we want to make sure that the locations and locations_big.txt are now identical. So let's just have a look at that. So locations.txt, the one that we've just written out, and locations_big. And let's just close down this run window so we can see a little bit more. So there's locations underscore big, which already existed, and then locations.text, which was the one that we've just created. And if we just scroll down randomly to have a look, it seems to be pretty good, but we'll just double check. 42. Looks pretty well identical. We'll just scroll down to the bottom, making sure we've got right to the end. And location 140 is the last one. Location 140 dead end. So I think that's pretty much identical. From my point of view, that looks pretty similar. If there's something different, I can't see it from a from a look now anyway. So it looks like we've done the right thing there. Now, if we close down these locations to those location files, and we have a look at our directions underscore big and directions underscore directions.txt, there are extra entries for the quit option, and we've added those with this code. And they've now been added. So directions underscore big has got only one, it starts on location 1, but directions.txt, we talked about that 0. Extra entries for the quit options, 1 for each location. Now there's 2 ways to deal with this. We could either stop the location constructor from automatically adding the quit exit, or we can change the code that writes out the data so that it doesn't write out any Q keys. And as is usually the case when programming, there's pros and cons to both approaches here. So if we prevent the location class from automatically adding the quit option, we're cluttering the data file with entries that really aren't part of the game. And there's a risk that someone editing the files may forget to add a quit option for any new locations that they create. But if instead we change the program so that it doesn't write out the quit exits, then there's really no need to remember to include them in the data file. But then, of course, we lose the ability to have quit do something slightly different for certain locations. For example, if we wanted to add that functionality. So if the player had been lost in a maze for a long time, for example, you may want to offer them the chance to be taken out of it in exchange for some of their treasure if they quit. So for my solution, what I'm going to do is change the main method so that it doesn't write out location 0. So let's go back and do that. So back in locations.java. So at the moment we've got the code there, and you can see that we're looping through, and we're using that for loop there for the directions, and we're just writing out everything. But what we need to do to ensure that we're going to miss this the quit option, we're basically going to add an if comparison there. We're going to put if not direction dot equals, we'll use ignore case to make sure if it's lowercase q or higher case that we're still testing it. So then only if we're not, we haven't got the quit as the direction, as the option I should say, then we're going to write that out. So once we do that, we should now find that the directions file is identical. So let's just run this again. Run locations.main again. And then let's have a look at directions.txt. We're now starting with 1 this time, and that's obviously identical to that. So if we just scroll down and look down to the bottom, 396 is the last line, 396. So basically we've got identical outputs from both. So that's good that we fixed that. Now there's actually a third way that we could deal with that issue, and what we could have done is we could have completely removed location 0 from the exits maps and dealt with the quit option by then checking the user input in the main game. That would slightly complicate the code, but it would save the memory used to store all those extra exits. Now the memory of course isn't a big issue with our 140 locations, but with that said, it's always a good idea to consider all the options before settling on a particular solution. So that's the end of this challenge, and we've now seen how to buffer both input and output. In the next video, what we're going to do is we're going to start looking at writing binary data using byte streams rather than the character streams that we've been talking about today. So I'll see you in the next video. So in the previous few videos, we've looked at how to read and write text files, or text data I should say, to files using the file reader and file writer classes. So we also looked at buffering the data to make the program more efficient, which is reducing the disk access time by reading large chunks of the file into memory in the case of a read operation, or writing data to a buffer, then saving a large chunk to a file in a single operation when writing. So I'll continue to use buffered streams in this next example, and here we're going to take a look at byte streams, or binary data in other words. Now once again we need some data to work with, so what we'll do is we'll continue using our locations data for this first example. But once I've covered how to read and write binary data, I'm going to switch over and use some different examples so you don't get too bored. So to clarify what's going on with the static initialization block in the locations class, just open that up. In the static block, you can see on the screen there now. When we run locations.main, the main method in this class, this is the code that is up here starting on line 14. When we run that main method, the class has to be loaded before its main method can ultimately be executed. So what that means is the code in the static initialization block is executed before the main method. And what that means is that the locations and directions files have been read in before the main method is executed in this class. So to start with, what I'm going to do is rewrite the main method to save the data that's read in by the static initialization block in a binary format. Now once we've got a binary file to experiment with, then what I'll do is I'll change the static initialization block to read from this newly created file. Now in terms of binary data, one advantage of dealing with that data or byte stream is that we don't have to parse the data into the various data types that were stored. And the reason for that is that a byte stream itself can be used to read and write any of the Java primitive types, such as int, double, byte, etc. And also as a special case, it can also handle string variables, even though string isn't actually a primitive type. And I think you'll agree that's pretty cool. So working with byte streams, they follow the same pattern, or working with byte streams follows the same pattern. The difference is we use the file input stream and file output stream classes instead of file readers and file writers. Once again, I'm going to buffer the data using the buffered input stream and buffered output stream classes. Now, in terms of doing this, we could work directly with these objects, but they only handle raw bytes. So reading or writing either a single byte or a specified number of bytes. Now, there are occasions when that's probably all you'll need, but generally speaking, when storing and retrieving data, you probably want to work with the Java types. Now, the Java I/O package, luckily for us, makes this easy by providing the data input stream and data output stream classes, and they provide methods such as readInt to read an integer value from the stream. And it does this by reading 4 bytes from the stream and building up the integer from those 4 bytes. So I'll have a look at how those classes work together in a minute, but it's probably easier to have some code to work with. So I'm going to replace the code in the locations main method now with some new code. Instead of trying to change it, I'm just going to delete everything and start again, just so it's a little bit clearer for you. So I'm going to try, and it's going to be data output stream lock file is equal to new data output stream, and it's going to be a new buffered output stream, which needs a new file output stream. And noticing how IntelliJ is finding those for us automatically, which is pretty cool. And the file is going to be locations.tat. Then we'll use our loop for locations.values. We're going to iterate through the list of values. Lock file dot, we're going to write an integer first, so write int using the write int method. That's going to be location dot get location ID, so we're writing that as an integer, and of course it is of type int. Then lock file dot write, we need write UTF, which we can use effectively to write a string, and you can see the input there it's looking for is a string, so write UTF location.get description. Then we'll just print out where we're up to, just to the log, to the console, writing location plus location.get location ID plus a colon there, and then we'll just location.get description. Just putting that to the console, what we're writing. And then we're going to indicate how many exits we're going to be writing out for this particular location. So writing plus, that's going to be location.getExits.size, take 1 plus exits. That's how many exits we're writing for this particular location. So let's now write that number out. So it's going to be lockfile.writeInt. It's going to be location.getExits.size, take 1. Then we're going to go through those list of exits. So 4, and it's going to be a string for each location, so, or direction I should say, string direction, location.getExits.keyset, so go through the list of keys. And we don't want to record the quit, and that's why we've deducted 1 from the total size. So it's going to put if not direction dot equals ignore case Q. So if we're not writing the quit location, or we're making sure that the direction that we're processing isn't quit, then we're going to print this out. So I'll print this to the console first with a couple of tabs, plus direction, just so we can sort of see what's being written out, plus comma, plus then the location dot get exits dot get direction, which is the current direction that we're processing. Then we just do lock file dot write UTF to write out the description, or the direction, I should say, direction. And then we want to write the location effectively where that direction goes. So it's going to be lock file dot write int, and it's going to be location dot get exits dot get direction. And we need another bracket there to close things off. And I just messed up this try line, because remember we're using the try with exception. So what we should have done is put a bracket there and a bracket on the end. And I'll just move that to there. That's what I should have done the first time, and by doing that, that's going to fix the error. So we may as well try and use that try with exception from now on in the course, because that is the recommended way to process, and of course it means we don't need to have that finally in catch. We're already throwing the IO exception anyway, and we don't have to worry about it finally, because of course, as if you recall, this is automatically set up to close our files when we finish processing them. And just one thing to note, we're going to be writing locations.dat. We're using .dat because it's no longer a text file. It's 2 advantages. Firstly, it's needed anyway, because the main reason we're doing that is to not conflict with locations.txt, but equally importantly, it's clear that this isn't a regular text file, so we wouldn't want to call it .txt and people thinking they can open it with a text editor, when of course it's effectively binary data and it won't open. So that's the reason why we've chosen that. So let's run this program and see if it works. And you can see we've got a locations.dat file now. And just out of interest, if we try and open that, IntelliJ is having a bit of a fit, but we'll just say treat it as text anyway and open it. You can see it looks a little bit like gibberish. There's some weird stuff in there as well. And even if you click on reload in another encoding, we're going to get the same result. I'm actually not going to proceed with that. The bottom line here is IntelliJ seeing that this is not a regular text file compared to, say, locations.txt, which of course we could read because that was a text file, but this is a binary file. So we still get to see some of the information, but you can see in the case of line 1, those bytes there are ultimately going to be an integer, which correspond to the first thing we wrote out, which was the location ID. And just in terms of seeing where we're up to, if we go back and scroll up to the top here, after the imports, which happen in this static initialization block, scroll down a little bit. You can see writing location 0, where what the location was, sitting in front of a computer learning Java, writing 0 exits, because there weren't any exits. Location 1, then we've got various directions, and then the location, or the direction corresponding then to which room that goes to, or which location that goes to. So basically that's the text representation of what's been written in that binary file. And I do recommend when you're working with binary data like this, it's generally a good idea to do something like this and to keep your code up to date. So getting back to the code again, I'll just close down this file. So a good idea as you're writing your code to have this sort of debugging capability built in, and adding and updating that as you update this particular method. If you're writing data, if you're adding new data to the file, update your debugging information as well, because it really makes it easier to work on this in the future. Now later in the course, I am going to look at logging, because really, if you think about it, this output shouldn't really be shown to users of the program, so it's better to write it to a log file where it's hidden from users, but it's available to us as developers if we need to diagnose errors in the future. So you notice that we created the DAT file, that was number 1, but secondly, did you pick up the fact that we're now writing locations and exits all in the same file? Now, because locations have different numbers of exits, the number of exits is written first and it's followed by the exit data for that location. Now, if you think about it, there's no reason why we couldn't have done that for the text files as well, but it was useful to see how data from different files could be related, and that's the reason that I used that different approach. In the case of the text files, they can also be readily read by humans, so it's worth spending time to decide how the data should be presented in that case, whether a single file is okay or split into locations and exits, as I did when we're working on the text files. Once again, you can make arguments for and against either approach. But in the case of binary data, though, humans wouldn't be reading the contents of the file, so the decisions is probably a lot easier to make. So the question to ask yourself here is, why use two separate files when a single file will do, especially if using two separate files doesn't give you any advantage. Now, you may feel that having separate files makes the code easy to debug, in which case it's fine to do it that way. It's your code after all, so you can really do it whichever way you want. But it is a good idea to understand the options when you're making a decision. But actually, also looking at the code from line 13 through 24, there's not really a lot of code there anyway. So, it's not particularly complex what we've done, sort of writing this out to a single file. And again, just looking at that code, you can see that the code to write to the byte stream is very similar to writing to a character stream. The file output stream object's used to open the file for writing, and once again we buffer the output, as you saw, with the buffered output stream object. Now, I could have left it at that, and I could have written code to produce the bytes representing the integer and string values to be written. It's a bit fiddly doing that way, but not too difficult. But fortunately, the data output stream class deals with all that for us automatically, and you saw that as I was typing this code in. All we really have to do here now is to write an integer. For example, is to use the .writeInt method. You saw an example of that on line 15. And then write UTF on line 16 is an example to write the string out. The good news is there are also methods to write out all the Java primitive types. So the data output stream class includes write long, write float, write double, etc. So let's just spend a short while looking at what the writeInt method actually does. So I'm going to command click, so command or control click writeInt. Click onto that, and there's the method on the screen. So you notice here we're using this particular operator. This is called the shift right zero fill operator, which is a bit of a mouthful. But basically what it's doing there, by using 24 in the expression here, it's actually moving the top 8 bits, the highest byte, into the lowest position by shifting them right 24 places, if that makes sense. I'm just going to put on I'll open up an image and show that on the screen to make a bit more sense of this. Let's have a look at this on the screen. So in the example on the screen here, you can see that the original value is 922.342.959. I wanted to show you how the various shift operations result in the 4 bytes being extracted for writing to the file. So you can see here by using that first line, I'll just put it over here so we can sort of see this as well, corresponding to the lines of code that this writeInt is using. And you can see in the first case, right shifting by 24 bits results in the value 00110110, which is hex 36 or 54 in decimal, being moved to the rightmost byte, with all other bytes containing 0. And as we move down, the next shift operation shifts right 16 bits. That's the 16 here on line 198. And so we get 36F9. And you can see the number there in binary. It actually gives us 001101. 1011111001 in binary, and that's just about the maximum number of digits I'm prepared to read out. So I'm going to give all the remaining examples in hex. So shifting right by 8 when the next line causes the 2F value to fall off to the right, and we get 36F9D6. You can see this on here, the third example. And then finally shifting right 0 place does nothing and the value is unchanged. So because only the single rightmost byte should be written each time, the shifted value is ANDed with the hex value FF, which is 000000FF when stored as an integer. So that results in a high 3 bytes being cleared to 0, giving the value that must be written to the file. Now you might be looking at that and thinking, Tim, what the heck are you going on about here? The point I'm wanting to make here with all of this is because we've got the data output class, the data output stream class, we don't have to worry about any of this. But there could be situations where you may have to deal with raw data streams at some point, so it's probably useful to understand what's going on. Now we can do that without getting too bogged down in binary. So in the next video I'm going to create a new Java file to hold a class called shiftInt, and we're going to print some values out that ultimately will be written out, just so we can sort of see what's happening at a lower level than you're probably used to. So let's work on that in the next video. So I hope I haven't freaked you out too much from the last class when I went into all this detail about what this right int does and shifting right and all this sort of stuff. But I am alluding to something. I'm getting to something that I want you to look at because it's really useful to understand what's going on at the low level. Not something you'll need to do all the time, but it's there if you need to. So what we're going to do is we're going to create a new class, and I'm going to call this one shift int. So I just want to go through this a little bit more. And I need to create so what I'm going to do, I'm going to paste some code in rather than typing it, and this code will be available in the resources section. The reason I'm pasting it in, it hasn't really got anything to do with the IO section. I'm just using it to show the 4 values that the right int method produces when it saves an int value to the binary stream. So in other words, there's no real advantage to you seeing me type this in. So I'm just going to copy this code and paste it in. And again, you can get this code in the resources section of this video, so you can do the same pasting that I did. So you can see what I've done is I've created my own right int method, and that's based on the right int method that was on screen at the start of this video. But what I've done also, I've used a display method to do some formatting so that the output's easy to read. And I've also used a technique that may not work on some Windows versions to show the rightmost 8 bits in a different color to make it easy to compare the ANDed values with the values that they were produced from. So if we actually run this program now, and you can see the values on the screen now. So the program, as you can see, and hopefully works on your Windows computer too if you've got one, it colors the last 8 bits purple. And you can see it obviously works on a Mac, and it will also work on most Linux distros. Now it also works on Windows 10, but there's a chance it won't work on earlier versions. The code itself will still run, but you might actually see strange codes instead of the color change. I've got the binary data that's showing in purple on the screen. So I've included the constants for other colors, so you can see on the screen there, in case you want to do this for console apps. But again, you might want to remember that it hasn't been tested on versions of Windows earlier than Windows 10. It should work, but we haven't tested that. Bottom line is, if it doesn't, you might want to try changing some of these colors. So we've got ANSI purple. We're using ANSI purple in here and the ANSI reset command. So try using, instead of purple, try using some other colors and see if that works. If and only if you're having difficulty getting this to work. So you can see that the original values written to the file as the 4 bytes 54, 219, this is numbers over here to the left hand side, 214 and 47. Now the output shows how those values were obtained by shifting the binary number right, then masking off all but the rightmost 8 bits. And that's what the code here on line 27, the AND 0xFF, that's what that's actually doing. So if this seems really complicated, then don't worry. The data output stream class does take care of writing Java primitive types, and there's also a corresponding data input stream class that reads them back in again. And in fact, let's switch over now and start having a look at that. In other words, reading that binary data that we created in the previous video back in. So say goodbye to shiftint.java. Okay. So getting back to our locations.java. So obviously we've got our main method now that we use to create the locations.dat file. And of course that used the binary output stream classes to do that. Now reading it back in again, it's actually easier than reading the data from a text file, and that's because we don't have to do any string parsing to get the integer values. So the data input stream class takes care of building primitive types such as int and double from the bytes in the file. So what I'm going to do is I'm going to comment out the existing code in the static initialization block, then we're going to add some new code to read from the binary file. So I'm just going to comment the lot out. This is in the static initialization block in our locations.java. Right down to the end of the class, to the method I should say. Then we'll come back up to the top now and let's add some code. So the code's going to be try. We're using a try with resources, so data input stream block file is equal to new data input stream new buffered input stream new file input stream file input stream, and the file name is going to be locations.dat, which was the file that we created in the last video. Okay, so that's our try with resources. There weren't too many brackets there. we're going to set up a loop while true. So we're going to break out of that loop once we've finished processing the data. So we're going to do map string integer. It's going to be exits is equal to a new, we'll do a linked hash map. And then we're going to do int lockid is equal to lockfile dot readInt. And there's our readInt method to retrieve that integer. And with this one, what we'll do is we'll actually catch an IO exception because we're not throwing it. So we'll just catch IO exception. And we'll just do a print out if there's an error, IO exception. String description. So I've read the location ID description is equal to lockfile dot, this time it's read, UTF to read the string. So we've got the ID and the description. So next we need to determine the number of exits. So that's going to be int num exits is equal to lockfile dot readInt again because that's an integer. So at this point we can do just print out some stuff to the console, read location and the number lock ID plus, and we'll just put the description there as well. And then we'll do found number of exits, the word exits. So now that we know how many exits there are, we can use a for loop. So for int I equals 0, I less than num exits, I plus plus, and string direction is equal to lockfile dot read UTF, reading in the string direction. Then with the destination, so destination is equal to lockfile dot readInt, and exits, we're going to put the exits dot put, and it's going to be the direction and the destination. So building up our map, destination, and then we just output that to the console, direction plus destination. Oops, destination. And then outside of the loop, after we've got all the exits, we can then save this entire location. So locations.put, and it's going to be location ID, then a new location class or object, which is going to need the location ID, the description, and then the exits. And we've already caught any potential exceptions, and that's all that exists in terms of the code. So you can see the old version I've commented out is actually longer than what we've written here, and I think you'd agree that this is also tidier. And the main reason it's tidier is because there's no parsing of the data required. It just sort of reads integers and strings using the methods in the data input stream class. So just to confirm, the code reads in the location ID, the description and the number of exits from that location, and then the exits can be read back in using a for loop, as you saw me code on line 42. The one strange thing you might have noticed is that the loop while true, which I started on line 35, hasn't got an apparent exit condition to terminate the loop. And in fact, if we come over here, we're actually getting an error from IntelliJ. If we open that up, while statements cannot complete without throwing an exception. So this isn't a particularly good way to write code, hence the warning. But if you attempt to write this by just referring to some of the examples on the internet, or even in the Java documentation, then this seems to be a reasonable way to do it. But before going into more detail in that, let's run the program to make sure it still works. So in here, we want to remember that we don't want to execute the main method from the locations class. We did that in the previous video so that we could create the locations.dat file. But what we want to do now is we want to run the main method from the main class so that we can actually test that the program is working. So I'm going to go back to the main class and just right click that and then run. And we can just try a few directions to make sure it's working. We'll go west, east, up, down, and quit. That seems to be working okay. And just to confirm again that the code in this static initialization block in our locations.java, that was executed, of course, when the locations class is loaded from the main method in the main class. Now, the Java documentation should be read carefully before applying it to your own code, and it's quite easy to pick up on the fact that the data stream readers throw an IO exception when there's no more data to be read from the stream. And in actual fact, they throw a subclass of IO exception called EOF exception, and we should really be checking for that as a way to terminate the while loop rather than just using the IO loop, the IO exception, as we've done in this code. And just to confirm, just to run this again, run the main.java method, run that again. Down here, IO exception, so you can see that that code was executed, the code that we added. I'll just disconnect that from our locations.java, so in the static initialization block, this exception was caught here. We caught that and then we outputted that as IO exception. But the point I'm making here is that how we've done this isn't really the best way of terminating the while loop. And that's because the IO exception is going to cause the program to jump out of the while loop and be caught in the catch block. But the code really is messy. Now, for example, what happens if an IO exception is raised for another reason than the end of file? So it's very difficult to treat a real exception, such as the input file not being found or having insufficient permission, to allow us to open it differently to the end of file being reached, which, in fact, is an expected event. Very few data streams are infinite after all. So the point is, it's very easy to cause an exception, but we'll just try to read the binary data from a file that doesn't exist by changing the file name up here on line 34, just to sort of simulate what will happen. So instead of locations, I'm going to call it location.dat. And if we go back to our main method and run that again, we can see we've got something different now. We've got exception, null pointer exception, which we would expect because the file doesn't exist. And you can see that obviously IO exception was printed, so the code in the catch block did execute. But if you were debugging this, was that because the data stream ran out of bytes, or was there some other reason? Now, without a detailed and time-consuming investigation, we've got no idea. So we'd really want to do this in a use a better mechanism to sort of determine what the error was. So the way to fix that is we're going to close this down and go back to our locations class. And what we're going to do is we're going to add another try block. We've got a few other lines as well. So within the first try block, we're going to add a boolean for end of file, set that to false initially. And then we're going to change the while. So it's no longer while true, it's going to be while not end of file. But then within this loop now, we want to add another try. Then we want to catch end of file exception, different exception to the IO exception, E. And the end of file exception, all we want to do there is set EOF to be equal to true. And then what we need to do is grab this other code here that was initially in the first loop, in the first try block rather, and paste that into the second or the second try block. And once we've done that, we've now got no other errors. So looking at that now, you can see we've got a boolean end of file equals false, and we're going to keep going until while not end of false, another end of file EOF. So in other words, we're going to keep going until while EOF is equal to false. If we do hit the end of file exception, which again is generated automatically by these classes when it reaches the end of input, we're going to set that to true, which will then exit the while loop automatically. So in other words, it causes the while loop to terminate nicely. But the other good point here is that any other exceptions are going to be caught by the try with resources catch block, the outer one. And if we go back to main.java and run that again, we'll see that we've still got that error because we've got the file name wrong. We changed the file name to a file name that doesn't exist. So if you were debugging this, you'd know that the problem isn't caused by the input stream running out of data. Now, obviously, in production code, we'd do more than just print a message in the catch block. We'd be logging the error, and the file name is the minimum we'd consider probably doing. And just to make sure this works, let's go back to locations.java and change our file name to the correct name again, locations.dat. Go back to main.java and right-click and run this. And we can see that the code is now working nicely. So working with byte streams is really no more complicated than reading and writing character streams, but you do have to know the format of the data that you're reading. Now in this example, we knew when to use readInt and when to use readUTF, and that's because we'd written the original file, so it was just a case of using the corresponding read methods in the same order as we'd used the write methods. So provided that you know the format of the data, reading from a byte stream is straightforward. Now of course, we also had to know the format of the text file, so that we knew when to try and convert the data to an int. But in the case of a text file, it's generally easy to open it in a text editor to work out the format of the data. And of course, as we've established when we opened the binary data file in the previous class, that's not so easy to explore. And for example, a sequence of 4 bytes in a binary file could be a single int value, 2 shorts, or 4 bytes, for example. And you wouldn't know that if you weren't involved in the process that created that binary file. And as a result, you want to know the format of the data by reading the specifications for the system that produced that binary file, so that you can write the code to import and read in that binary data. So as I mentioned, byte streams can be used when dealing with Java primitive types. In the next videos, we're going to have a look at how to handle binary I/O when dealing with objects. See you in that next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
So far, we've written the locations and directions data as text, as well as a binary stream. Right now, we read and write each object field individually. For example, we use readInt, writeInt methods to read and write a location's ID. And we use readUTF and writeUTF methods to read and write a location's description. Now, if an object has had 20 fields, we'd actually have to call 20 methods. So instead of that, we can use the object input stream and object output stream classes to read and write objects as a single unit. Now, when we write an object to a file, it has to be translated to a format that can be stored to a file and then reassembled into an object later when it's read by an application. Now, the process of translating a data structure or object into a format that can be stored and recreated is called serialization. Now in Java, when we want to use an object stream to write and read the objects of a class, we have to make the class serializable. Now we do so by making it implement the serializable interface. Now this interface has got no methods. It's just used to give the JVM a heads up that we may want to serialize the object to storage and to read it back again at some point. Now when we make a class serializable, it's strongly recommended that we declare a long field called serial version UID. Now if we don't do so, the compiler will give us a warning. Now this warning can usually be turned off when using an IDE and unfortunately sometimes off by default, and it will then calculate a default value for us. But however, different compiler implementations may calculate different default values, and that can lead to problems down the road if we change the compiler we're using. Now there are compilers, for example, other than the one included with the JDK. For example, a class compiled with the standard Oracle compiler for a desktop application would be compiled by a different compiler if we were to add it to an Android project. So for that reason, it's recommended that if we care about serialization, we actually set the serial version UID field ourselves. So we set that value. And it's recommended that the field be private, since no other class should have to use it. So what is this serial version UID field used for? Well, think of it as a sort of a version number for the class. Now, if we don't explicitly set it, the compiler will create it based on class details, such as the number of fields and methods, etc. And if we ever change a class, for example, by adding another field or method, or change a field type, we'd have to change the serial version UID value. When we read an object from a stream, the runtime checks the stored serial version UID against the one contained within the compiled class file. If they don't match, then there's a compatibility problem and the runtime will throw an invalid class exception. Now, if we wanted later versions of an application to be able to load files created by earlier versions, we'd have to provide custom versions of the write object and read object methods by overriding them, which are methods we use to read and write objects. So the bottom line here is that we don't have to worry about declaring a serial version UID field unless A, we explicitly use serialization, as we do when we use object input stream and the object output stream classes, and B, there may be a compatibility issue down the road. But some developers and the Java documentation recommend always declaring when A is true, that's when we explicitly use serialization, or whether B also is true. And that's there may be compatibility issues down the road. So with that theory out of the way, let's actually go ahead and modify our code to use the object input stream and object output stream classes. Our first step is to make the location class serializable by having it implement the serializable interface. Let's go and have a look at that. So location. So we just want to change this now. Public class location. We're going to do implements serializable. And noticing that's in the java.io package. Now we don't get any errors about unimplemented methods, and that's because serializable doesn't actually have any. Right, so if we take a look at our location class, we notice that at the moment it's actually got 3 fields, an int, a string, and a map. Now int and string are primitive types, but map is an object. So will that be serialized when a location object is written to a file? Well, in our case it will be, because linked hash map implements the serializable interface. So we're actually in luck here. When we write a location object, the entire contents of the exits field will also be serialized. Now if linked hash map didn't implement serializable, we'd actually be responsible for writing the code to store its content to the file ourselves. Now ideally, when we want an object to be serializable, all its fields will also be serializable. So you have to keep that in mind when writing your own classes. If a class we want to serialize will have fields from other classes that you write, then you need to make sure those other classes are serializable as well. But as I mentioned, we're in luck for this application, so serializing location objects to a file will be straightforward. Alright, so our next step is to declare and assign the serial version UID field in location. So we're just going to start by doing that, and we're going to assign it the number 1 because it's version 1. So we'll do that as private long, and it's serial version UID, making sure you get exact spelling there with case, equals 1L. And at the moment, if we have a look at that, IntelliJ is complaining that this field's never used. But unfortunately, that's because it doesn't recognize the field as the recommended one to include with serialization. So next what we're going to do is modify the locations.main method to write the location objects using an object output stream. So let's go and have a look at locations. So we've got our main method here. Now remember that when the class is loaded, the static initializer will run and read the locations from the locations.dat file. So that's this code down here in the static initializer block. So by the time the main method runs, we know the locations are loaded and available to use. So looking at the code that's there now, what I'm going to do is comment that out and write the replacement code. So I'm just going to comment that out so we've got that there. We need to refer back to it at some point. And actually what I'll do is I'll take a copy of this first line because that's going to be the same try with resources. So I'll paste that in and remove the comment. And in terms of writing the objects, we just type for location, location. It's going to be locations.values. And it's log file dot write object location. But instead of using the data output stream, we're going to use the object output stream, like so. So I think you agree that looking at the code that we've replaced, that we've considerably simplified the code. Now since location is serializable and all the non-primitive fields in location are serializable, all we really have to do is call write object for each location object as we've done here on line 31, and we're actually done. And also you can see that we can use a buffered output stream to buffer the output, so I'm using that there still. So literally all we had to do, which you saw me do, was change the data output stream object to an object output stream as we did there and there on line 29. Alright, so let's now run this locations main method, and this is not the applications main method, this is the main method in locations. So I'm going to right click that, run locations.main. Alright, so that's run okay without any errors. So let's actually have a look at the locations.dat file. So I'm just going to double click that. Now you can see here that it's less human readable than it was before, And in fact, we're getting this error here that IntelliJ is telling us that the document contains very long lines and soft wraps were forcibly enabled to improve editor performance. And also a note here about the wrong encoding. But that's actually fine, because a file containing serialized objects is meant to be read by a Java application and not by a human or an IDE for that matter. Now we'll notice that right at the top of the file here, you can see that the package name's there. And if you look carefully, you can actually see there's actually some class names as well. So before we move on to reading the objects, note that the object output stream implements the data output interface, and the object input stream implements the data input stream. Now the data input and data output interfaces contain the declarations for the write-int, read-int, as well as write UTF and read UTF methods and other read-write specific type methods. Because of that, object streams can contain a mix of serialized objects and primitive types. So in other words, they're not limited to only containing serialized objects. In our case, we don't need to mix objects and primitives, but we could do it if we actually needed to. Alright, so let's close down this locations.dat file because we really don't need that anymore. The next thing we want to do though is back in locations.java, we want to actually have a look at modifying the static initializer block. And again, what I'm going to do here, I think for simplicity, I'm going to actually just comment out the whole while loop, because that's basically the major part that we're changing there, and I'll just type that in again. First thing we'll do is we'll change the data input stream again to an object input stream, and just repeat it. And I'll write it up here, the new code. So we're going to start with while, not EOF, so that code doesn't change. And we're going to add a try. We'll do location equals casted as a location, lock file dot read object, and print out read location plus location dot get location ID plus a colon there to separate it, plus location dot get description. Then on the next line we'll print found plus location dot get exits dot size plus exits. Then we'll do locations dot put. It's going to be location dot get location ID, comma, and then location. So the error we want to catch here will be a end of file exception. So EOF exception E, and we'll set EOF to be equal to true, which will exit the while loop. And in terms of catching errors, and I might just put this code up the top here so it's all together. We're catching an IO exception, but also we need to catch this exception as well, the class not found exception. So I'm going to do a catch, class not found exception. We're just going to print out a message if that happens. Class not found exception. Do e.get message. Perhaps we'll do that as well if we get one. Okay. So a few things to note. Firstly, once again, I'm sure you'd agree the code has been greatly simplified. We changed the data input stream that was on line 39 to object input stream, but the rest of the try statement pretty much remained the same. And that's because we're still using this buffered input stream to buffer the data. Now reading a location object, which we're doing here on line 43, well, that actually takes care of reading all its fields and exits. The read object method returns an object, so we have to cast it to a location object, which again we're doing on line 43. Now once the object is read, all we have to do is add it to the locations map in the locations class, which we're doing here on line 47. We're also printing out the information, as you can see there, on lines 44 and 45. But this time we're getting the values from the location object created by the read object call on line 43. Now in addition to IO exception, you saw me having to add another catch, which was the class not found exception. And that's here on line 54. Now this is going to be thrown when the runtime reads an object from the stream and it can't find the corresponding class on the class path. Now, for example, if another application that didn't contain the location class tries to read the objects inside the locations.dat file, then it would actually get a class not found exception. Right, so let's end the video here because it's getting a little bit long. In the next video, we'll come back and we'll run this locations.main method and check that the static initializer block code is actually working as well. So see you in the next video. Alright, so in the previous video, we wrote this code and made some changes and talked about catching this class not found exception. So let's actually now try running this to make sure that our main method, again this is in locations.main, not in the main class, making sure this still actually runs. So we'll actually run this again. And we can scroll up there. You can see that all the locations are printed to the console, so that means we're still reading the objects from the file correctly. So now that we can see that that's still working okay with our locations.java main method, let's go back and run the applications main method to make sure the game's still working. That seems to be working fine still. We'll quit out of that. So game's still working, and our code, I think you'd agree, looking at it now, is a lot easier to read. And because I've saved this in the previous video now, the commented out code, I'll remove this from the source code. And likewise for this commented out code in our static initializer block. Let's also remove that code as well, just to clear things up a bit. But the point is though, looking at that code now, there's our main method in our locations class and the static initializer block, and it's far more concise, I think you'd agree, and also easier to read. Now for fun, let's actually temporarily comment out the declaration of the serial version UID in the location class. Come up here and just comment that out. We go back to the main method and run it again. You see we've now got an error. In this case we've got originally an IO exception, and then ultimately we've got a null pointer exception as the result of that one. And so it's coming back from that other class. And that's because we didn't explicitly set the serial version ID. Because we didn't do that, the compiler assigned one when it recompiled the location class. But this means that it no longer matches the value we wrote to the file, which if you recall was 1L. Now because of that, the exception is thrown when we try to read objects from the file. So in order to get this to work again, and if I just run it again, we'll get the same result, it'll crash. We actually have to then uncomment it from the location class to get our application to run again. And here's our application running again. But actually what I should do is just show you something else. I'm going to go back and just comment that out again. Now, in the previous video, I talked about the fact that an invalid class exception would be thrown when the serial version UIDs don't match. Invalid class exception is a subclass of IO exception, and so the existing catch block also catches the invalid class exception. So let's actually go back and add the invalid class exception to the static initializer code in the locations class. We'll catch that. So we've got IO exception here, so let's actually catch that first. Catch invalid class exception, and we can just do a print out invalid class exception plus e.getMessage. I'll just put a space there because that didn't have one in the output before. So now if we run that, we actually see the invalid class exception showing up there because the serial version UIDs no longer match. Right, and again we'll just go back to the location class and we'll uncomment the serial version UID, run it again. We should find that it works. Okay. Now before we leave this topic, let's touch on what happens when two objects that we serialize point to the same object. And as an example, let's say we want to serialize a class called foo, which contains a field for a bar object. Now if two foo instances point to the exact same bar instance and we serialize the two foo instances to a file, the question is, will the file contain two bar objects or just one? Well, the answer is that it'll only contain one. Since both foo instances refer to the same bar instance, only one bar instance is serialized. So in other words, a serialized file will only ever contain one copy of the same instance. So that's pretty cool. But now imagine that we want to do the same thing, but for some reason we want to create two files. So we write both foo instances to file 1 and then both to file 2. So how many instances of bar will be written this time? Well, the answer in that case is 2. Object instances will be unique within a file, but not across files. So in this case, when the two files are read back into an application, two distinct instances of bar would be created. Now this may not matter, but it could, which is why it's important to understand that that can happen in this case. Of course, in the two file case, there could also be two instances of each foo object read back in as well. Alright, so to close the section on the java.io package, we're going to take a look at the java.io.randomaccess file class. Now, so far we've been reading and writing files sequentially. We start at byte 0 and we read or write bytes one after the other until we reach the end of file or until we finish writing the data. So we don't jump around in the file, in other words. For example, we don't read bytes 20 to 35 in the file and then read bytes 50 to 100 and then bytes 10 to 15. And likewise, we don't write out bytes 100 to 150 and then bytes 20 to 30. So far, we've only moved forward and we've done so without skipping any bytes. Now, let's actually say that we have thousands of locations in our file, so many that we don't want to store the locations in memory because they take up too much room. So instead, every time a player moved to a new location, we'd read that location from the file. So to do that, we'd need to jump to the place in the file where the information for that location is stored. Rather than reading the file sequentially, we'd need to read it in a random fashion, in other words. So this is where the random access file class comes in. Now honestly, it would be far more efficient if in that scenario to use an embedded database like SQLite, especially when we've got two data sets that are related to each other, as we do in this case with the locations and the exits. Because of course every location has a set of exits. But let's just pretend that for whatever reason we have to use a flat file. Now when accessing a file in a random fashion, it's important to understand the concept of a file pointer. Now the file pointer is an offset in the file where the next read or write will start from. Now for example, if the file pointer is set to 100, then the next time we call a read or write method, the read or write will start at byte position 100 in the file. Now if we're reading an int, the bytes at positions 100 to 103 would be read, since an int is 4 bytes. The byte position is 0 based, so the first byte in the file is at position 0. Whenever we read or write the file pointer is advanced by the number of bytes we read or wrote. So for example, if the file pointer is equal to 100 and we read 5 bytes, then the file pointer will be equal to 105 after the read-write has taken place. Now also we use the term offset when randomly accessing files. So an offset is a byte location in the file. So for example, if the value has an offset of 100, that would mean that the value is located at byte 100 in the file, so we'd want the file pointer to be set to 100 when we read-write the value. Now the value could of course occupy more than one byte, but the offset is where the value's first byte is located. The remaining bytes would follow that first byte sequentially. Now when using random access files, we refer to each set of related data as a record. In our application, the location ID, description and exits make up the record for a location. When the user moves to a location, how will we know which bytes to be read from the file? Well, if all the locations occupied the same length and we wrote them out in order, location 1 followed by location 2 followed by location 3, etc., well, that would be easy. We could figure out a location's offset from its location ID and the fixed location length. For example, let's say every location occupied 30 bytes in our file. So the first location's offset would be 0 and its data would occupy bytes 0 through 29. And the second location would begin at byte 0 and end at byte 59, etc. And when a player moved to location N, we'd figure out which bytes to read using a formula, assuming location IDs were 1 base. So the formula would be something like, let's put this in a comment, start byte equals, and it'd be ntate1 times 30. Again, that assumes that each location occupied 30 bytes in the file, and N is location here. So that would be great if we knew that each location was of a fixed length. But unfortunately, our records don't have the same length. The length for each location is different, and that's because the description length and the number of exits differ from location to location. So because of that, we have to include an index in our file. I'm just going to delete that comment. And that index stores the offset and record length for each location. And we also have to include the location ID in the index. Now, given that, reading a location is going to be a two-step process. Firstly, we're going to get the index record for the location. Then secondly, we're going to use the index values and read the location data. Now, I'm going to go through a bit more theory about what we're going to do here, and then we'll end this video, and then in the next one, we'll actually start the coding. So getting back to what we're trying to do here with this two-step process, firstly, we're going to get the index record for the location, and secondly, use the index values to read the location data. So every index record has to be the same length. We wouldn't want to have an index for the index after all. Now, typically an index contains a unique identifier for each data record, the offset of the record in the file, and the length of the record. Now in Java, that's 12 bytes. The index for our application is going to contain the location ID, the location's offset, and its record length, which matches the typical case. Now, because of the description, a location record will always be longer than 12 bytes, so the index will be much smaller than the location's data. Now, we can access the index record we need by reading it from the file when the user moves to a new location, or we could load the entire index into memory when the application starts. Ideally, we'd want to load the index into memory. And the obvious reason for that is that accessing memory is much faster than accessing files on disk, so loading the index into memory will always provide better performance. Now, usually the size of each index record will be smaller than the size of the data records. But when that isn't the case, then of course it wouldn't make sense to load the index into memory if we're using a random access file because memory is tight. So if we're using a random access file for other reasons, then it'll really depend on a specific case. Another important point, I've been saying that the first data record starts at byte 0, but that actually won't be the case if we write the index before the data. We have to save the offset of the data section, which in our case is the locations, to the file. And that's typically saved near the top of the file. Now, sometimes the number of data records would also be saved there. Now, for our application, we're actually going to load the index into memory. So our file format will look like the following. And I'm just going to put some comments in here as well. So firstly, we're going to have the first 4 bytes. It's going to contain the number of locations. So that's bytes 0 through 3. And let's put this in the right place. I've got this comment at the moment in the main class. Let's go back to locations and put it in there. And we'll just put it the comment just above the static initializer block. So firstly, the first 4 bytes are going to contain the number of locations in our game. Secondly, the next 4 bytes we are going to contain. It's going to contain the start offset of the location section. That's bytes 4 through 7. Thirdly, the next section of the file is going to contain the index. Now the index is 1692 bytes long, so it'll start at byte 8 and end at byte 1699. Okay, and then lastly, the final section of the file is going to contain the location records, the actual data for the game. and that's going to start at byte 1700. So when we want to move to a specific offset, what we'll do is we'll use the random access file.seek method to move the file pointer. Now we won't always have to do this. When we want to do a bunch of sequential read-writes, we'll start by positioning the file pointer to the offset of where the first read-write will take place. Now if the next read-write we want to do will immediately follow the previous one, we can just use the read int, the read long, the read UTF, etc., and the corresponding functions write int, write long, write UTF, etc., and we've seen those methods that we'll be using those as we've used them before. The file pointer is always advanced by the number of bytes read or written, so if the next piece of data we want to read-write immediately followed the last piece that we read or wrote, then the file pointer will be already positioned correctly. So in that case we wouldn't need to call seek first. So we only really have to call the seek method when we want to jump to a different offset in the file. And we'll see examples of this as we move forward. Alright, so let's finish the video here now. In the next video, we're going to start by changing our application to use a random access file and to load these locations on demand. So I'll see you in the next video. Alright, so we talked about random access in the last video. So let's get started on changing our application to use a random access file and then to load these locations for the game on demand. Now, because we're going to have to change quite a bit of existing code, and also because it'd be nice to keep your existing project, the one we've worked on here to date, as a reference, what we're going to do is use a new project. Or rather, we're going to copy this project and create a backup version of it. So the easiest way to do that is to have the project open, which I've got, just to select the project up here and right click. And on a Mac I can reveal in Finder, and on Windows or Linux there should be an option, something like Open in Explorer or Open Folder or something like that. So click on that, and that takes you to the folder where that project is. So I'm going to just copy that. I'm going to copy and paste that. And you can see in my case on a Mac it's duplicated the folder. So you'll do something similar for your operating system. And I'm actually going to change the name of this. Instead of input output copy, I'm going to change that. And I'm going to call it something completely different, Adventure Random. Because it really is the adventure game that we've been talking about and working on recently. And you can see that's been renamed. Now that I've done that, I'm going to close this project down. And then I'm going to navigate to that folder and open the new project. And again, we're doing this so that we can make changes to this code freely. And we don't have to worry about losing the original code we had. And Adventure Random is the name of the project, so I'm going to open that. Alright, so you can see now that I've got the Adventure Random project that I just copied and duplicated from our previous project open, and we're going to work on that moving forward now. And just before we start, let's just make sure that it still works. Right click and run. I'm running the main class's main method. And it looks to me that it's still going to work okay, but we'll just test this out a little bit. And I'll just put this up a little bit so we can see this a little bit better. North, southeast, and quit. That's working fine. Okay. All right. Now we're going to use the locations.main method to use random access file to write out the locations. So our first step is going to be to write the number of locations to the file. So I'm going to open our locations class, and again we're making the change in the main method in locations.java, so up here. So our first step, as I mentioned, is to write the number of locations to the file. Now since the file pointer is positioned at byte 0 when a file is first created or opened, we don't have to call the seek method that I talked about in the previous video. So consequently it's pretty straightforward. All we really need to do is with this try, we're going to change this, instead of an object output stream, it's going to be random access file. And we'll call this an RAO is equal to new random access file. We're going to change the name of the file as well. So locations underscore rand.dat. The second parameter is rwd, which we'll talk about shortly. I'll get rid of this other code. And the code is raw.writeInt. And it's going to be locations.size. So again, it's the number of locations that we've got at the moment. We're writing that to our random access file, locations_rand.dat. Now I've called it RAO here because we're going to be loading locations on demand when we run the game. Now the locations data file will have to remain open while the application runs. So we're going to call the variable we use to read the file something different so we don't confuse it with the one that we're using here, which is the one that we're writing the locations with. Alright, so the first argument to random access file is locations_rand.dat, and clearly that's the file name, the name of the file that we're writing it to. But this second option here, well, that indicates that we want to open the file for reading and writing, and also that we want writes to occur synchronously. Now you can open a file as read-only. We can also not specify that updates to the file have to occur synchronously, but if we do that and multiple threads can access the file, you'd actually be responsible for synchronizing the code yourself. So in this case, it doesn't matter since only one thread will access the file. But generally speaking, it's good practice to have the random access file class handle the synchronization when it does matter. So using RWD as we've used here on line 14 as the second argument is a good idea. Alright, so we've written out the number of locations so far to the file. What we'll do now is we're going to write the start offset of the locations section. And once again, since the file pointer is already positioned correctly, we can just go ahead and use writeInt. So we're going to type int index size is equal to locations.size times 3 times integer.bytes. Then we're going to do int location start equals int index size plus RAO dot get file pointer plus integer dot bytes. Then we're going to do RAO dot writeInt. It's going to be location start. Alright, so each index record will contain 3 integers: the location ID, the offset for the location, and the size or length of the location record. Now we're calculating the index size by multiplying the number of locations by the number of ints contained in each record, in this case 3 by the number of bytes contained in an integer. So you can see that we've done that here on line 16. So locations.size gives us the number of locations. We're multiplying it by 3. And again, the reason we're doing 3 is because our index is going to store the location ID, also the offset for the location, and then the size or length of the location record. And then we're multiplying that by the size of an integer, and we're getting that by using the integer class .bytes. So once we've done that, on the next line, we then calculate the current position of the file pointer to the index size to account for the value that we've already written to the file. And we also have to account for the integer we're about to write to the file, the location section offset we just calculated. So we also have to add the number of bytes to an integer. So we're doing that down here on the end of that line. So this will give us the offset for the location section. Now, as an alternative, we could also have added the index size to the size of 2 bytes, but I like to use the file pointer wherever possible, and I suggest that you should probably do that as well. And over here, we had to cast to an int, and that's because the file pointer is a long value. Now, we could have written a long, but we're going to read and write ints wherever possible. And I suggest you do that. And if you were working with an application with lots of data, such that the file offsets could be larger than an int could hold, then of course you'd have to stick to using longs to make sure you didn't exceed the maximum size of an int. Alright, so we've written out that location start now. Now the next section in the file is the index. But before we can write the index, we have to write the locations, and that's because each index record requires the offset for the location, and of course we don't know the offset until we've written the location. Now I guess we could write a location and then write the index record for it, and then write the next location and then write the index record for it, and so on and so forth, but that would actually involve a lot of jumping back and forth in the file. Now disk access is expensive, and it's even more expensive when it's not sequential. So instead what we're going to do is write all the locations and then we'll write the index as a whole. Now to do that, what we have to do is build the index in memory as we write the locations. Now because we want to jump back to the file when we've finished writing the locations, we'll save the current position of the file pointer so that we can jump back to it when we want to write the index. Since we'll write the index after the two integers we've already written, we'd be writing it to offset 8, which is where the file pointer is currently positioned after writing the number of locations and the locations section offset. Alright, so what we'll do there, some code long, index start is equal to rao.getFilePointer. Alright, at this point we're ready to write the locations. Now we've already calculated the offset of the locations data section. Now we're going to assign that to a variable called startPointer, which will update after writing each location. And then we'll loop through the locations, write out each location, create an index for it, and add an index record to a map. Now to do all this, we really need an index record class. So we're going to add a new Java class called index record to our project. So let's go ahead and do that. New class, index record. So we're going to have two fields here, the private int start byte, which I mentioned, and private int length. We want a constructor, and the constructor should accept both parameters and save those to the fields. And let's also set up pass some getters and setters for this as well, for both of them. Alright, so there's our class, pretty simple. Now we said that an index record could contain the location ID, start, offset and length, and when we load the index records into memory, the location ID will act as a map key, and that's why we don't have to store it in the class, in case you're wondering. Right, so let's go back to our locations class and write out each location. Now I'm going to type in all the code first and then we'll discuss it. So we're going to start with and I'll just split this code up a little bit so it's easy to read. We'll start with an int start pointer, and that's equal to location start, and rao.seek start pointer. We're going to do for location, and locations dot values. Then we're going to do rao.writeInt, and it's going to be location dot get location ID. rao.writeUTF, and that's going to be the description, so location.getDescription. Then we want to create a string builder, so string builder is equal to new string builder, and then we're going to do for string direction, then location.getExits.keyset. If not direction is equal to quit or equals ignore case Q. So if it's not quit, we're going to do builder.append direction. Then we want to do builder.append a comma builder.append location.getExits.get direction. And then builder.append another comma. Okay, and then just move this up a little bit. Then it's going to be rao.writeUTF, and it's going to be builder to string. And obviously I'm one level too deep. That actually should have been there, of course. We still want to stay in the for loop. And we also need to create our index record. So index record, remember we're writing the indexes later, but we need to build up this index in memory first. And so new index record, the first parameter is going to be start pointer. Then we also want to store an int, or cast that as an int, which will be the rao.getFilePointer take start pointer. Index.put, we need to create that in a minute. So location.getLocationID, and then the actual record, the index record itself. And then we need to update start pointer. So start pointer will then equal cast as an int rao.getFilePointer, whatever the current file pointer is. Right, so let's actually just add our index field. I'm going to go ahead and add it up here. So it's going to be private static. It's going to be map integer index record index equal to new. And it's going to be linked hash map, which obviously makes sense for our application, given there's a list of rooms that all link to each other in some way. So I'll initialize it like that. And that should mean that the code's ready to go. Now we've still got a bit of work to do on this. The video is getting a little bit long here. So let's pause the video and continue on this in the next video. Alright, so at the end of the last video, we typed in this code and we didn't really go through what it's all about. So let's look at doing that now. So we start off here on line 23, and we set the offset for the first location into a variable you can see there called start pointer. Now we need to use this value to calculate a location's record length after we've written it to the file. Alright, so once we've done that, we then use the seek method on line 24 to move the file pointer to the first location's offset. Now we only have to do this for the first location because after that we write all the data sequentially. Now for each location, you can see down here we're actually writing the location ID on line 27, the description on line 28, and also then the exits for each location. And you can see the code for the exits basically on line 30 right down here to finishing off on line 37. Now that's the same manner that we've written them out in the past. Now one drawback to using the random access file is that we can't read-write objects. The random access file class doesn't contain read object and write object methods, unfortunately. So it's back to writing each piece of data individually. Now also notice that we're not using a buffered stream. It wouldn't make sense when accessing a file randomly because buffering is just like a queue. What goes in first is read or written first. So in other words, it's sequential. So random access file can't be chained with other types of IO classes. Also, unlike the stream and file classes we've previously used, it can be used for both reading and writing. So when we actually write a location, we build an exit string that looks like the following. This is the code here that you can see that we've used with the string builder. So it's basically what we're trying to do there is something along these lines that we're writing out. It's going to be direction, location ID, direction, location ID. So as an example of what we'd be writing out, it'd be something like N1, U2 for north, then the location ID of 1, and then up would be the location ID 2. So that's actually what this is trying to do when we're actually writing that out. Now the string ends with a trailing comma. You might be wondering about that on line 35, which we don't need, and if we wanted to be diligent, would not write it for the last location. But it doesn't actually harm anything, and this space isn't a problem for this file, so we're not going to check for the last exit case and try and remove that last comma. Alright, so after we've written the data, and obviously there is where we're writing the exits on line 38. So after we've done that, we've come down here to this code starting on line 40, and we create the index record for it. Now the start byte for this location is equal to the start pointer value, and the record length one, and that's what we've got the value there in the index record that we're actually passing, and the record length is the current position of the file pointer, which we're getting here with rao.getFilePointer, but then we're deducting the start pointer. So it's the current position of the file pointer minus the start pointer. And we're then adding the index record for the location using the location ID as the key on line 41, and then we update the start pointer for the next location, line 43. Alright, so that's actually the code. So at this point we've now written the locations to the file, and we can now write our index because we've got the full list of indexes available. So let's go ahead and do that now. And the code for that will be down here because we want to make sure that we've written out all the locations which we have there from the for each that we've got on line 26. So down here what we want to do is do an rao.seek. We're going to seek the index start. Then we're going to do for integer location ID, and it's going to be index.keyset rao.write int location ID, and rao.write int, it's going to be index.get location ID dot get start byte, and then finally rao.write int again, index.get, and it's going to be location ID again. This time the pointer is .get length, or the result rather is get length. Alright, so hopefully you look at that code and think it's fairly straightforward. So we're seeking to the offset that we've saved previously on line 46. So that's where we're doing the seek, and index start was actually defined up here. So we set that to the offset previously, so we knew what that would be. So going back to that location again, then we're just looping through all the index records using the index.keyset and actually writing them to the file. Right, so let's actually run now the locations.main and actually just confirm that it actually works. And we might check out the file that it's created as well, just to see what that looks like. Alright, you can see we've got something written out there. We've also got this locations_ran.dat, so double click on that. So you can see at the top of the file here, this is a part where we're saving lots of ints. You can see that it isn't really readable, but if you look down here, you can see that we've got some strings in the location section that do appear to make a bit more sense. And you can see the actual exits there, east 12, west 14, comma, etc. So it doesn't all make sense, but again, it's not a human readable file, but you can hopefully see the gist of what we've done with this random file now. Right, so let's close that down. And what we want to do now is change the static initializer so that it reads the index from the file. So I'll go back and have a look at our static initializer here. Now, remember that we won't be loading the locations into memory anymore. We load locations on demand. Now what that means is that our locations.main method will no longer work because it depends on all the locations being loaded into memory. So if we wanted to run the method again, we'd have to change the static initializer to load all the locations, but then that would defeat the purpose. So because of that, what I'm going to recommend here is that if you need to run the locations.main again, you copy the static initializer that uses a buffered reader or input stream from the older project into this project's locations class, and this will read the locations from locations_big.txt into the locations map. Once you've done that, you then comment out the random access file static initializer. Run the locations main method and then comment out the old static initializer, and finally uncomment the old one that uses the random access file. Now because you may have to do that if something goes wrong and you want to write out the locations file again, we'll actually leave the class as is in terms of extending map and declaring a locations map. So hopefully that makes sense. So if you do need to access that again, go through the process that I've just outlined, and that will work. But with a bit of luck, you won't need to do that anymore anyway, now that we've got it working. Alright, so let's now write the static initializer that uses the random access file. First, we have to declare a field for the random access file. So let's go up and do that. And I'll declare it just below the index here that we set up. So we're going to call this one all private static. It's going to be a random access file, we'll call it array. Okay, back to our static initializer block. Alright, so let's go through and put the code, type the code in, and then we'll discuss it. And what I'll do is for now is I'm just going to comment out the old code, because it'll probably make more sense to see me type it from scratch. Right, so we'll start with a try, then we want to catch an IO exception. And we'll just print out a message if we happen to get an exception. Okay, and in terms of the actual code, we'll start with array equals new random access file, and of course it's going to be locations_ran.dat, the file we just created, and rwd for the access. int num locations equals ra.readInt, and then long location start point is equal to ra.readInt. Then we're going to do a while ra.getFilePointer is less than location start point, and then int location ID is equal to ra.readInt. Int location start is equal to ra.readInt. And int location length is equal to ra.readInt. Then create our index record. So index record is equal to new index record, and the two arguments will be location start and location length. And index.put location ID and record. And that's our code. So we open the file, as you can see here on line 66. And then we read the number of locations into a variable on line 67, and also the offset of the location section on line 68. Then we load the index into memory. Now to read the index, we're looping through until the file pointer reaches the location's offset. So we're doing the code, the while loop that we've typed in here, and we're reading the index and creating the records as we go. And I think that's pretty straightforward. As you can see there, we're creating a new index record and then just saving that. So we're not actually using the number of locations, but it's a good practice to write the number of records in each file section at the beginning of a file that will be accessed in a random fashion. So we might need this later on if we were to modify the application. So in case you're wondering why that wasn't used, that's the reason there. So that's really for future reference. And again, it's good practice to do that in my opinion. All right, so at this point, we're actually done. We've written the static initializer block. Well, actually, no, we're not done. Our application won't work. And remember, the way that it's currently written, it assumes that the locations are all available in memory. But of course, that's no longer true anymore. When a player moves to a location, we have to load that location from the data file. So let's start working on that in the next video. All right, so at this point, we're actually done. Well, as I said in the last video, no, we're not done. And in fact, our application won't work at the moment. Now remember that the way it's currently written, it assumes that the locations are all available in memory. So it actually loads all the locations in memory. But of course, that's now no longer true. What we need to do is now when a player moves to a location, we have to load that location from the random access file that we've created. So to achieve that, what we need firstly is a getLocation method in the locations class. And we also have to close the file when the player quits. So we'll need to add a close method as well. So let's start off by adding the close method, mainly because it's easy. So I'm going to go back to locations.java. And we'll just add one right at the bottom. Public void close. We're going to throw the IO exception. And it's going to be simply ra.close. Closing the random access file when the player quits the game. Now the reason that we're throwing the IO exception is that we're going to let all the exceptions bubble up to the operating system, meaning that the application is going to exit and the exception will be written to the console. So in other words, we're not going to be doing any processing with any exceptions we do get. All right, so the next thing we need to add is a getLocation method. And this is going to be used anytime the player moves to a new location. And what I might do is just put that code back up here towards the top. And I'm going to delete this old static initializer block code because we no longer need that. We obviously replaced that. And so let's use this location for our getLocation method. So we'll need to return a location object. So we're going to do public location, getLocation. And we're going to get the location ID passed as an argument. So location ID. And we're also going to throw an IO exception and not deal with those directly in this method. All right, so firstly we need to get the index record for this location. So it's going to be index record is equal to index.get, and it's going to be the location ID that's passed as an argument to this method. And next we want to start accessing the file, the random access file. So it's going to be ra.seek record.getStartByte. So we're pointing to the correct offset so that we've got access to this location from the random access file. Let's read the ID. Int ID is equal to ra.read int. Then we want to read the description of the room. That's equal to ra.read UTF. Exits is the next thing, so we're going to do string exits is equal to ra.read UTF again, because it's a string. And then we want to extract the various exits, which if you remember are actually saved with commas between them. So we'll create a string array to do that. String array exit part is equal to a new string, and it's going to be exits dot split and a comma. So we're actually getting all the various exits for this particular location and storing them in a string array exit part. All right, next thing we need to do now is create a new location. So it's going to be location. Location is equal to a new location. We're going to pass the location ID, the ID of the room, and then also the description. And for the third argument, for the exits, we're going to pass that null initially. And the reason for that, if we go back and have a look at our location class, we can see that the constructor, the third parameter, is exits. And from previous videos in this course, we've worked on the location class. And you can see here we've got a test that if the exits are passed to the constructor, then we're creating a new linked hash map. Otherwise, we're just creating a new empty hash map, a linked hash map. And then we're actually adding, in either case, a default exit for quitting, which is for location ID 0. So, in other words, we're using the constructor here where we haven't yet got the exits, and that's because we're going to create those and then manually update them. All right, so we're passing null, as I mentioned, as the third argument. So it is still initializing the exits in the location. So consequently, what we need to do now is we need to send the exits. So we'll do a test here to make sure we're not dealing with location ID 0, which is the one that we've set up to quit the game. So if location ID is not equal to 0, then we're going to go through all the exits that we find and add them one at a time to the location. So for int I equals 0, I is less than exit part, our array dot length I++. And then for each one, let's actually print out a message. So we'll start with exit part is equal to plus exit part I. And then we'll also do exit part plus 1 is equal to plus exit part I plus 1. So we're just printing out what we can see in the array. Let's now get the direction. So it's going to be string direction is equal to exit part I. So we're grabbing the actual direction for the location, and then the destination is equal to integer dot parseInt, and it's going to be exit part then plus plus I. So incrementing I first and then grabbing that element, because if you recall, the exits is the actual direction and then also the location ID where that direction goes to, which room effectively or which location it leads to. All right, so we've now got our direction and our destination. We can add that to the location. So location dot add exit, and it's going to be direction destination. And then all importantly, we need to return the location that we've actually built up in this method. So that should now grab the location from the random access file. It builds up obviously the description and the exits, creates a location object, and then adds the various exits to the location and then returns that. So again, just going through this, we're starting off here on line 87. We're getting the start byte. So we're moving the file pointer to the location's offset by using the seek method from our random access file. And as I mentioned previously, even though we know the ID, we're actually retrieving the location ID because we stored that when we wrote. And I mentioned that's good practice to do that anyway, in case for some reason you wanted to access it without knowing the location ID. We've got that information on file. So it's really more or less a sanity test is what we're using that for. So we have to skip past that because we've recorded that, then move on to the description on line 89. And by the way, in case you're wondering how the read UTF method knows how many bytes to read, because after all, if you think about it, it can't really know how long the description is by magic. Well, the reason it knows is because the write UTF method, it actually writes the length of the string followed by the string itself. So therefore, the read UTF method reads the length first, and then it reads the appropriate number of bytes. So that's all happening behind the scenes, which is pretty cool. Right, so after getting the description on line 89, we're then retrieving the exits, and then we're extracting that into a string array, which you saw on line 91, and creating a new location object that initially has no exits. And then from lines 96 through 101, we're actually adding the exits to the location. And I added new string exits here. I didn't have to do that. I could have just changed that, by the way, and just made that exits. Either way will actually work there. It's probably better to do it that way to avoid any confusion. Alright, so at this point now we've got a method, getLocation, that we can use anytime we move the player or the player moves to a different location. So what we now need to do is go to the main class's main method to get or to actually add the call to the getLocation method rather than getting location information from a map. So let's go back to the main method. We'll have a look at our main code here. So basically before the while true, what we need to do is we're going to start off by creating the first location. So it's going to be, we'll actually get rid of this commented out int location equals 1. So after the lock equals 64 on line 29, we're going to add location, current location is equal to locations dot get location, the method we just wrote, and we'll pass lock to that, which is going to be location 64, which is our start. And what we're going to do is up here, we're going to throw the exception as well. I mentioned we're going to do that for our exceptions. If you wanted to handle that, you could, but we're just going to keep that simple there. Throw the exceptions for main to remove that error. All right, so we've got our first location, and we're still going to leave this locations get description, but we just need to change it marginally, and it's going to be, instead of locations.getLock, we're going to change that to be current location.getDescription. And for the break, instead of checking for the variable lock, in actual fact, what I'll do here is I'm going to remove that. So we don't really need that anymore. And I'm going to change that to be 64, which is our starting room. And again, that's you might want to code that as a constant to call it starting room or something along those lines. And we're going to change this, instead of lock equals 0, we're going to put if current location dot get location ID is equal to 0, then break. So we'll know automatically if we've reached the room with the location ID 0, we know that we can actually break out of this altogether. And then this map here that on line 38 currently is using locations.getLock.getExits. Well, we can change that again to use the current location that we've created. So it's going to be current location.getExits. And then down here on line 57, you can see that we're updating the lock variable. Well, in actual fact, what we want to do here is change that. Instead of the lock variable being updated, we actually want to update our current location object. So we type current location and equals, and it's going to be locations.getLocation. And we're going to do current location.getExits, then .get direction. So you can see there we're updating our current location, we're moving to whatever direction was actually selected by the user and updating our current location. So consequently, when the while loop goes through again, we can print out the description of the new room, and we've got all these other tests here, testing to see whether we're at location 0 to break out, and also updating our exits by using the current locations.getExits method on line 38. And one last thing we need to do is right after we've actually exited the loop, so basically down here, what we want to do is locations.close. So we want to actually close that file when the player has actually exited the game. Alright, so at this point, with the various changes we've made, we should be able to run the application and play it exactly the same as we've done before. So let's just try running it to see that it'll actually work. So I'm running the main method from the main class. And we've got our printout there just showing the various locations, just as a test. And we've started off okay, so we're at a complex junction. Let's just try moving. And if we move down again, we've complex junction. If we just change this also, we'll quit out of that just to make sure that it is working, and we'll go back and we'll change the ID. We'll get location 64, with which you may recall from some videos ago we changed it so we got to a different part of the game. Change it to location 1, which is the starting location, and let's just run that to make sure we are starting in the right place. You're standing at the end of a road before a small brick building, so that's good. So we can go, say, west here. You walked up a hill, still in the forest. East, back to where we were before. South, north, up, down. We can't walk down it again. We need to move to another location due to the way the game's been programmed. East, and we're back to where we were before. Okay, then we can quit out of it. Alright, so you can see that we've now modified our entire application here, and we're no longer reading all the locations from memory. So we've now got the basic shell of a game that could potentially have thousands or perhaps even tens of thousands of different locations, and we haven't got any problems with the amount of memory we're consuming for that, because we're only loading in the locations one at a time directly from our random access file. So in other words, they're loaded on demand. So at this point, you now know how to use a random access file to load data on demand. Now we move the file pointer to the offset we want to read, and then we read it. And as you learnt, if we're reading and writing data sequentially, we don't have to explicitly move the file pointer ourselves, but in a random file access scenario, of course, we'll need to do that. So that's all the coverage I have for the java.io package. But starting in the next video, I'm going to take a look at the java.nio package. So we're going to talk about what java.nio is, and then we'll actually get stuck into how to use it. So see you in the next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
In Java 1.4, a new I/O package was added to the Java Software Development Kit. Now they called it java.nio, and the package was described back then as an improvement to Java I/O, and that's because the classes in the package perform I/O in a non-blocking manner. Now Java NIO was also meant to fix some of the inherent problems developers could run into when using the java.io classes to work with the file system. Now the java.nio classes fall into one of two buckets, those that deal with the file system and also those that deal with reading and writing data. In this video, we're going to start looking at the classes that read data from and write data to a data source. Now when using classes in the java.io package, a thread will block while it's waiting to read or write to a stream or buffer. However, threads using the java.nio class or classes will not block. In other words, they're free to continue executing, and consequently you could really say that java.nio was introduced as a performance improvement. With that said, many developers have argued that the java.nio package was a step backwards. And in fact, there's examples on the internet that people have shown that blocking I/O, which is in the java.io package, is often faster than the non-blocking I/O in the java.nio package. And the discussion on threads and blocking, etc., is covered in the threads section of the course, by the way, just in case you haven't seen that section of the course yet and are wondering what that's all about. Now, also working with the java.nio class is more complex, and you'll see that when we go through to start writing some code. Now, as has happened with other additions to the Java language, many developers still prefer to write code using the older java.io classes, and you may very well decide to do that as well, but I do feel it's important to understand the new way of doing I/O with the java.nio package, just in case you're ever asked to work with code that uses it. Now previously you learnt that the java.io classes work with streams, that is character and binary. Now data is read one byte or character at a time and sometimes buffered depending on which classes are used. Now when using java.nio, however, you'll deal with data in blocks, and rather than processing a single byte or character at a time, one block will be processed at a time. Now to accomplish this, you'll need to use channels and buffers, and you'll see what they are and how to use those in later videos in this section in the course. So with all that said about java.nio, you can use java.nio methods to create a java.io stream. But more on that later. For now though, make a copy of the adventure game project that we've been working on in this section of the course that we last used to read and write the data as an object stream. In other words, before we looked into random access. Now to save you a bit of time, I've put a zip file, a link to the zip file in the resources section of this video of the appropriate zip file for that video, just to save you a bit of time. Alright, so I've already unzipped that particular file and put it on my computer. So I'm going to switch back now to IntelliJ and we'll open it up and we'll get started with java.nio. Alright, so I've already got the package. I've actually unzipped it and I'm using the input, well, I've actually called the folder input output NIO, so I know that it's different and distinct to the other projects. So I'm going to open that. And we're going to start making some changes to this to support java.nio. Alright, so now that we've opened that other project, let's just quickly run it just to make sure that it still works. And of course it should work just fine, but it's good for us to check that. It's looking okay, so I'll exit out of that. Alright, so now that we've done that, let's start working with java.nio. Now, the first thing we're going to do is update the locations class so that it reads data from the directions_big.txt and locations_big.txt files. Now, these files are text files, as you recall, and we've done this many times now, but you'll first run the locations.main class to write out the data, and then we'll change the locations class static initializer, which loads the data when the first instance of the locations class is created. And then once that's done, we can call the main method from the main class to run the game. Alright, so let's go to our locations class. And the first thing we're going to do is delete the code from the locations.main method. So I'm just going to delete all that out. And I'll delete this comment out as well. And we'll get started. So we're going to start by typing path, noting that that's a java.nio, or it's from the java.nio package. And lock path, the location path, is equal to file systems. And we'll talk about this as we go through, but again, file systems is another java.nio package or class. File systems dot get default dot get path. So we're going to put in the name of the file, locations _big.txt. And we'll do the same for the directions. So dir path is equal to file systems dot get default dot get path. This time it's going to be directions _big.txt. Then we're going to try with resources, so it's going to be try. It's going to be a buffered writer lock file equals files dot new buffered writer dir path. And then the second one is going to be, actually that should be lock path, the first one. So we're opening or using both the files, so we need to have a buffered writer set up for both. So buffered writer, this one's going to be dir file is equal to files dot new buffered writer, and it's going to be dir path this time. Then we're going to go through and loop through all the locations. So for locations.values, then lock file dot write, and it's going to be location. Should be location there. The variable name, so it's going to be location dot get location ID. We're writing that out plus a comma plus the location description, so location dot get description. I'm going to add an underline character to the end of that, /n. And the error we're getting at the moment is a typo. That should have been one there, one right parentheses, not two. Let's fix that up. And then we're going to go through all the directions, all the exits. So for string direction, colon, this time it's going to be location dot get exits dot key set. Then we're going to do a test to make sure it's not the default location. So if not, direction dot equals ignore case q Then we're going to do a dir file dot write, and we're going to write the location ID, so location dot get location ID plus a comma plus the direction plus another comma plus, and we'll just go to a new line for this. And that's going to be location dot get exits dot get direction, and then we're going to do an end of line character. And that should be it. And then we just need our catch. We're just going to catch an IO exception. And if we happen to get an error, we're just going to print out the message IO exception e.getMessage. Alright, now what I'm going to do is just paste in the code that we used when we wrote the file using the java.io.bufferedReader, just so we can see the difference, even though we ultimately aren't going to use that. And I'm just going to include everything but the final catch. So this is what we did. Even though it's at a different indent level, we should still be able to get the gist of it here. So we're comparing the code starting on line 22 to load the code that's starting on line 35. So all that's really changed is the way that we create the buffered writer. Instead of creating one directly by calling the buffered writer constructor, which we've done here on line 35 and 36, we're using the java.nio.files class to create the instance. These files here, files.newBufferedReader lockpath on line 22, and the same for line 23. So the files.newBufferedWriter method accepts a java.nio.path instance, and we obviously declared those a path instance on lines 20 and 21. Lock path and dir path. Now we are going to look at the path and the file systems classes in more depth later when you learn how to work with the file system. For now, just understand that the path class is meant as a replacement for the file class. So it's a more robust class when it comes to working with files. Now classes in the java.nio package work with path instances and not file instances. It's recommended practice to work with the path class if using java.nio wherever possible. Now sometimes you will have to use the file class, and that's because a method or constructor wants a file instance as a parameter, but when you do have a choice, make sure you use path over file. So creating a buffered writer this way creates a writer that uses java.nio to do its output. Now remember that the buffered writer wraps another IO class. So when we use the files.newBufferedWriter here on line 22 and line 23, a buffered writer is returned that performs I/O using an instance of the java.nio class called byteChannel. And you'll learn more about channels later in this section of the course. Alright, so let's get rid of that extra code that I copied and pasted in. Clean this up a little bit. Alright, so what we can do now is we can actually run this class, or run this method rather, locations.main. And you can see that it seems to have processed something. And if we have a look at the files, it's still pretty much as, directions underscore big was one of them. And also locations underscore big. They were the two files. And they're pretty much like they were before. Now the situation is the same when reading from a stream. So what we'll do now is we're going to update the static initializer so that it uses the files.newBufferedReader method to create the buffered reader. So the actual method will want a path instance. So looking at our static initializer, I'm just going to delete all that code out. And we'll just start again. So we want our two paths. They're going to be pretty much the same as they were prior to us changing the code here. Or after, I should say. So we want those two paths again. Then we're going to do a try. Scanner is equal to new scanner. And it's going to be files.newBufferedReader. We're going to start with lock path. We're going to accept that import. And we're probably getting, we're getting a java.io.io exception, but we'll look at that shortly. So we're going to do scanner.useDelimiter, a comma. Let's fix this up a little bit. And actually what I was trying to do there was a try with resources, so I'll fix it up like that. Tab that over and put another right curly brace. Okay. And we've still got our IO exception there that we need to fix. Right, so we've got, or specified the scanner is going to use the delimiter of a comma. We're going to go through now, so do while scanner dot has next line int lock equals scanner dot next int scanner dot skip. We'll be talking about this shortly. That's going to be scanner dot delimiter. String description is equal to scanner dot next line. We're going to print it out. We'll type it out as imported location plus lock plus colon plus description, so we can see some output on the screen. Then we're going to do locations.put lock, then new location, and it's lock and description. That's the two parameters. And then we need to put a null there, and that's because our code at the moment, if we look at our constructor, we talked about this previously, it's got the code built in to test to see whether null's passed, and it's going to create a new linked hash map for our exits if it has. Otherwise, it'll just save the value of, or save the map if one was sent to this method. But in our case, that's not happening because we're not passing that. So we'll go back to our locations code, leaving that as null. And what we still need to do is, I'll just finish this off so we've got at least got it catching some errors. IO exception E. Then we're just going to e.print stack trace. So what I'll do is I'll finish the video here now. When we come back, we'll actually add the code using the files.newBufferedReader, and this time we're going to add it for the directions, i.e. the exits, and actually add those as well. So I'll see you in the next video. Alright, so continuing on from the last video, what we need to do is finish off and add the code to the static initializer block to process the exits, the directions. So we're going to do this below the first try with resources block. So we're going to do it down there, and we're going to start with try, and it's going to be buffered reader dir file equals, it's going to be files dot new buffered reader again, and dir path this time. Then we're going to do string input, and while input equals dir file dot readline, well, that's not equal to null. And I got that, the parentheses slightly wrong with that. It should be one parenthesis at the end of the line and an extra parenthesis to the right of the dir file.readline. Alright, so then we're going to do a string array. Data is equal to input.split, comma. Then we're going to do int lock is equal to integer dot parse int. That's going to be data 0. First element, so string then direction equals the second element, so it equals data 1. And int destination is equal to integer dot parse int, and the next element data 2. Let's just print those out then. So I'm going to print out lock plus colon plus the direction plus another colon space then plus the destination, just so we can see that it is being retrieved okay. And next we want to create a location, so location equals locations dot get lock, so we're using that as the key to get it, the lock, the first element that we retrieve for the location. Then we want to add some exits, so location dot add exit, and that's going to be direction destination. Okay, and then to get rid of that other error at the top, or both errors, we need to catch the IO exception. And we need another right curly bracket there, catch, and e.print stack trace. I'll just tidy that up. Okay, and of course that should have been new buffered reader, because we're reading, not writing. Okay. And I seem to be having a bad day with coding. I've got an extra one in there. So I'll just reformat the code again. And it should be good to go. Nothing needed to be changed. Okay. So even though we typed in a lot of code, really the only thing we changed here is the files.newBufferedReader method call in both try statements. Also, we had to declare the two path variables. Otherwise, the code's pretty much identical to what it was when you called the buffered reader constructor directly in the two try statements. Now, as mentioned before, when you use the files.newBufferedReader or writer methods to create the buffered reader and buffered writer, the underlying instance used to do the I/O is a java.nio instance rather than a java.io instance. Alright, so what about reading and writing objects? Well, firstly, there isn't a files.new object input stream or files.new object output stream method, but there are new input stream and new output stream methods which return an input stream and an output stream respectively. So in other words, you can construct an object input stream from an input stream and an object output stream from an output stream. So with that said, you should be able to create an object input stream or an output stream from a path using a two-step process. So you call the files method to get the appropriate stream, and then call the object input stream or object output stream constructed directly using the stream you got from the files method. Sounds like a mouthful, but let's actually try that to see how it works. Alright, so this time we're going to be writing and reading the locations.dat file. Now you no longer need two files because you're going to serialize the contents of every location object to the locations.dat file. So to do that, we need to go to our locations.main method to write the file. So I'm going to go back up there. So we're in locations and looking at this main code. So what we're going to do here is we're going to just comment this code out to show you how to do it using objects. So we're going to comment that out entirely. So we've got a copy of it. And I'll actually start coding it at the top. All right, so again, we're working now with the locations.dat. So I'm going to start by typing path. Lock path is equal to file systems dot get default dot get path. And this time, as I said, it's locations.dat. Then we just do a try, and we start with an object output stream. Lock file is equal to new object output stream. Then we do a new buffered output stream, and then we pass to that the files dot new output stream, and for location path. And then in terms of writing it out, it would be code as you've seen before. So for location, colon, locations.values, lock file dot write object, location. So two things to notice with this code. First of all, you're using the files.newOutputStream method, this one up here on line 21. We're using that to get an output stream using a path instance. This is passing lock path, and of course that's using the path, the java.nio path object, or path instance I should say. And secondly, what we're doing is exactly what we did when we created a file output stream using the file output stream constructor. So you're wrapping it up still in this buffered output stream, so the IO will be buffered. Then you're wrapping that in an object output stream. So really the only change you've made is the code, or to the code, is to call the files.newOutputStream rather than the file output stream constructor. So that's where the java.nio code comes in. Alright, so we've got an existing locations.dat file. If you wanted to, we could delete it, but we're just going to run it again and it should be recreated. So let's run that. Okay, the code is has been written, and the static initializer block also was executed, which was in case you're wondering where that output come from. Obviously, we didn't have any output here for locations.dat while we were creating that. All right, so now that we've done that, let's now modify the static initializer so that it uses the files.newInputStream. So let's go down and have a look at that. And the code is going to be a lot easier because we're reading objects instead of reading it and using delimiters and so forth to retrieve the data. So I'm going to copy that or comment that out, and let's have a look at it. The code to do that now, path, lock path is equal to file systems dot get default dot get path. This time it's locations.dat which we've just created in the main method for the locations class. And then we're going to do try, and it's going to be object input stream this time. And lock file is equal to new object input stream this time, new buffered input stream, and then files.new input stream lock path. Alright, then let's write the code now to get the objects. Boolean EOF equals false, and then we do a while, not in the file. We want to try there, and we're going to catch the end of file exception. And we'll put EOF equals true for that call exception. And the code in here is going to be location equals cast that as location, lock file dot read object. And then we want to do locations dot put location dot get location ID, comma location. And we've got another exception that we need to catch here. And another one here, because if you remember the code when we've done this previously, we had a number of exceptions. We do a catch. First one is invalid class exception. If we get that, we'll just print out a message. Valid class exception plus e.getMessage. We could have just printed out the stack trace if we wanted to. We also want to catch the IO exception. Right, and print out the message as well. And then the third one we do want to catch here is the class not found exception. Class not found exception. And that one's going to be class not found exception e.getMessage. So the code is very similar, almost identical to what we used previously to read objects from locations.dat. Except we're using the files.new input stream up here on line 51, using that method to create an input stream, and then we're wrapping that with a buffered input stream, and then we're finally wrapping that with an object input stream. Okay, so if we run that, we should find that our code still works. And obviously we're not getting any errors, which is a good thing. We're also not getting any output anymore because we didn't put any debugging code in our main code, but also not in our static initializer block either. So essentially you can use files.new input stream and files.new output stream to create any stream that descends from input stream and output stream respectively. Alright, so at this point you now know how to use java.nio classes to create commonly used java.io streams. In the next video we're going to start looking at how to read and write text files using java.nio exclusively. And if you recall a few videos ago I said that doing IO using java.nio means that data is processed in blocks rather than one byte or character at a time. So to accomplish this, java.nio uses channels and buffers and sometimes selectors. So let's start looking at channels, buffers and selectors and figuring out how to use java.nio to do all our I/O in the next video. Alright, so in the last video we finished working with java.nio and java.io. So in other words, we're getting the java.nio classes to create commonly used java.io streams. But it's now time to take a look at how to read and write text files using java.nio only. Now I said that doing I/O using java.nio means that data is processed in blocks rather than one byte or character at a time. And to accomplish this, java.nio uses channels and buffers and also sometimes selectors. So in terms of definitions, a channel is the data source you're reading from or writing to. Now that can be a file, a socket or any other data source. Now to use a data source as a channel, you need a class that implements the java.nio.channel interface and that can connect to the data source. Now a buffer, on the other hand, is the container for the block of data that you want to read or write. Now buffers are typed, and that means that they can only hold one type of data, and you can actually specify the size of the buffer as well. And finally selectors, well they allow a single thread to manage the I/O for multiple channels. Now we won't actually be covering selectors because they're really generally only needed in large enterprise applications. Now, when working with streams, which if you recall can be byte-based or character-based, and we saw that in previous videos, you need two instances of a java.io class if you want to both read and write a file. So you need one instance for reading and one instance for writing. As an example, if you wanted to read and write to a file in a non-random way, you need to use file reader and file writer. But when using java.nio, you only need one instance of a channel to both read and write the same data source. Also, reading and writing is always buffered, so you don't have to wrap an instance with a buffered instance as you do when working with java.io. So to be used as a channel, classes must implement the java.nio.channels.channel interface. Now the JDK contains channels for several data sources, including files, network I/O, as well as sockets. Now at this point in time, we've pretty well beaten the adventure game application to death, so we're going to create a new project to get familiar with how java.nio is typically done. So let's create that new project, and we'll call this one Java NIO. Java NIO. And I'll just put it in the right place on my computer. Okay, and what we'll do to start off with, we're going to create a file called data.txt just with a bit of data in there. So I'm just going to right click on the project name, click on new, select file. We'll call this one data.txt. And we're just going to put 3 lines of text. Line 1, line 2, line 3. Pretty basic. Alright, so now that we've got a file to work with, we're going to create the channel that's going to be used to read and write the file. Now there are 2 ways to do this. You can create a channel from an open file instance, or alternatively you can use the filechannel.open method. So let's start by creating a channel from an open file. We can get a file channel from the instances of 3 classes: file input stream, file output stream, and random access file. So we're actually going to be using a file input stream. So I'm going to open the source folder and open our main.java that was created with this project. And we'll add a try block. We're going to catch IO exceptions. And we'll just print the stack trace if there's an error. And the code is going to be file input stream, file equals new, file input stream, data.txt, the file we have just now created. And then we're going to do file channel equals file.getChannel. So you create the file input stream as we're doing on line 11, and then on line 12 we're calling the getChannel method to get a file channel. Now I said earlier that when using channels you only need one channel for both reading and writing. Now file channel is an exception to the rule. If you create a file channel from a file input stream, it's actually only open for reading. Now if you create a file from a file output stream, it's only open for writing. And for a random access file, it will depend on the parameter you pass to the random access file constructor. And if you remember that when we create a random access file instance, you can specify whether the file is open to read or write by using either R or RW as the parameter that you pass to the constructor. Alright, so your next step will be to create the buffer that's going to be used to read from the file. But hang on a minute, under the covers, file channel is an instance of seekable byte channel. And we're actually working with text. So you might think that it should be easy to read a string or text from a file using java.nio, but it's not, or at least it wasn't until fairly recently. Now when you create a buffer to use with a channel, you have to specify the size of the buffer, which will specify how many bytes are read from the file at any one time. Now what should the buffer size be for your file? Right now all the lines are the same length, so you could create a buffer that has a size equal to the length of each line in the file. But what about files that contain lines of varying or different lengths? For example, if the first line is 25 bytes long and the next line is 100 bytes long, what should the buffer size be? If it's 25, then on the second read, you'll only get 25 bytes of the second line. And if it's 100, then the first read will return all the first line and the first 75 bytes of the second line. So on each read, you'll have to parse the buffer for new lines. If you only found part of the line, you'd have to do another read to get more of the partial line, etc. It does sound complicated, and this is why you'd really want to do it that way when dealing with text files. But fortunately, new methods were introduced in the java.nio.files class in Java 8 that makes it easy to read one line of a text file at a time. Perhaps now you're getting some idea of why the development community hasn't embraced java.ni for file I/O. It has been around for years, but the performance improvements often aren't there, and some pretty common ways of doing I/O were in fact overlooked. In fact, the files class was only introduced in Java 7. It contains static methods that typically deal with file I/O. Hurrah, finally! Now since the file we're working with is small, we're going to change the code so that it reads the entire file in one shot. Now since we're going to be using a method introduced in Java 8, this won't work with early versions of the JDK. So it's JDK 8 specific. So we're just going to comment out those 2 lines there. You're not going to be using those. And the code is going to be path, data path is equal to file systems dot get default dot get path data.txt. Then we're going to do list strings. So a list of string array, we're creating a list of string objects, calling it lines, and that equals files dot read all lines, data path, that's reading the entire file contents. And then we're going to go through for each line. So for string, line, colon lines. And we're going to do a print out of lines. And that should be it. And we're getting this error here because my new project hasn't been set for using JDK 8. And you can see there that it's telling us that the usage of API documented as since 1.7 plus. So we need to go back into our project. Open module settings, click on project, and we want to make sure that we're specifying version 8, lambdas, type annotations, etc. And that fixes that error up. Alright, so let's actually try running this now. And actually what have I done? I've actually got an error here. I'm trying to print out the list each time instead of trying to print out the individual element. So let's delete that and print out line is what it should have been. Run it again. And we've now got our 3 lines of information coming out of our data.txt file. So very easy to do. So you can see that essentially that we've got the path to the file as we've done before. We then call the files.readAllLines method. You can see it here on line 16, and that returns a list of string objects. And each entry will correspond to one line in the file, as you can see when we ran the output, when we actually ran the contents. Now, if you want to access the file in a random fashion, then you get a file channel from an instance of random access file. And we'll see how to do that in an upcoming video. But if you're working with a text file that you want to read or write sequentially, using the methods in the files class is the way to go. Alright, so we've seen how to read data. Let's actually add some code to write some data. So we can actually do that by putting some code in the line after the path definition. And we're going to be using the files.write method. Now, a few things to note here. Firstly, when using the files class to write a text file, each write is considered an isolated write in the sense that you don't open a file, call a write method a bunch of times and then close the file. So each call to files.write involves opening the file, writing to it, and then closing the file. Because of that, if you wanted to write more than one line, you'd typically use something like String Builder to build the text up that you wanted to output and do it all in the one shot. Now, if the amount of output is large, you could do it in chunks perhaps, something like 10 or 50 or maybe 100 lines at a time. Now the files write method writes bytes, not strings, and so we're going to be calling the string.getBytes method to convert a string to bytes. So let's see how this works. So I'm going to type in files.write data path, the name of our path, that links to our points to our file. And in terms of the output, we're going to do a /n to go to a new line, line 4. Then we want to do dot get bytes, and I'm going to pass or specify UTF-8 parentheses, and then we want to put a comma, and that's going to be standard open option dot append. So that's actually it. That's the code to write some data to that file. So let's actually run that and see if it works. You can see we've got 1, 2, 3, then we've got a space, and then line 4. That's because if we're looking at our text file, I think I pressed enter after line 3, which created a new line. So we could actually delete that. Come back to here, and then we could comment out the right again because we don't want it to process again. Or in fact, what we could do is make it look right on line 5 this time. Run it again. We've now got our 5 lines of output appearing, and our file has now got 5 entries. Alright, so that's working well. And again, the only real thing there that could potentially be confusing is the fact that we've got a string here that we want to write, but we're using the .getBytes and passing the parameter of UTF-8 for the character set. So we're converting that string to bytes, in other words, and that's because files.write, that method actually needs bytes, and because it actually writes bytes and not doesn't process a string directly. So we're passing UTF-8 as the character set, but when you're actually using the read all lines, the UTF-8 is assumed. So if you want to write text that's in a different character set, you can specify the character set as a second parameter to the read all lines. So if we have a look at that, you can see here that by default it's returning read all lines path standard char sets.utf8, so that's an overloaded method. So we could do something very similar to that. We could pass that as standard char sets dot, and we could use something else like US ASCII for argument's sake. But again, we're not doing that, so UTF is assumed, and that's why we're only using that first method. And by the way, the other thing is here, you may not actually need the leading new line character in the string. If you included a new line character at the end of line 3, as you saw me do when you added the existing contents to the file, then you wouldn't need it. Alright, last thing to note before we finish the video is this third parameter though, this standard option open.append. Now that obviously means that if you want to write to a file that already exists and you want to append the bytes to the end of the file, that's the one that you're actually using. That would be the right one. Now if you don't specify a third parameter, the method assumes that you in fact want to start fresh. So if the file doesn't exist, it'll create it, but if it does exist, it'll truncate or wipe out the existing contents. You can explicitly ask for that behavior by passing standard open option.create as a third parameter, and also standard open option.truncate underscore existing as a fourth parameter. The write method only requires the first 2 parameters. Any others are optional and have to be of type open option. But again, as you can see in our case, clearly what we've done is working because we've now got 5 lines of output appearing in that file. The other thing to note here about this files.readAllLines method is that it reads the entire file into memory. Now, what would you do if you needed to read a huge text file and you didn't want to read the entire thing into memory? Well, honestly, to be completely honest, you'd use the java.io classes. You could use a byte buffer and go through the pain of parsing out each line. You could also call files.newBufferedReader to create a buffered reader that's using a byte channel under the covers. But as mentioned earlier, some developers have benchmarked java.io versus java.nio and found that java.nio is actually often much slower. Now, if you're working with a huge text file, another thing to consider would be using a different file format. Perhaps you should be using a database rather than a flat file. Now, the adventure game examples that we've worked with use small files, but since there's a relationship between the locations and the exits, it may well have made more sense to store the data in a database and retrieve it on demand, as you did when using the random access file class. There's really no rule or best practice that dictates using java.nio over java.io. If you're considering java.nio, really you should benchmark both ways and see which one wins for your application. The only case in which java.nio might be the recommended approach is when you're working on a large application that uses multiple threads to do I/O. Otherwise, my opinion is that java.io is absolutely fine to use. Now, as you'll see later though, java.nio is an improvement when it comes to dealing with the file system. Alright, so let's finish the video here. In the next one, we're going to turn our attention to binary files and how to work with those with java.nio. See you in the next video. Alright, so in the previous videos we talked about or looked at the files class to read and write text files. Let's now turn our attention to binary files. So we're going to start by writing to a binary file so that we've got something we can read. So we're going to start by writing the string hello world to a file in binary format. So I'm going to comment out this code. And at the top we're going to start by typing file output stream. bin file is equal to new file output stream. And we're going to call the file data.dat. Call it anything you literally like there. Then we need a file channel. So file channel, bin channel, is equal to bin file dot get channel. All right, so far so good. But the next thing we need is a buffer. Because we're writing to a file, you've got the data, and so you can create a byte buffer that matches the length of the data. In the read cases, you don't know the length of the data, so all you can really do is create a buffer of a given length and then parse what it receives. But note that you don't have to use the same buffer to do all your reads and writes. You can create as many different buffers as you like. So before we type some more code, let's get some terminology out of the way. Firstly, a buffer's capacity is the number of elements it can contain. Now, a buffer's position is the index of the next element that should be read or written. It can't be greater than the buffer's capacity. A buffer's mark is used by the buffer.reset method. When this method is called, the buffer's position is reset to its mark. Now, if you know you want to rewind the buffer to a certain point, you'll mark the point, and then later you'll call the reset method to reset the position to the mark. But you'll see more of how this works as we proceed. So with that out of the way, let's actually now write this hello world string to a file in binary format. So firstly, we need to create a byte array for the string that we want to output. So it's going to be byte array output bytes, we'll call it, is equal to, and we'll just type in hello world exclamation mark dot get bytes. So there's our byte array. And then we need a byte buffer. So we type byte buffer. You can see that's a java.nio import. Buffer is equal to, and it's byte buffer dot wrap. Noting we're using a static method there. Then output bytes. So we've created our buffer now. So when we first call this string.get bytes on line 14, or we do call that to create the byte array, then we're calling this byte buffer.wrap static method to create a byte buffer from the byte array. The actual wrap method itself does the following. Firstly, it wraps the byte array into the buffer. What that means is that the buffer is backed by the byte array. Now this is actually important. Modifications to the buffer will actually change the array, and modifications to the array will change the buffer. Now if you use the buffer to write out our string or our bytes, and then you use it to read from a file, the output byte array will be changed. In other words, it will no longer contain hello world. So essentially, when you call the wrap method, you're telling the runtime that you want to use the byte array as the buffer. And since you've used wrap, the buffer is already filled. May not be what you're expecting to happen there. Secondly, it sets the position of the buffer to 0. And when you use the buffer, the read-write will start at position 0. Thirdly, the buffer's capacity will be set to the byte array's length, which you would expect. And fourthly, the buffer's mark will be undefined, and that can be set later. So now that we've got our buffer and it contains the bytes, which was the string object that we wanted to write, we can use the channel to write it to a file. And the way we do that, bin channel.write buffer. And if you want to know how many bytes are actually written, you can get that from the write method's return value. So we could change that to be int num bytes equals byte channel.write buffer, and then we could print that out. Num bytes written was plus num bytes. Finally then, you'd have to close the input stream and the file channel. Because of that, you can use try with resources instead of creating the instances with the try block. So it's probably better to do it that way. So let's actually change that to be a try with resources. So it's going to be try file output stream bin file equals new file output stream. I guess we could have just copied the definitions there. Actually, let's do that. Be much easier to do that. So I'm going to put those both in here like that, and I'm going to put another parentheses there and then open a code block, and that should fix that. So now that we've done that, we'll find that both the channel and the output stream will be closed once we've finished execution, because we're using try with resources. I think that's preferable to creating them within the try block. So let's actually try no pun intended, to run this application. You can see we've got 12 bytes written, which will be consistent with hello world, which is exactly 12 bytes. And we can see over here our data.dat file was actually written, and we can actually see the text is actually appearing in that file. Now, by the way, it looks like a text file because we've used the default UTF-8 character set. And as I mentioned, you can see the 12 bytes were actually written in the console window down the bottom. Right, so let's go back to our code and actually change it or add to it to actually write an integer. Now we could reuse the buffer, but instead what we're going to do is create an int buffer that you'll use whenever you want to write an integer. So we'd actually do that instead. We'd go byte buffer int buffer is equal to byte buffer dot allocate integer dot bytes. So we're calling the byte buffer dot allocate method, and we're passing to it the size that we want the buffer to be, which in this case is because we mentioned we want to write an integer. This is the number of bytes in an integer. So now that we've got the buffer, we can write an int to the buffer. So let's write an integer number, pick a number, say 245. So we'll go int buffer dot putInt 245. Let's write it to our bin channel. So num bytes is equal to bin channel dot write. It's going to be int buffer this time. And then we'll print that out again. And let's just copy that line up there. Alright, so let's actually run it and see what happens. And look at our file. Well, that's a bit weird, as you can see. The integer's not appearing there in the data file. And then down here under the second write, num bytes written was actually 0. So what actually happened? Why isn't the integer in the file? And why are we getting 0 as the output when trying to write out the integer? Well, here's the deal in a nutshell. When you created the buffer, the position of the buffer was set to 0. Now when you called the putInt method on line 21 here, we wrote the int into the buffer, which changed the buffer's position. Now when the bin channel.write method, which we're using on the next line, line 22, goes to read the buffer's contents, it'll start the read at the buffer's position. So you have to explicitly reset the position to 0 if you want the bin channel.write method to start reading the buffer from the beginning. So to do this, we're going to call the byte buffer.flip method, and the flip method resets the position to 0 and discards any mark that had been set previously. Now, it would be obviously fantastic if the IO methods did this for us, so that developers didn't have to explicitly reset a buffer's position to 0. But alas, that's not the case. That was a design decision, because you may want to do multiple writes or reads to a buffer before writing to the channel, in which case you wouldn't want to reset the position to 0 after every write. Now, we don't have to use flip when we use the wrap method, and that's because it resets the position to 0. The wrap method up here on line 16, in case you're wondering. So by using the wrap method, it's automatically resetting the position to 0. And I listed 3 things the wrap method does, and the second item on that list is that it sets the position to 0. So that's one method that does take care of this for us. It's a convenience method to use when writing byte arrays. But when writing numerics, and that's an int, a long or a short, using the putInt, putlong and putShort methods, etc., you do have to take care of resetting the buffer yourself. And as mentioned, you may not want to do so after every read or write, and that's why they've actually got that in there. So if you had 20 integers to write, for argument's sake, you could create a buffer large enough to accept 20 integers and then call the putInt method 20 times. Each write would start at the buffer's position in that case. For the first putInt method, the buffer's position would be 0. For the second call, it would be 4. The third, it would be 8, given that 4 is the number of bytes for an integer. Now also note that you can write to an explicit index in the buffer. To do so, you pass a second parameter to the put method that specifies the start index for the read or write. But let's flip the buffer before using it to write to the channel. So we need to put that code before the write and after the put. So down here, we're going to put int buffer.flip to reset the position to 0. And if we run now, we should find that the integer is written to the file, and we get 4 back as the number of bytes written. Open data.date. we've now got this message, which is consistent with the fact that we're now writing binary data, and we've got the integer showing there. You can see there's 4 bytes being added there. That's the representation of our integer. But importantly down here, number of bytes written was 4. So that actually worked. All right, so let's actually write another integer this time, and we'll use a negative number. And let's actually pretend, I'm going to actually just copy these 3 lines. I should copy these 4 lines, but I'm going to get rid of the flip. And the number I'm going to write, I'll use a negative number, negative 98765. So we're pretending that we don't understand that we have to call the flip method again to reset the buffer, both before you write negative 98765 to the buffer, and then before you write the buffer to a file. So if we do that now in this scenario and run it, we actually get an exception. You can see here we've got java.nio.buffer overflow exception. And the actual error, you can see, is on line 26. And line 26 is this put int negative 98765. And the reason for that is, well, after we wrote the last integer, 245, to the file, the buffer's position was set to 4. But the buffer is only 4 bytes long. And that's because when we use the buffer, we set it up using the buffers.allocate method to integer.bytes, which is the length of 4 on a computer. And that's usual with Java, the position 0 based. So 4 is actually outside or out of bounds of the buffer's capacity. There's no room at position 4 to write any more bytes, and hence we're getting an exception for that reason. So calling flip will obviously solve the problem. So we need to do 2 flips here. We need to do a flip, and I'll just copy the code. A flip before our call to the put int, and then also we need to do a flip after the put int prior to the call to the write method. We'll just run this to confirm that it works. This time you can see that it was written. We've got 2 calls, 2 bytes, lots of bytes written, or integers written I should say. And you can see, although we can't understand it, we can see that the extra bytes actually were written to the file. So the point here, always remember to call the flip method whenever you want to reset a buffer's position to 0. It's a common error to forget to do it and then wonder why the data isn't being written to the data source. Now, if you're going to do multiple writes to a buffer before writing the buffer to a channel, you don't have to call flip after each write, but you do have to call it whenever you flip from reading to writing or writing to reading, and hence the name flip. When you've filled a buffer and you're ready to write it to a channel or to the channel, you'll actually be reading from the buffer at that point. Now read from the buffer and write to the channel, and hence a call to flip is required. Alright, so that's it. I'm going to finish the video here now. In the next one, we're going to start taking a look at reading files using channels and buffers and other things along those lines. So I'll see you in the next video. In the last video, we used java.nio to write data to a data.dat file. Now we're going to read that data back into the application. Now we're going to use java.nio, but we'll start off using java.io to accomplish this reading of the data back into the application. Now a file is just a file. It doesn't matter how it was written, so we can use java.io to write a file and java.nio to read it, and vice versa. That really doesn't matter. So let's look at the code that we used to write the data to the file. First, we started off by using the write method to write a series of bytes out for our hello world byte array. And if you recall, when you use methods such as write UTF, the length of the string is written before the string itself, so that when the read UTF method's called, the method knows how many bytes to read. Now, you didn't write the string length because this is just a simple demo app. After the string, we followed on by writing the integer 245, which we defined on line 21, then wrote on line 23, and then finally we wrote the integer we defined on line 27, negative 98765, and then wrote it with the code on line 29. So now that we've done that, let's actually use the java.io.randomaccessFile class to read in this data. Now we're going to use the same project, as you can see that I've got opened here as last time, and we're just going to add more code into the main method, and we're going to add it into the try with resources block. So I'm going to clear out some of this code all of this code that was commented out from a previous video. All right, so we're going to start here with defining our random access file. So random access file array is equal to new random access file, file name being data.dat. Then the mode, we're going to do RWD as we've discussed previously. Next, we're going to define a new byte array that's going to contain the data we're reading. So byte array B equals new byte, and we're going to define the number of bytes based on the byte array length that we defined on line 16. So we can just use new byte and in square brackets output bytes dot length. So we're getting the right length for the hello world text there with our byte array. Then we're going to use the array.read method and pass the parameter of B so that what we read is going into the byte array. Then let's just do a proof of concept by printing out a new string B, which converts the byte array to a string, and we should be able to see that on our console. So if we try that first, we should get our printout showing us that we've read it okay. And you can see we've got hello world showing there on the screen after the number of bytes that were written, so clearly that's worked okay. So far so good. So next, what we need to do is we need to read in the two integers. To do that, we're going to do a long int1 equals array.readInt, then long int2 equals array.readInt, and let's print them both out. So int1, int2. Let's try that, make sure it works. Alright, so you can see we got the numeric results 245 and negative 98765. So really nothing remarkable here. We've used the random access file.readInt methods on line 38 and 39 to retrieve our integers. Now it's okay to write the data every time you run the main method. Okay, so you've demonstrated that the data you wrote is indeed what ended up in the file. We demonstrated that by being able to retrieve it and seeing the results on screen. And that also confirms the package you use to write a file doesn't matter. In other words, there's no association formed between the file and the package. You can use a different I/O package to read the file, or a different application written in something other than Java for that matter, and that will work just fine when we come back to reading it. Alright, so again, as I mentioned, we're using the random.accessFile class, which is part of the I/O package. What we're going to do now is read the file using java.nio. So for now, let's comment out that code that we just used to retrieve it via the random access file class. Leave it commented there so you've got access to that code. And let's do the equivalent thing, this time using java.nio. So we actually start with a random access file again, but I've left that code commented out so it's we've got an entire block of code there that's accurate. So random access file, RA equals new random access file. We'll need that starting code again, and then set the mode to RWD again. But then now let's actually define a channel. So file channel, and file channels of NIO, so you can see, are from the NIO package. Channel equals RA.getChannel. Then we're going to use the existing buffers to read the data back into the application. Firstly, the string, I'm going to create a new variable here, long numbytes read equals channel dot read buffer, and we can see we're writing it back into our byte buffer here that we defined on line 17. So after making this call, the string will be in the variable buffer, which we used to write out the string earlier in the main method, as I just pointed out. Again, that's on line 17, but at least the definition for the buffer is on line 17. We actually wrote it out on line 18. Now to print the string, we need to access the byte array backing the buffer. Now in this case, there's actually two ways to get at it. Firstly, if you recall that when we called the wrap method, the byte array we passed as a parameter is used to back the buffer. So after the read, the string should be in the output bytes byte array. And this is the byte array we defined on line 16. And I'm talking about this wrap function here on line 17 that was called. So let's see if that's true, and that does happen. But first, are we forgetting something? What do we have to do before switching from writing to reading? Well, you should call the flip method. But let's actually see what happens if we don't call it. We're going to add this statement now to print the output buffer variable. So I'm going to do that after the call to channel.read on line 35. So we'll do an output, and we'll say output bytes equals plus new string output bytes. So if we try to run this now, let's see what happens. Alright, so we see the expected string, hello world, showing in the console, but this is actually deceiving. And that's because the output bytes byte array already contained hello world from when we wrote the file originally, and because we didn't call flip, the read method that we called here on line 35 didn't actually do anything. And that's because the buffer's position was actually at the end of the buffer. So to demonstrate this, we're going to change the contents of the output bytes array before we do the read. So let's just go ahead and just put a couple of changes there. So we'll put output bytes, then 0 in square brackets equals A, then output bytes 1 equals B. And actually that should have been before our call to read. So I'm just going to cut it out of there and put it before. So it's after the ra.read channel, but before the channel.read. So I'm going to put it in there. All right, now we're going to run this again. And you can see we've now got ABLLO world now showing, which is representative of the fact that we changed the output bytes variable on line 35 and lines 36, at least the first two elements of the byte array. So what should have happened is when we read this buffer, we've actually saved this as hello world, and that's what's been saved to the file. So we've actually changed the buffer in memory to AB as the first two characters there, as the first two chars, as you can see there. So the read to the read buffer should have actually replaced that with hello world again. So clearly that confirms that the read method isn't being called correctly, or rather it is being called but not actually returning what we think it should be returning. So now to demonstrate this further, let's add a call to flip. And we'll do that after those two definitions on line 35 and 36. So we'll do buffer.flip. And we'll run that again. And this time you can see we've now got the expected results. We're seeing hello world printed to the console, even though we changed the byte array on line 35 and 36. But then of course we should have got hello world showing because we wrote that out originally on line 18. And now that we've done this, introduced the call to flip, the read method is successfully able to read that byte array back in, and we're getting hello world printed. The bottom line, always remember to call the flip method. Now it is unfortunately so easy to skip this step, and this is one reason why many developers aren't really all that keen on using java.nio to do I/O for their files. Now there is another way to get the string from the buffer. We can call the byteBuffer.array method, which returns the byte array backing the buffer. Now to do that, it's actually good practice to call the byteBuffer.hasArray method before doing that to ensure that you can access the byte buffer backing the array. So let's add the code to get the byte array using this second way of doing it. So after the read, what we're going to do is I'll just comment that line out for now, and we'll put if buffer.hasArray. Then we're going to do print out of, we'll put the output to be byte buffer is equal to plus new string. Then we'll do buffer.array. We'll just demonstrate and see that that still works. We've still got hello world printing out, so that's working okay. Okay, so what I will do is now read the two integers using the existing int buffer instance. So to do that, we're going to type int buffer.flip. Then we're going to do num bytes read is equal to channel.read int buffer. Then int buffer.flip again. And we're going to do a printout int buffer.getInt. Then we need to do int buffer.flip again. Then num bytes read is equal to channel.read int buffer.flip. Then we need to print out int buffer.getInt. And the other thing we should really be doing is closing the channel and file after reading the data, and that's because we didn't use the try with resources statement to open them. So I'm going to do channel.close and also the random access file object.close as well. And we'll just run this to make sure that it does work. We get our two integers, the number 245 and negative 98765. But we had to flip between each axis of the buffer. And just to confirm, the read call actually writes the buffer, and then the getInt method reads the buffer, if that makes sense. Now, to avoid calling flip, you can use another version of the getInt method. When you don't pass any parameters, as we're doing here, with our call to getInt on line 45 and also on lines 49, or line 49. If you do that without any parameters, then the read begins at the buffer's current position. But instead you can pass an index to getInt, and when you do that, the read will begin at the index you passed. So the first type of read is based on the buffer's position, is called a relative read. The second type of read is called an absolute read. So we're doing obviously a relative read here because we're not passing any parameters. But let's now change the code so that we can pass 0 to the getInt calls and get rid of one of the flip calls for each method. So what I'm going to do there, just to make it clear, I'm going to comment this code out so you've got a copy of that. And we might actually put a comment in there to that effect. Actually, I'll include this first line as well. It over a little bit, and we'll say this is the relative read, and now we're going to put absolute read. So it's a little bit different, the code, and I'll close this one window down so we can see the code for both. So we start off still doing an initial flip, so int buffer.flip, but then we can do numBytes read equals channel.read in buffer. So far that's the same, but when we go to print it out now, we can do int buffer dot getInt, but pass the number 0 as I mentioned. This is basically going to begin the read at the index position we specified, 0 in this case, and then we need to do one flip, int buffer dot flip, and basically we can do the same thing again there. I'll just copy that code. So you can see with it, we've only called flip twice here in total, but in this case here for the relative read, we actually called it a total of 4 times. But importantly, let's just check that it actually works. Still got the same results as you can see. And just to be clear, I'm not actually using the numBytes read variable here. We could print that out if you wanted to know how many bytes were read. I'm just sort of showing you the code for that. So basically by using an absolute read, which we've defined from line 43 down to line 49, we don't have to flip the buffer after reading from the file channel because we use the absolute version of the getInt methods on line 46 and 49 where we pass the index number of 0. Now you can do relative and absolute gets for all the data types, and you can do the same when doing puts to the buffer. So in other words, you can flip the buffer or you can provide an index. You have to do one or the other. Now, depending on what you're trying to do, you may not have a choice, but when you do, good idea as always is to be consistent. All right, so let's finish the video here. In the next video, I want to go through and just talk about the buffer position and how it's not updated when you're using absolute indices. But more on that in the next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a Starfreelancer.
Alright, now one thing to keep in mind, as I mentioned at the end of the last video, is that when you're using absolute indices, the buffer position isn't updated. So for example, when you used this code here on line 46 and 49, when we used int buffer.getInt0, that is to read an integer, after the method call, the buffer position remained wherever it was before the call. So to demonstrate this, we're going to change the code to flip the buffer, then do an absolute read, and then do a relative read. So let's make a change to that code slightly. So we've got our flip, which is going to remain the same. And we're going to read our int buffer, and then we're going to go to the next line and print out int buffer.getInt0 as per normal. Do another flip, and then we're going to go straight into another read, and here we're going to do another flip. So int buffer dot flip, and we're going to print out using the get indices 0 there, but then also after that we're going to do a print out, and I might just reformat this document. Int buffer dot get int, like so. Right, so if we just run this, so you can see the results down the bottom. So we're now reading the second integer from the buffer twice. So after the second channel.read call, we've flipped the buffer, and that sets the position back to 0, and then we're doing an absolute read and then a relative read. So in other words, we're doing the flip here, we're doing the absolute read here on line 50, and then on line 51 we're doing the relative read. And you can see down the bottom in terms of results, we get the negative integer 98765 printed twice. And if the absolute read had changed the buffer's position, then we would have got a java.nio.buffer underflow error, as you've seen before, because the buffer's position would have been pointing to the end of the buffer after the absolute read. But an absolute read doesn't change the buffer's position, and that's why the relative read on line 51 actually succeeds. So hopefully by now you can see that mixing relative and absolute reads could very quickly become error prone. So as I said earlier, actually in the last video, be consistent in your approach. I suggest you do it one way or the other. Mixing them up would make your code a nightmare to maintain, or at least potentially make it a nightmare. Alright, and in terms of the examples we're using here, at the moment we've reused existing buffers. Now of course we could also have allocated new buffers using the byteBuffer.allocate method. And if we come up here and have a look, we can see that we were using that when we were retrieving our integer bytes. We used byteBuffer.allocate on line 21. But let's actually do that for reading the string. At the moment you can see here on line 17 we're using byteBuffer.wrap for the string. So let's change that to use the allocate method instead. So what we're going to do is change the call on line 17 to byteBuffer.wrap to byteBuffer.allocate, and this time it's looking for the length, or the capacity I should say, of the buffer. So we need to pass in the length of the byte array, so we'll use .length after output bytes. Then the other thing we want to do after that is use a buffer.put, so buffer.put and our output bytes array, like so. So again, here instead of using the wrap method and passing a byte array, we've changed this line 17 to allocate a buffer, and then after we've allocated the buffer based on the length on line 18, we're using the put method to copy the contents of the output byte array into the buffer. So it's important to remember that when we use the wrap method, the byte array passed to the method is used as the byte array that backs the buffer. But that's clearly not happening here. Instead, when we use byteBuffer.allocate, as you can see on line 17, a new byte array is created, and that's used to back the buffer. Now earlier when we used the buffer created by wrap to read the string, the output bytes byte array was updated because it backed the buffer. That won't be the case anymore, as you'll see in a minute. So let's actually run the code based on what we've changed to see what happens. And you can see here what's happened. Firstly, the byte buffer now looks like it's got some random characters there, but also we've got an exception. java.lang.indexOutOfBounds exception. And if we click on the line number down here, or the where it's crashed, we can see it's crashed right down here, and it's an index out of bounds exception. So based on the code that we've added, obviously that has caused it to crash because it was working prior to us using the allocate and the put. So this is a mini challenge for you to try and figure out what's gone wrong. Now you should be able to figure out what has happened and fix that code so you don't get an exception. So I'm just going to pause the video now, have a go at seeing whether you can fix that problem and stop the exception, the index out of bounds exception, and I'll see you when you get back. Alright, so how did you go? Hopefully you worked it out. I want to give you a mantra with fixing errors with java.nio. So learn this mantra, learn it and keep it and just don't forget it. The mantra is, when something goes wrong, flip. So the above code isn't flipping the buffer. This is the code here on lines, well actually the code that's after line 18. It's not actually flipping the buffer between a read and write. When we called the put method on line 18, we wrote it to the buffer, and when we call binChannel.write, line 20, you're reading from the buffer, but you have to flip between those two actions. That's actually the issue here. So if we come back here after the buffer.put and we add a, well actually we'll put it down here just to clear it. Doesn't really matter, buffer.flip. But if you put the call there, run the code again, and this time we get the correct results. Alright, so now it's time to read the string back in. Now the way we're doing it now is fine because we're calling the byte buffer.array method to get the byte array backing the buffer. And if we come down and have a look at that, this is the code here, byte buffer equals, on line 43, byte buffer.array again is the method we're calling to get the byte array backing the buffer. Now when you were using the wrap method to write the string, we didn't have to call the array method because the output bytes array was backing the buffer, but now that we're not using the wrap method, that's no longer the case. So just to demonstrate that, we're going to temporarily change the code to print out the output bytes array instead of the one we get from this array method call here on line 43. So let's comment that out temporarily and instead replace that with output, and it's going to put to byte buffer equals plus, and then we'll actually add new string and it'll be our output bytes array. So if we try running that, notice the output ABLO world. So the problem here is that since the output string array isn't backing the buffer anymore, the first two characters you set aren't overwritten when you use the buffer to read the string from the file. So when we're using that code on line 41. So far you've been reading and writing variables individually. You write a single value to the buffer and then you write the buffer to the channel. And often you'll want to write a bunch of data to the buffer before writing the buffer to the channel, or read a bunch of data into the buffer before pulling data from it. So let's actually update the code so that it reads and writes all three values, that is the string and two integers, in the one shot. Now we're going to start with writing the data since you're currently doing that. We are doing that in the first main method at the top. In addition to the data that we're already writing, we're going to write another string and integer. Now you can delete or comment out the existing code in the main method. Let's actually do that, and we'll basically sort of start from scratch and go through it all. And just before I do that, though, I'll uncomment that and comment out that other one in case you need to refer to this code later. So what I'm going to do is just keep literally that first line, the output bytes hello world, and I'm going to comment everything else out. Absolutely everything out, as you can see there, all commented out. So we've got nothing in there other than the try and catch and this first line here. So we've got our byte array, output bytes, is going to contain a string to output. But before that, we're going to create a buffer. So we're going to do byte buffer. We'll call it buffer is equal to byte buffer dot allocate. We'll allocate 100. Then we've got, as I mentioned, our byte array output bytes. Let's go ahead now and output some stuff. So buffer dot put output bytes. Then we can do buffer dot put int 245, and we can do buffer dot put int again negative 98765. Then what we'll do is we'll write that extra string as I mentioned, so another byte array. We'll call this one output bytes 2 equals nice to meet you in double quotes dot get bytes. So there's our byte array, and let's put that out, print that out, or write that out I should say. Buffer dot put output bytes 2, and let's put another number on the end there. So buffer dot put int 1000, buffer dot flip, then bin channel dot write buffer. Okay, a few things to note here. Firstly, we've allocated more buffer than we need, but that's fine. So we've allocated 100 here on line 15. The buffer knows how many bytes have been written to it. And second, we only have to call the flip method, which I've defined on line 23 once, after we've written all the values to the buffer. So you do so at that point because you're flipping from writing to the buffer to reading from the buffer to write its contents to the file channel. Now third, you haven't specified an index for any of the put calls, and so all the writes are relative writes for that reason, which is what we actually want here when we're writing the values sequentially. And you can see that consequently the code's a bit cleaner than the previous versions we've worked through when you're using multiple buffers. Alright, so let's end the video here, and in the next one we're going to have a look and see what happens if we remove that flip call, but then continue on and start reading the data back from the file as well. So I'll see you as always in the next video. Alright, so in the last video we talked about, we consolidated the code now to make it a bit more efficient by actually putting a bunch of data, putting that in the buffer before we actually wrote it out. So let's actually just run this to make sure that it does work. And we'll look at our data.dat file. We can see there that obviously we can't read the numeric values, but we can see that the hello world and nice to meet you are actually showing there. I'll just close down this data.txt. So far so good there. And I think you'll agree that the code's a little bit cleaner than the previous version was when we used multiple buffers. So for fun now, and perhaps a mini challenge, we're going to remove the flip call here and see what happens. So I'm going to take that out, and can you guess what's going to happen when I remove the flip? Alright, so let's try running it to see what happens with the removal of the flip method call. And look at our data.dat file again. And you can see it's dramatically different. So effectively there's nothing in there. There's these strange characters showing up on the screen, but obviously the output that we saw prior to having the flip method removed has changed dramatically what the output will be. And the point is, if you don't use the flip method, the buffer's position will be set to after the last value you wrote to it when you call binChannel.write. So I'm going to close that down again. Now since there's nothing to write beyond that position, nothing's actually written to the file. So calling the flip method resets the buffer's position to 0, which is why we actually need that. So obviously we've got to uncomment that again, run it, and we get our result back. Alright, so I'm just going to remove this code that we commented out in previous videos. Make things a little bit tidier. Alright. Alright, so now that we've written things out in a single buffer, let's use a single buffer to read the contents of the file in one shot. So I'm going to come down here after the bin write buffer, and we'll do a random access file, RA equals new, random access file, data.dat being the file name, and RWD being the mode. Then file channel equals RA.getChannel. Then we're going to do a byte buffer, read buffer is equal to byte buffer.allocate 100, and channel.read read buffer. Then read buffer.flip, and then we're going to do byte array. We'll call this one input string is equal to new byte. And we're going to pass the output bytes that we actually used previously, dot length. So we're getting the right size byte array. Then we're going to do read buffer dot get, and that's going to be input string. And let's do some output here. So we're going to put input string equals plus new string input string. Then we'll do another one. We're going to put int1 equals plus read buffer dot get int. Another printout for int2 equals plus read buffer dot get int. Then we want byte array input string 2 is equal to new byte, and it's going to be output bytes2 dot length. Then we want to do a read buffer dot get, this time input string 2, and then we'll print out input string 2 equals plus a new string for input string 2, and let's print out int3. So int3 is equal to plus read buffer dot get int. Now we could reuse the buffer that we used to write the data here, by the way, but then the buffer's contents would already be set to the contents of the file, so you're starting fresh. That way you can be sure that the file is actually read. That's why we're doing it this way with a new buffer, using read buffer. So we're declaring a buffer of the same size as before, using the allocate method call on line 31, and then we're actually doing a channel.read for the read buffer. Now the read method is smart enough to stop reading, by the way, when it hits the end of the file. And next we're calling flip on line 33, because we're going to now switch from writing to the buffer to reading from the buffer. So at this point it's just a matter of calling the appropriate get methods as we go through. So we're using get here to get the first string, then we're getting the two ints and printing those out at the same time, then moving down to get the second string or the second set of bytes, and then find the final int as well. Alright, so let's actually check to see whether that's worked or will work. So you can see here we've got hello world, nice to meet you, showing 245 negative 98765, and int 3 is 1000. And that's obviously corresponding exactly with what we've actually output here when we've written the buffer to our file, to our data.dat file. So clearly that's actually working, which is nice. Now one last thing, the put methods all return the byte buffer, and that's great because that means we can chain multiple puts together. And I'm going to show you an example of that. So I'm going to come up to where we're writing. So I'll just take a copy of this first. We just need the various variables there because we're going to use those shortly. So I'm taking a copy of that, and then I'm going to comment that entire block of code out other than the buffer up here on line 16. And do comment it out because we're going to need that code again in a minute to use the unchained version. But I'm going to show you a chained version of these method calls. So I'm just going to change the position here and put the string at the top. And we can now do this. We can do buffer.put output bytes, then dot put int 245 dot put int negative 98765 dot put output bytes 2, then dot put int 1000. And then we can just do a buffer.flip, and then as we did before, the bin channel call, but that's actually going to be still called down on line 37, and I'll delete that other code. So you can see we're chaining method calls here, and the reason again we can do that is that with these put methods, they actually return the byte buffer, and as consequently we can chain those put methods together, as you've seen me do now on line 20. So if we actually run this now, we get exactly the same results as we did before, and obviously the reading has returned the right information there, but we can confirm that also by checking out the data.dat file. You can see it's still got the data in there. So you can see it's exactly the same as before, the results, and the code's a little bit more compact for that reason, less lines, and you might well come across code in your travels that's written that way as well. Now we've been using a random access file to read the file, but only because it was convenient to get a channel from it. Now since you're always reading and writing data sequentially, you could also have used an input stream. Now other than creating the stream, the code will then be the same. But moving on, now let's learn how to use random access using java.nio. So to jump around in a file, you have to use a seekable byte channel, which has the notion of a current position. Now, a seekable byte channel only has a small number of methods, and it's actually been available since Java 7. Before then, random access file was the only game in town when it came to non-sequential I/O. And seekable byte channel is actually an interface, and there's quite a few methods there. And there's actually 6 methods that I want to bring to your attention. And what I'm going to do, I've actually got them written out. So let's just put them on screen so you can see. So I'm just going to paste that in there, and then I'm just going to comment it out, so you can sort of see what they're all about. So there's 6 methods from the seekable byte channel interface. We've got a read byte buffer, reads bytes beginning at the channel's current position, and after a read, so I'll just put that to the next line so we can read it a bit better. Okay, we'll start again. So read, the first read method from the seekable byte channel accepts an argument of byte buffer, and it reads bytes beginning at the channel's current position, and after the read, updates the position accordingly. And note that now we're talking about the channel's position, not the byte buffer's position, so that's important there. And of course the bytes will be placed into the buffer starting at its current position. So that's the read method. The interface also defines a write method. It also accepts a byte buffer as an argument, and ultimately it's the same as read except that it writes, but one exception to note, and that's if the data source is opened in append mode, then the first write will take place starting at the end of the data source rather than at position 0, which you would expect for an append operation. And after the write, the position will be updated accordingly in both cases. We've got position. Now that method is meant to return the channel's position. And there's a second method that's overloaded for position, which accepts a long argument, and that sets the channel's position to the passed value. We've got a truncate method that has an argument of type long, truncates the size of the attached data source to the passed value, and finally a size method returns the size of the attached data source. So that's actually all the methods in the seekable byte channel interface. Now here's the good news about that. You've been using one all along because the file channel class implements the seekable byte channel interface. So let's modify the code we have so that it reads the integers in backwards order. So to do so, when we write the data, we're going to save the start position for each value. Now, as you saw previously when we were working with random access file, normally you'd have to have something like an index in the file that would enable you to read values on demand. But you've already learned how to do that, and so we're going to keep things simple here. We're going to go back to using the unchained version of the write code because you'll need to store the file position after every write. Now, in this simple case, you know what the data is and the order in which it's written. Now you could calculate the positions before you do each read, but in this case, just to save a bit of time, we're going to pretend that we can't do that. So let's have a look at doing that. So I'm going to comment out now the chain versions of our code, and I'm going to uncomment down here the longer version that we originally had that we commented out earlier in the video. And now we need to add those extra pieces of information in terms of the length. So we're going to start by coming down here after the output bytes. So outputting output bytes, okay, that's fine. But then we need to do a long int 1pos is equal to output bytes dot length. We're going to put the int on line 39, leave that as it is, but then after that what we're going to do is create a second variable. So long int 2pos now equals int 1pos plus integer dot bytes. We're then outputting our second int, which is negative 98765. Coming on down, we're defining our output bytes 2. Then we'll go ahead and output that. Below that, we're going to calculate int pos 3. So long int 3pos equals int 2pos plus integer dot bytes plus output bytes 2 dot length. Then we're putting our putInt 1000. We're doing our buffer.flip, and we're still doing the write buffer. So what have we done here? Well, it's the same code as we had before, as you saw me uncomment, except we're now saving the start position of each integer that we wrote to the file. So we wrote the first integer, 245, here on line 39, right after the string, so its start position will be the number of bytes in the string. Now the second time we define one is here on line 40 when we're defining the position for the next int, and we're then writing the int negative 98765 after that. So the start position for that int is the length of the string plus the int of an integer in terms of bytes. Now the third integer, 1000, well that's actually written last, so its position will be the starting position of the second int. You can see me defining it here on line 44. And then to that we're adding the size of the integer in bytes, integer.bytes, plus the size of the second string. And then we're writing out the value and doing a flip and then writing the contents to the buffer. Alright, so now that we've got that defined, we want to start reading the ints back in the reverse order we wrote them. But let's start working on that in the next video. Alright, so at the end of the last video, we finished off consolidating this code to make it a bit more streamlined, and then we went through setting it up and reading the information back. But let's actually try reading the integers back in the reverse order that we wrote them. So in other words, we want to read the 1000 first, followed by negative 98765, and then followed by 245. So you can see here it's obviously the reverse. Now if you're feeling ambitious, you could try this yourself as a mini challenge. That being the case, pause the video now and give that a go and see whether you can figure out how to actually read the integers in reverse. So pause the video now if you're going to do that, otherwise we'll continue on now. What we're going to do is we're going to use the channel's position method to set the file position before each read. And remember that you also need to call the flip method when you have to as well for that to be able to work. Alright, so let's look at the code to read things in reverse order. So I'm going to come up here. We're going to leave the, actually what we'll do is, it'll take a bit longer, but let's actually just comment out this code altogether. So we've got our channel defined. We're going to create a byte buffer, call up to read buffer is equal to, it's going to be byte buffer dot allocate. Then we just need enough for an integer, so integer dot bytes. Channel dot position. We want to start with our int 3 pos because it's the last number. We're reading backwards, and I'll just put this up so you can see the code that we wrote out. So we're starting at int 3 position, which we calculated in the previous video as being the location for the third integer. Then we want to do a read. So channel dot read buffer. Then we need to do a read buffer dot flip. And then just to confirm it, we'll print it out. So we'll try int 3 equals plus read buffer dot get int. Alright, so we'll continue on. So we'll do a read buffer dot flip again. Then we're going to do a channel dot position. This time, no surprises, int 2 pos. Then we're going to read that into our buffer. Then we're going to do a flip. So read buffer dot flip after the read. Then we'll print it out. So it's going to be int 2 is equal to plus read buffer dot get int again. Then we need to, well, just put this code up a little bit now. Read buffer dot position, and that's going to be int 1 pos. And we can do read buffer dot flip, and of course that should be channel. So read buffer dot flip again, then channel dot read buffer, read buffer dot flip, and then let's print out the last one. Int 1 equals plus read buffer dot get int. Alright, so that's ultimately the code. So for each integer, we're first calling the position method to specify the start position in the file, and we then call the read method with a buffer. Now if you want to write the result to the console as this code is doing, you have to then call flip before calling the get method. And also after writing the value, you have to call flip again before reading the next integer into the buffer. And we then repeat that process for all 3 integers. So we can actually just run that. We've got the integers returning in the right order there from the last one, int 3 through to int 1. So just to clarify, I'm just going to make a bit of space here so it's a bit more clear. So we're doing a flip before the printout, which we're doing in all 3 cases here. Then we're doing before we're doing a channel.position to go to the relevant position, and we're reading it into the buffer. We're doing a flip after reading it from the buffer. So technically there's an extra flip here with a channel.position from int 1, so we could probably remove that and be a bit consistent with our code and do it exactly the same each time. And also I haven't got a read buffer.flip after the printout here and from the int 2, but it would be good to be consistent to do that as well. So basically, like so. So again, we just run it to make sure that it's going to work, and we still get our same results. Now, when reading in a random manner, probably you would normally create a buffer for each read that matches the size of the data. So for example, let's think back to the adventure application. Now, if we wanted to use java.nio to load a location on demand, then we'd already know the length of the location record from the index, So therefore, for each read, we'd create a new buffer of that exact length. Now you might think it'd be more efficient to create a buffer that's long enough or large enough to hold the longest location record and reuse it, but you may never need to load the longest record, and Java's garbage collector will take care of the buffers you're creating, so they won't actually clog up memory. Alright, so now that we've done this, now let's write data in a random fashion. So instead of writing it sequentially, we're going to write all the integers first into the same positions they've always occupied, and then the two strings. So let's have a look at the code and how about to go about doing that. And I'm going to leave the code that I've got in there for reading the integers as is, but you could comment that out if you wanted to. And actually I might just delete this other code here now. Alright, so let's start this. We're going to start with a byte array, output string equals hello. What I'll actually do, just to save a bit of time, why don't we just grab this again? So I'll just start again. I think it'll be quicker. So hello world dot get bytes. Then we want to start with long str1 pos, string 1 position, make that equal to 0. Long int 1 pos equals, it's going to be output string dot length. Then long int 2 pos, we'll call these new int 1 pos and new int 2 pos. That equals new int 1 pos plus integer dot bytes. Then we want byte, which is going to be output string 2, a byte array that is, and that's equal to nice to meet you dot get bytes. So we want long str2 pos equals new int 2 pos plus integer dot bytes. Then we want long new int 3 pos is equal to str2 pos plus output string 2 dot length. Alright, so that's our start, and I'll just move this up. And we're going to create a byte buffer. Byte buffer int buffer is equal to byte buffer dot allocate, and we start with integer dot bytes. Then we want to do int buffer dot, and we'll start with putting an int 245. Then we're going to go int buffer dot flip. Then we're going to do bin channel dot position int 1 pos, and that actually should be new int 1 pos that we've defined above, new int 1 pos. Then we want to go bin channel dot write our int buffer. Then we want to do int buffer dot flip. Then we write our negative integer now, so int buffer dot put int negative 98765. Then we do int buffer dot flip again, and then we do a bin channel dot position new int 2 pos and bin channel dot write int buffer. Alright, so that's 2 numbers done. And next we're going to do int buffer dot flip again, no surprises there, and int buffer dot put int, and we will put there our value 1000, int buffer dot flip again, then bin channel dot position, and that's now going to be positioned to new int 3 pos, the third integer, and we're going to write it, bin channel dot write, and that will be the int buffer again. Alright, so that's our 3 integers, and now we need to write the 2 strings. So to do that, bin channel dot position str1 pos, bin channel dot write, and it's going to be byte buffer dot wrap, and it's going to be output string. And then we want to do bin channel dot position to str2 pos, and bin channel dot write byte buffer dot wrap, and it's going to be output string 2. I'll close it off just so we can see it a bit better. So that's actually the code. Now there are other ways to write this code, but doing it this way does make each step clear. So firstly, we're calculating all the start positions. We're doing this all up here from line 73 down to line 79. And you should be fairly familiar with how these are being calculated by now, so I won't go through them again. And then with each chunk of code here, we're actually writing the 3 integers. And for each integer, we're writing the value to the buffer after flipping the buffer if necessary. Then you flip the buffer to prepare it for writing to the channel, and you then set the channel to the start position for the integer. And then you write the value to the file. And for the second and third integers, you have to then flip the buffer before writing the values to it. Now the strings are simpler when we get down to this code down here from lines 99 and onwards, because we're using the wrap method, and that takes care of creating and flipping the buffer for us. So if we actually run this now, we see that the numbers were printed out as they were before, nothing's changed there. But if we take a look at the file, data.dat, you see that it pretty much looks the way that it's always looked. We just didn't write the values sequentially this time. So again, the point here is that you have to understand how important it is to make sure you call the flip method when changing from reading the buffer to writing it, and vice versa. Now often the reads and writes aren't intuitive. For example, when writing a buffer to a channel, the buffer is being read. Now if you haven't called flip when you're supposed to, you'll usually get a buffer underflow exception when reading from the buffer. So in the case of writing values, you won't actually see the value appear in the file, and that's because you didn't flip the buffer, and the buffer's position will still be positioned after the value you put, and so the channel goes to read the buffer, so it can write the value to the file, and it thinks there's nothing to read. So if you only take one thing away from these videos about doing I/O with java.nio, and that is to remember to flip the buffer when switching from reading to writing, and vice versa. Alright, that's all there is to randomly accessing a data source. Now you've learned the concept in a previous video, and you know the methods available now when using java.nio. In the next video, we're going to move on to another topic, and that's how you can use a file channel to copy one file to another. So I'll see you in the next video. Alright, so let's move on to the next topic now, and that's using a file channel to copy one file to another. So we're going to try copying the data.dat file that we've been reading and writing to a file called datacopy.dat. So to do so, we're going to use a method called transfer from, which is from the file channel class. So add the code that I'm about to go through after the code that reads the 3 integers in reverse order. So looking up here, we've got the 3 integers. So I'm going to put the code there right after that last call that retrieves the first integer, first of the 3 backwards, in reverse order. So we're going to create a random access file class. We're going to call this one copy file is equal to new random access file, and we're going to call this one datacopy.dat, and RW is going to be the mode. And we're going to do a file channel. Copy channel is equal to copy file dot get channel. Then we're going to put long num transferred is equal to copy channel dot. This is the transfer from method. Then we pass channel, comma, 0, comma, then channel dot size. And then we can print out a message to put num transferred is equal to num transferred. And actually what we'll do is put some close commands here. So we're going to put channel.close, ra.close, and also copy channel.close. And we'll just comment out that rest of the code that we're working on in the previous video. Alright, so you can see that when we're using the transfer from method on line 75, we pass the source channel. That's the one we're copying from, and you can see channel is the source which has been defined on line 74, and it's based on the file name datacopy.dat, which we've created a random access file object for on line 73. Now we also need to specify the number of bytes that we want to copy. So here we've chosen the start, which is 0, and channel.size to get the complete number of bytes that are in that file. And notice that I'm calling the method using the destination channel. So obviously data copy.dat, which is our random access file, and then the copy channel that's based from that, a channel has been created from that. So that's our destination. So we're calling the transfer from on that destination channel. And we're using the channel.size here on line 75 to get the number of bytes to copy. And the transfer from method, so you can see there, is storing the number of transferred or returning the number of bytes transferred, and we're saving that into a num transferred variable and then printing that out on line 76. So let's just try running it and see what happens. All right, number of bytes transferred equals 24. We've got data copy.dat. Let's have a look at it. And something weird went wrong. So obviously something went wrong there. What is the problem here? Well, from the source channel, we're using the same channel we used to read the integers in reverse order. So we'll go back and have a look. We're using it here on line 75. Now the position you pass to the transfer method isn't an absolute position. It's actually a relative position. So in this case, the channel's position is currently set to 1 byte after the last integer that you read. And if you want to copy the file starting at absolute position 0, then you need to set the file position before calling the transfer from method. So what we'll do is before that line that does the transfer from or calls the transfer from method, we're going to put channel.position, we're going to set that to 0. And now if we run it again, number of bytes transferred this time, notice it's 40. And if we have a look there now, that's much like we would expect it to be, which is pretty well a mirror copy of our data.dat file now. So that's demonstrating that when working with methods that accept channel and buffer positions as parameters, you have to actually be careful to read the method's documentation to see if it uses the position as an absolute value or a relative value. So in this particular case, the transfer from method is using a relative value, which means whatever you pass is treated as an index relative to the current position. And note also there's a transfer to method that does exactly the same thing as transfer from, except you call it using the source channel rather than the destination channel. So let's actually change the code to use that instead. So the difference here would be instead of this line there, which I'm going to comment out, we would do long num transferred equals, this time we'll do channel dot transfer to, and then we will do 0 channel dot size, comma, and copy channel. And we'll leave the printout there on the next line. Just to confirm, we'll actually delete the data copy.dat. Delete that. And run our method again, or run our code again. And have a look at our data copy.dat. And you can see that it's still there and it has worked nicely. Now usually you use a method in the files class to copy one file to another, but if you've already got one of the files open, using transfer from or transfer to may actually be a more efficient way to do it depending on the operating system. Now we're going to see how to do it using the files class in an upcoming video. Now before we leave the topic though of reading and writing using java.nio, I want to take a brief look at pipes. Now pipes are used to transfer data between threads. And they're actually a one-way connection, so the data can only flow one way. Now a pipe's got two channels, the sync channel and the source channel. One or more threads can write or writes to the sync channel, and the other thread or threads read from the source channel. So let's actually have a look at an example. And what we're going to do now is we're just going to comment out all this code. I'll actually comment out everything. Well, actually what I'll do is I'll just delete some of this stuff that we've got copies of in previous videos, source code, to clean things up a little bit. Likewise for this, I'll just clean all that up. Then I'll just comment out everything else here. Much shorter now, right down to and including the catch. All right. So we're going to try and have a go at one of these pipes. So we'll do a try. Then we're going to do pipe, noticing it's coming from java.no. Pipe is equal to pipe.open. And then we can catch an exception. And just an IO exception. And we'll just print a stack trace if we do get an error. Now you'll need two threads, one that will write to the sync channel and the other that will read from the source channel. So let's actually add the writer thread first. So I'm going to put some more code in here. And we'll type runnable writer equals new runnable. Press enter there so it creates the method for us. And within the run, we're going to do a try. Then we're just going to catch any exceptions. And if we do get one, we'll just print a stack trace. But the actual code, we're going to type pipe.syncChannel. Sync channel is equal to pipe.sync. Then we're going to do a byte buffer. Buffer is equal to byte buffer.allocate. And we'll use the number 56 there. We're going to create a loop for int I equals 0, I less than 10, I plus plus. Then we're going to do a string current time is equal to the time is plus system dot current time millis, short for milliseconds. So we'll assign that to the string. Then we're going to do buffer dot put current time dot get bytes. Then we're going to do buffer dot flip. And then we're going to move down and do while buffer dot has remaining. Then we're going to do sync channel dot write buffer. Then outside of the while loop, buffer dot flip, and then thread dot sleep. We'll add 100 there, and then add a semicolon down here. Now we could have used a lambda expression for the runnable, but we've spelled it out here for clarity. So the write method is calling the pipe.sync method over here on line 18 to get the sync channel. It then allocates a buffer on the next line, and we then got a loop here starting from lines 21 down to lines 33 because we want the thread to terminate at some point. Now inside the loop, we're creating a string that includes the current time. So we're creating it there and then putting it into the buffer. So writing the string to the buffer and then we're flipping the buffer. We're then writing the string from the buffer into the sync channel. And at this point, you have to flip the buffer again once we've finished that for the next iteration of the loop. Then the thread sleeps for 100, as you can see here, to give the reader thread a chance to read the source channel. So let's go ahead now and add the code for the reader thread. All right, so let's do that. So we're going to come down here and put it in our loop. We're going to create our reader. So it's going to be runnable reader equals new runnable. Same deal there, and we'll put the semicolon down there for starters. Then we want to try, and we're going to add a catch there for an exception, and we'll just print a stack trace if we do get an error. So the code for the reader is going to be pipe dot source channel is equal to pipe dot source. Then we're going to do a byte buffer equals byte buffer dot allocate 56 again. Then for int I equals 0, I less than 10, I plus plus. Int bytes read is equal to source channel dot read buffer. A byte array time string is equal to new byte, and we set that to bytes read, the right number of characters, so that it'll fit in our byte array. Then we do a buffer dot flip. Then we do a buffer dot get time string. Then we're going to do a print out system.out.println, and we'll put reader thread plus new string time string. Then we do a buffer dot flip and a thread dot sleep for 100. So this is very similar to the writer. except here we're calling the pipe.source method to get the source channel, or get to the source channel. You can see that on line 51. Otherwise, it's pretty much the same code, except this time it's reading from the channel using the buffer.get, line 54 there, and it writes what it then gets to the console, line 55. So finally, now we've done that, we need to start both threads, first the writer, then the reader. So if we come down and do that, down here, so we're going to do new thread, and we'll start with the writer, dot start, then new thread, reader, dot start. Alright, so let's actually try running this now and see what happens. And you can see that that worked away there, and we got the time, the reader thread reading what the time was, and it went through 10 times as per the for loop and then stopped. So we could try that again, and obviously that's still working nicely. Now if a timing problem crops up for any reason, you could actually try increasing this number here and here as well, if you find that there's some problem with it not working on your computer. But you can see in the case of my computer, it's actually worked fine. So that was how to go about using a pipe to send data from one thread to another. Now there are other ways for threads to communicate and pass data, so it would be a good idea to benchmark the different ways and then choose the one that's the most efficient for an application. So sometimes using a java.nio pipe may not actually make sense. And because of the nature of the content in this course, I've actually added this particular video at a later point after I've actually created the threads section of this course, which confusingly isn't until later in the course. So it's a long story, that the reason that's been designed that way, but the point I'm making here is if you're not understanding these thread concepts, there's a separate section of this course dealing with threads, so you might well want to actually go and check that out, and once you've been through that you could come back and look at this particular video again, and it would probably make a lot more sense. The point is though that I wanted to make this section fairly complete, in that it is important to be able to know how you can use a pipe to send data from one thread to another. Alright, so that's it. That's all there is for reading and writing using java.nio. In the next video, what we're going to do is take a look at how to use java.nio to work with the file system. So I'll see you in the next video. So far you've learned how to create, read and write files and data sources using java.nio. Now sometimes you don't want to read from a file or write to a file. You may want to copy files, delete files, move them, so on and so forth. In other words, you want to work with the file system. Now in this case, java.nio has you covered. In fact, there's a whole package dedicated to working with the file system called java.nio.file. So what we're going to do is start by taking a look at the path interface, which is what you'll use to identify a file on the file system. Now, we've already used paths previously in this section of the course. If you recall, we created them when we wanted to use java.io classes to read and write files, but we called a method such as files.newBufferedWriter so that the buffered writer would be backed by a java.nio buffer and channel. So what actually is a path? Well, no doubt you're familiar with the concept of a file path because you use them all the time. Now, if you open the File Explorer on your system, you'll see a bunch of root folders, usually hard drives, peripheral drives like DVD or Blu-ray drives, external drives, thumb drives, etc. Each of these top-level drives is a root node in a path. For example, on Windows, the directory C:\/ is the root node for the C drive. Now each folder, which is also referred to as a directory, is also a node in a path. And then of course there's the file itself. Now if you've downloaded a file and placed it in the C:\/ directory, again on Windows, then the file path has three nodes. One for C:\/, one for the downloads directory, and then one for the file itself. So this path is unique. You can't have two files with the same name in the same directory because each file is identified by its path. For the downloads example, if you named the file you downloaded data.txt, then the path would be C:\/downloads/file.txt, again on Windows. So you wouldn't be able to place a second file called file.txt into that same directory. So the character used to separate the directory names in a path is called the delimiter, and it can differ between operating systems. For example, in Windows the delimiter is the backslash, but on Unix and Mac the delimiter is the /. So everything we discuss about paths applies to files and directories. To keep things simple, we won't always refer to both, but you can create a path for a file or a directory. Now sometimes it won't make sense to use a path to a directory, for example, when you want to create a file. But other times it'll only make sense to use a path to a directory. It will depend on what you want to do. So just keep in mind that paths can refer to either a file or a directory. Now file paths can be absolute or relative. So the path c:\downloads/file.txt, well, that's an absolute path because it starts at a root node. But the path photos/vacation/mountain.jpg, well, that's a relative path because it doesn't specify a root node at the start. In other words, it doesn't contain enough information to identify the file. So in other words, it would have to be combined with another path that does contain a root node. Now when using relative paths in applications, there's usually the concept of a current or working directory that you can combine with a relative path. For example, when you were running applications that used path, we didn't specify the entire path. We did something like the following on the next slide. You can see there we didn't actually specify the root node. So the string data.txt in that code example doesn't give enough information about where the file is located. But you'll notice that we're calling the file systems.getDefault method first and then the getPath method. So what's happening here is that the getDefault method call returns a file system object with a working directory set to the current user directory. So when running an application from within IntelliJ, the current user directory is the IntelliJ project directory, and so that's the working directory for the file system object. Now the working directory is then combined with the path that you pass to the getPath call, and that's why the files are created then in the IntelliJ projects directory. So instead of what we did in the previous example, we could have done something similar to what you can see on the screen there now. And we've got 2 backslashes there. Because we're using a backslash, we have to escape that so that Java actually knows we're referring to a backslash. But the point is here though, we could have changed the scenario and used paths and then called the .get method with an absolute path call instead of what we did in the previous example. But notice here that we're using the paths class, which has got an S at the end when we call the get method. So there's only 2 methods in the paths class, and both of them return a path based on a string. But anyway, enough talk. Let's now jump back into IntelliJ and we can play around with paths a bit. Alright, so what I'm going to do first is create a new project. And I'm going to click on Java, next. We'll create the template like we normally do. And we're going to call this one, unsurprisingly, paths. And I'll just save it in the right place on my computer. And I'm just going to replace the current project with this new one. Okay, got a bit more screen real estate. Alright, so what we're going to do is create 3 files. Alright, so let's go ahead and create the first one. So we're actually going to do this in the current path. So at the moment you can see the path here is set to the paths folder on my Mac. So just within that path we can right click on the path itself, click on new and click on file. We're going to call this first one working directory .txt. And I'm going to copy some text in there that we're going to use. And this text is available in the resources section of this video. That'll do for that. So that's the first one. Next we want to create a directory within the project directory called files. So I'm going to come back here to the paths again, right click, click on new, this time select folder. And I'm going to call the new folder name files. And then I'm going to right click on the files folder, click on new, click on file. And we're going to call this new file subdirectory.txt. And you can see we've now got a file within that folder. And I'm going to paste some text again in the resources section. And by the way, folder and directory are interchangeable terms. Depending on your operating system, you might be used to calling it a directory or a folder. Essentially, it's the same thing, which you're probably already aware of. All right, now in the third example, what we're going to do is we're going to create a file, but this time we're going to create it in another folder that's outside of the entire path for our current project. And to do that, I'm going to go to the folder, click on Reveal in Finder again. And again, it will be something different on your operating system, but essentially that's the folder that's containing our files. You can see we've got working directory. We've also got this files directory. So I'm going to actually move up one level into my folder there, and I'm going to put the file in there. But the way to do that, I'm going to take a copy of this working directory. You do something similar on your computer, and we'll go up a level, and I'm going to copy that. So we've now got this working directory.txt, but I'm going to call it something else. I'm going to click on that. I'm going to call it out there.txt. So it's actually not in the path at all for IntelliJ. And I've just double clicked that. You'll open that in whatever editor you've actually got. And I'm going to copy some text again that's available in the resources section, paste that in there. And I'll save that. So again, you'll just save it in whatever text editor if you're not using a Mac. So at this point now, we've got three files. We've got this out there.txt that's outside of the project path. You can see in this case, it's the one folder above the paths folder. If I go into the paths folder for our IntelliJ project, we've got working directory, then the files subdirectory, and then the files subdirectory.txt. All right, so back to IntelliJ. And obviously we can't see the out there.txt because it's outside of the project path. So how do we access these? Well, let's close down these files first, and let's actually start writing some code. So I'm going to build some paths now to access these files. We're going to start with a try with resources. So it's going to be try buffered reader file reader is equal to files. Actually, what we'll do, instead of doing that there, let's actually create a static method. So we'll do a private static void print file. And we'll accept a parameter for a path, the path. And I'll make sure we're using the java.nio import, which we are. And we'll do our try with resources in there. So try with resources with the left parentheses, buffered reader, file reader is equal to files, java.nio.file, dot new buffered reader, and path being the argument that was passed to this method. And in terms of the code, we're going to start with a string line. Then we're going to do while, two parentheses, line equals file reader dot read line. Well, that's not equal to null. And we want one parentheses here after the read line method, one extra one I should say, and one to close off the statement. Then we're just going to print out the output. So print line. And then outside of this, we're going to catch any IO exceptions we get. IO exception E, print e.getMessage, and then let's do an e.print stack trace. And I'm getting this error about try with resources not supported at this language level. Let's kind of right click that, click on open module settings, go to project, and make sure that I've got JDK 8 selected there. Click on OK, and that should keep things happy, keeps Java happy now. All right, so that's the method now that's going to basically read the contents of a file and output them on the screen. Nothing particularly hard to understand there. That's all pretty straightforward. So the method opens with a buffered reader, then uses the buffered reader.readLine method to read and print each line until it reaches the end of the file. So let's try this now. We'll try this with the working directory file first. And I should actually rename that because it's not working directory.txt. Working directory file would be more appropriate. So let's just rename that while we're here. Refactor, rename. Working directory file.txt. That's better. And the same for this one, just while I remember it. Refactor, rename, subdirectory file. Okay. All right, so let's start with trying to read this working directory file. So to do that, we're just going to type path is equal to, that's going to be file systems dot get default dot get path. This is a relative path, and it's going to be working directory file.txt. So we want to get it exactly the file name we've got stored in our root project folder. Then let's actually call our method print file path. So all we're doing here is creating a path the same way we've done previously and then calling the print file method with it. Now since this file is in the working directory, we only have to pass the file name to the getPath method. So in other words, we're just specifying a relative path. But we'll run the application to confirm it works. And I'll just move this down to the bottom. And you can just ignore this warning on the screen, by the way. That's an issue at the moment with the Mac on a particular version of the JDK. I'm hoping that they'll correct that soon. The research that I've done has told me that they are working on a fix for that in a future version of the JDK. But at the moment in time, that's not actually fixed. So it just gives you a bit of a warning here when you run a program, a Mac only, but we can ignore that. But the point here is, though, file with the working directory is output, and that's the same content. So clearly that's actually working, and it's read that file successfully. All right, so far so good. We're able to read that file correctly. Let's now try putting the contents of the file in the files subdirectory. So I'm going to start by typing path. I'll call this one file path is equal to file systems again dot get default dot get path, and let's type in the name sub directory. Get your capitalization correct there. And actually what I've done is, I've got that exactly the same, that's good. And then we'll do a print file path. And if we actually run that, and you can see that we've got an exception there. And you can see the error is telling us no such file exception, subdirectory file.txt. So that's thrown when the line that creates the buffered reader in the print file method was executed. In this case, the file wasn't found or couldn't be found because we didn't build the path correctly. When we only specify a file name as we've done here, the string you provide to the getPath method is combined with the file system's object's default or working directory to come up with an absolute path. In this case, though, the working directory is the project directory, which of course isn't the folder or directory that contains the file we're trying to look at. So since the file isn't located in the working directory, we have to provide more information to the getPath method. And we can do that by passing a second parameter to the overloaded getPath method to achieve that. So the way to do that is we come back here to the getPath call, and the first argument will be files, being the name of the subfolder. Then the second argument we leave as it is, which is the name of the file. All right, so we try running that. And this time we're able to get it file within the subdirectory, as you can see here, this output. And that obviously corresponds to the output that's in the file. So far so good. Now if the file has 2 or 3 subdirectories deep, then you'll add each subdirectory as a parameter in the order that you want them to appear in the path. Now you can also pass everything as a single string, and you'll see an example of that a little bit later. Alright, so now just before we end the video, let's print the contents of the outthere.txt file. Now, since the file is located outside the working directory, we can't call the file systems.getDefault and then getPath method. Instead, what we're going to do is use the paths.get method and specify the absolute path. So we can do that by typing, we'll reuse the file path. Let's just reuse that again. So file path is equal to paths. Notice it's paths and not path this time. Dot get, and you'll need to actually put in the exact location where that file is. In my case, if I go back to my Finder, we can see that I have to actually specify quite a long path, but I've also got the path up here that I can actually use as well. So I'm going to do that knowing that I need to specify the folder Java programs and then the name of the file, but you'll substitute it to whatever is appropriate for your operating system. So in my case, it's going to be /volumes /production /courses /programs /Java programs. So we know at the folder where that file is, and then I need to also put another slash there and put in the name of the actual file. So in my case, we called it, if you go back to that folder, Java programs, and that's the name of the file there. So I'll just take a copy of, and I'm going to paste that to the end there. So that's the path on a Mac. If you're on a Windows machine, if you put the file, say, in an examples folder, you might do something like d:// Remembering you've got an escape if you're using backslashes, so you put 2 backslashes for the path on Windows, and it might be d:// // as you can see there, examples, // and then out there.txt, that was the name. So that would be if you've got your file on the D drive in the examples subfolder, and the file is called out there.txt, that's how you do it on Windows. But in my case, I'm on a Mac, so that's the right format for me. All right, so now that we've got that, then we just want to print it out. So print file path. So let's actually run that and see if it works. And you can see here we've got file in some random location on the file system, which is exactly what we want there. And if I go back and have a look at that, file in some random location on the file system. So clearly it's reading from the right file. All right, so let's finish the video here. In the next video, we'll talk a bit more about alternatives to retrieving the working directory and the subdirectory using the paths.get method. I'll see you in the next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
Alright, so we ended the last video by running the application and we saw the contents of the 3 files printed to the console. Now you can always use the paths.get method. An example of that is on line 17. You could have used it for the working directory file.txt and also the subdirectory file text files. Either one of those would have worked fine. But when you know the file's path will be relative to your working directory, it's actually more convenient and in fact better practice to get the working directory using the file systems.get default method and then tacking on the file name using the get path method call. Now you have no way of knowing which directory a user will install your application into, so when you want to install files installed within your application or with your application, you can't specify absolute paths in your code. So you have to rely on getting the working directory for the application. Now you could have the installer store the install path somewhere, but it's still better to get the working directory using methods because it's a foolproof way to do it. Now for user created files, absolute paths may make sense because usually when the user wants to open them, they'll navigate to them in the file system. But in that case, you'll have the absolute path. Now in addition to file systems.get default, there's also another way to get the working directory for an application. And you can use the dot to represent the current working directory. Now if you know your way around the terminal or command prompt, you'll know that the dot always refers to the current directory on both Windows and Unix-based systems. So let's actually print out the working directory using the code. So we're going to come down here and start typing. And we'll do file path is equal to paths.get. And in parentheses and double quote and the dot or the period as they call it. Dot is what we call it in Australia. Then we'll do a sout file path dot to absolute path. So I'll run this and then I'll talk about that. You can see we've got the output showing here right down the bottom in the console output. So I'm using the path.toAbsolutePath method call to get the absolute path represented by the path instance. And you saw that we can see the absolute path printed to the console, noting that it also appends the full stop to the path, and that'll be a / full stop or period if you're running on Windows. And we're going to come back to this in a minute. So what we can try and do is use this dot or period to build a path rather than calling this the file systems.get default method. So let's change the way that we're building the path to the subdirectory file.txt file. So we come back here at the moment, we've got this path file path equals file systems.get default.get path. So we can, in fact, can actually change that. I'm going to take a copy of that, duplicate the line by Command D or Control D. I'm going to comment one copy out. And what I'm going to do is change this method or the method call to paths.get. And in terms of the folder it's going to, we're going to start by putting a period in double quotes there first, comma, and then we've got our files and then the subdirectory file.txt. So here we're actually passing 3 path segments to the get method. Line 16. First we're passing the current directory, which will resolve to the IntelliJ project directory. Then we're passing the files directory, which is the subfolder, and then finally we're passing the file name itself. So you do have to pass them in the correct order. So if you were to pass the file name before the files directory, then we'd get something completely different. We might get something on Windows along the lines of d:// subdirectory file.txt files or something like that. So it obviously would be wrong because the actual file name is appearing before the files. So again, this order is very important as to how you go about calling that. And just to confirm this, let's run this to make sure we get the same results. So we've still got our working directory, we've got our files within the subdirectory. That's still working as well. And obviously we've got the file in some random location on the file system. So clearly the changes we made on line 16 are still working. Now, of course, you can build paths relative to any directory. It doesn't actually have to be the current directory, but keep in mind that a root node has to be included. So when we use this path here on line 18 to get access to the outthere.txt file, we actually specified the absolute path as a single string. And obviously that's the complete path there, in my case on a Mac. But we can also split that up into pieces too if we want to do that. So if we're doing something on a PC, we could, I'll comment this out, we could do something like we could try d:// as the first argument. Then we could put examples and then the outthere.txt. And that would build the path that way. And from a Mac point of view, we could do something like, if you wanted to do 3 arguments, we could do programs as the first, the volumes, production, courses, programs, and comma. As the second one, we could put /Java programs. And the third argument would be the name of the file, outthere.txt. So if we run that, we should find that still works for us. And you can see we've still got the example here, file in some random location on the file system, so it's clearly still working. So we've just broken it up into 3 distinct areas, and we could have broken that up in even more if we wanted to. And again, on line 19, that's the Windows equivalent. Now getting back to down here where we printed out the path, the absolute path of the working directory, and then there's this /dot or /period that was appended to it. Well, as I mentioned previously, that period or dot, full stop, means the directory. So appending the /dot is actually redundant. We don't actually need that in the path. So depending on how you built paths, you could then end up with something weird. So we could end up with something like in Windows terms, we come back up here, if we left that in there, it would be something like d:/examples dot / and if there's a subfolder. So clearly that wouldn't be right with that extra dot there, it's just actually redundant. And by the way, if I change that to ... to subfolder, then /... and then directory, well, that's actually still a valid path. The 2 dots, or the 2 periods, that means the parent directory. So in this particular case, in that example, the path ends up being d:/examples /directories. And the reason for that is, so we've got d:/examples /subfolder, but the 2 dots means move up to the previous folder, in this case moving back to the examples folder, then directory would then navigate down to the directory subfolder from examples. So it's just a way to move back up 1 level to whatever the parent folder was for the current folder. It's a little bit confusing, but in practice it's easier than how I'm describing it. But I think you'd agree, looking at that example with the 2 dots, it's actually better and more readable to not have those dots, the period or the 2 periods in them. You can remove these path segments using the path.normalize method. Let's actually see how that would work in practice. So we can do something like path2 is equal to file systems.getDefault.getPath. And we're going to navigate to the same folder for subdirectory file.txt. So I'm going to use the period in double quotes, files in double quotes, 2 periods in double quotes, and then the file subdirectory file.txt. And actually I want another one in there. I want to put another files in there like so. So now we've done that, believe it or not, that entire path will still get us to subdirectory file.txt. So we're starting on the current working directory. So the single period there in double quotes on line 27, that returns the working directory. So effectively that's redundant and does nothing. Then we move to the files subdirectory. Moving on, we move back up a level because we're using the 2 periods there, which navigates back to the parent, which will be back to the working directory in this case. Then we move down again to the files subfolder, and then we've got the actual subdirectory file.txt path, which is the actual file name itself. So let's just confirm that that works. So we're going to do a print out of path2.normalize method call .to absolute path. So we can do that. Let's also do a print file just to make sure it works. Path2.normalize. So let's run that. So you can see there, that's now the full path. That's the path to our file, and you can see that that still worked. And obviously files within subdirectory, that's the text which is actually within that program. So clearly that's worked okay. So basically the point here is that when you're getting a path from a user or some other source, it's generally a good idea to normalize the path before using it. Alright, so now that you've got an idea on how to build paths to files in the current directory, in a path relative to another directory, or to anywhere on the file system using an absolute path, let's now briefly discuss why the path interface came about. So the java.io file class also points to files on the file system. So why did the Java developers introduce another class that effectively does the same thing in Java 7? So the file class, while useful though, has a few problems. And specifically those problems are, firstly, many methods in that class don't throw exceptions or don't provide specific error messages when they fail. An example would be the file.delete method, which returns a boolean. And if the deletion fails, you can't actually tell if it was because the file didn't exist, or the application doesn't have permission to delete the file, or some other reason. So unfortunately, the method doesn't provide that level of information. Now the file.rename method works differently on different platforms. And Java is supposed to be portable, as you know, across platforms, meaning that the code shouldn't have to worry about which operating system it's running on. Another problem, there's no support for symbolic links. And a symbolic link is a kind of file that points to another file, sort of like a shortcut in Windows, if you're familiar with that. Now they're often used with networks to point to a remote location. Unfortunately, the file class doesn't understand those symbolic links. The file class doesn't provide a way to get metadata about a file, information such as its permissions, its owner, or other security information. The metadata that it does provide is retrieved inefficiently as well. Now, many of the methods don't perform well when working with lots of data. For example, if you use the file class to request a list of all the files in a directory, and there are a lot of files, the method can actually hang, believe it or not. And lastly, the last error, since the file class doesn't understand symbolic links, walking through a directory tree is therefore problematic. So I'll end the video here. In the next video, let's have a talk about how java.nio solves these problems, and also how it splits the functionality that was in the file class into several different classes and interfaces. See you in the next video. So in the last video, we ended up talking about the file class and some of the limitations. So in this video, we're going to talk about how java.nio solves these problems, and also how it splits the functionality that was in the file class into several classes and interfaces. Now the java.io.file class contains methods for pointing to files and also for performing file operations like delete. Now in java.nio, the path interface sticks to file paths. So file operations have been moved to the java.nio.file.files class. Now we saw this class in an earlier video when we used it to read text files, but now we're going to actually look at it in a bit more detail. So the files class contains methods that perform file system operations such as copy, move, delete, etc. Now all its methods are static, so you don't need an instance of the class to call its methods. So I'm going to start off by looking at how we can check whether a file or directory exists, which you may want to do before you attempt other operations on that particular file or directory. Now it is important to understand that the path interface doesn't actually know anything about the file system. It merely understands paths. So in a previous video, we got an exception when we deliberately didn't pass enough information to build a path to the subdirectory file.txt. And if you recall, we saw that the exception didn't occur when we created the path, but rather when we tried to create the buffered reader. So what this demonstrates is that you can successfully create paths to files that don't actually exist. So to confirm that, let's actually give that a go. So we're going to create a path to a file that doesn't exist. So I'm going to start typing path3 equals file systems dot get default dot get path, and we're going to put a file that clearly doesn't exist. So this file doesn't exist.txt, and clearly that doesn't exist over here because we're going to be using the IntelliJ project by default. And then we're going to print out a message there, path3 dot to absolute path. All right, so we'll just run this and see what happens. So we can see here we get the output. So happily it's printing out the absolute path to a file that doesn't exist. Now the java.io.file class operates the same way, by the way. Until you actually try to access a file, the path and file is actually abstract. Now in our application, the rubber only really meets the road when we try to create a buffered reader using the path, and that's why the exception is thrown at that point. Only then does it matter if the file pointed to by the path actually exists. Now, of course, if you're creating a file, then it doesn't matter if it does exist. But to create a file, the directory you specify has to exist. To confirm that, let's actually try the following code. So I'm going to type in path4, and equals paths dot get, and we're going to enter a path that we know doesn't exist. So on my Mac, I'm going to put a fictitious path, volumes/test.ing, something that clearly doesn't exist. And if we wanted to, we could add a second part of that path, abcdf, and we'll finish with a file name, whatever.txt. Now, if you're on a PC, you might want to do something instead like z:\\, comma, abddef, and whatever.txt. So basically, you want to specify a series of parameters to make sure that we're pointing to a path that doesn't exist. All right, once we do that, we're going to just output it. So output path4 dot to absolute path again. And obviously we're not doing anything different to the previous example other than specifying another path. So we should just get it quite happily printing out that path, as you can see it's doing down here. So in other words, no exceptions are thrown. Now because of this, depending on what you want to do, it can well be a good idea to check for the existence of a file or directory before you try to use it. Now let's check to see that the files directory actually exists. So we can do that with by typing file path equals file systems dot get default dot get path. We're going to type in files, and we know here that files is the subfolder that we created in a previous video. And let's actually see whether it exists. So we're going to print out exists equals plus file dot exists file path. So we actually run that. And you can see we've got an exists equals true there. So it's telling us that that folder, or that directory rather, the files directory or the subdirectory, does actually exist. So let's actually check our bogus folder here, either one of those. We'll actually select the second one. We'll actually select the file name, but it could be a folder. And we can do print out exists equals plus files dot exists path4. So if we try that, we should get a false, because that path, whatever we've chosen there, shouldn't exist. We made sure earlier that it doesn't exist. And we get exists equals false there, which is what we expect. Now this exists method has an overloaded method that accepts a second parameter that specifies how you want to handle symbolic links. So you can choose to follow them or not follow them. By default though, they're followed. And if they aren't followed, then if the path contains a symbolic link that points to an existing file, the method will return false. And there's also a files.notExist method which returns true when the file or directory pointed to by the path doesn't exist. Now in a real-world application, you could check for the path's permission in the print file method and throw an exception if the file doesn't exist, or perhaps just let the IO exception be thrown when you try to create the buffered reader. Now, even if a file exists, of course, your application may not have permission to use it. But you can actually check that by using the files.isReadable method, the files.isWritable method, and the files.isExecutable method. All right, so let's move on now on how to copy a file. So we've set up a folder previously that contains that file. But let's actually create another folder now that's got a few other directories. And the folder structure that we're trying to create should look something like this. All right, so that's the folder structure that I'm about to create. You can see we've got an example subfolder, dir1, dir2, and we've got a dir3 here. We've got various files in each one of those structures. So that's the folder structure we're going to try and create. You'll see me creating that when we go back to IntelliJ. All right, so let's go ahead and we'll start by creating that new directory. We're going to call that examples with a capital E. And within the examples folder, we want to create two directories. So it's going to be dir1 and also dir2. Then in the dir2 folder, we're going to have a dir3 folder, like so. And then we need some files in each one of those folders. So I'm just going to take a copy of that and paste it into the first folder. But I'm actually going to change the name and call it file1.txt. So I'm going to take a copy of that. And that file also needs to exist in the dir2 and dir3 folders. So dir2, I'm going to paste it into there. Same file name, and also the dir3. Paste it in there. And we also want that file to appear in the top level examples folder. So I'm going to paste it in there. All right, so we've got file.txt in the examples folder, in the dir1 and the dir2, as well as the dir3. And let's take a copy of the file1, and we're going to call this one file2.txt. We're going to copy that into the dir3 folder, as well as the dir2. Okay, so paste it into dir2 and dir3. Right, so there's our folder structure. We've got examples. We've got file1.txt in the examples folder. We've got a dir1 folder that contains file1 and file2.txt. The dir2 folder contains file 1, 2, and 3, which we haven't added 3 yet, but we'll do that shortly. And then the dir3 subfolder contains file 1 and file 2. So let's just take a copy of this and paste that, and we'll call that file3.txt. And then we'll be good to go. And again, the contents really don't matter of the file. It's more the directory structure and the fact that there are files there. So let's close off some of these files that I've opened. Okay. So we've basically now built up a file tree and a few files that we can work with. So let's start off by writing some code to copy examples.file1, this one here, in the examples folder, to copy that to examples file1 copy.txt. And what we're going to do is comment out some of this code that we no longer need. So I'm just going to comment all that out. And I'm also going to comment out the print file method because we no longer need that. And I'll just add another right curly brace there to make the code valid. And we're going to start by typing path source file. We need to accept that import. That's equal to file systems dot get default dot get path. We're going to use examples. That's the subfolder name. And then the file1.txt. So make sure you get your capitalization correct there, and that's using exactly the same case as you used for your folder names and your file names. So that's the source file we want to copy from. Then the copy file is equal to file systems dot get default dot get path. And that's going to be examples. We're going to call this file1 copy.txt. And then we just want to do a files.copy source file, comma, copy file. And what we need to do is wrap this with a try catch. So I'm going to do that. So try, let's move the code into there. And and we'll catch an IO exception, and we'll print a stack trace if we get an error. So let's just try running that to see that it does work, and we should see that a file1 copy.txt gets created. And we can see we get this file1 copy.txt file that was created from the copy. Alright, so let's finish the video here. In the next video we'll continue on. We'll start looking at how to move a file, how to rename a file, how to delete a file, so on and so forth. So I'll see you in the next video. Alright, so in the last video we created this code that actually copied a file, and we can see that the file1.txt got copied correctly to file1 copy.txt. But I want to show you what happens if we actually run it again, and we're going to make a change to the IO exception. What we'll do is, instead of printing a stack trace, let's actually just print out the message, so e.getMessage. The other thing, just before I run it, just to confirm, we've got file1.txt and file1 copy.txt, so you can see they are in fact, or do have the same content, so it was a proper copy in that sense. Alright, so this time we should, at the moment, with the way we've configured things, get an exception because the file already exists. So let's actually run that and see that that does happen. And you can see the exception was thrown, examples / file1 copy.txt was the actual e.getMessage from the exception that was actually generated. And the reason for that is that the destination file for the copy already exists. And by default, the copy method then throws an exception if that happens. But fortunately, we can change that. If you want the file to be copied even when the destination file already exists, you can pass an optional third parameter to the copy method. So let's actually do that. Up here on line 14, we'll pass the third parameter, which will be standard copy option dot replace _ existing. And now if we run that again, we should avoid the execution block being executed. The exception block, I should say. And now we haven't got any errors on the screen, and then meaning that the file copy successfully went through and the file got replaced, and we didn't get the message printing out in the exception block of code because of course there was an exception. Now the other thing you can do is you can actually copy directories as well as files using the copy method. So let's have a go at actually doing that instead. So I'm going to come down after that code, and we're going to put source file. Well, actually what we'll do is we'll put that here after the copy method. We'll put it in the block because that's where we've defined our path for source file in copy file. So we'll put source file is equal to file systems dot get default dot get path, and we're going to type in examples as the path. And you can see in the left project window we've got the examples folder that we created in the last video. So I'm going to put the get path will be examples. That's the first argument, and the second one argument or parameter will be dir1. So we're basically trying to copy the source file is the directory dir1, which is a subfolder from the examples directory. And the destination, we're going to do copy file equals file systems dot get default dot get path. We're going to go with examples. This time we're going to do dir4. And you can see over here that we've got a dir1, a dir2, and we've got a dir3 subfolder, but we've actually got nothing at that level at all that's relating to dir4. And then we'll just copy this code here and paste it, because that's going to do exactly the same thing, but this time it's going to copy that dir1 folder into the dir4 folder. So let's actually try running it. And you can see over here I've got the dir4 folder was successfully created from that operation. But note that the actual files weren't copied, so you can see that there's no way for me to navigate into that folder because there isn't any files. And I obviously get this little disclosure triangle on my Mac if there are files in that folder. So it's actually expected by default for it not to do that. When you want to copy a directory and all the files and directories it contains, you have to actually walk the file tree. And we'll be talking about that in a future video in this section of the course, how to do that. But by default, when we're copying it, copies just the folder only. So I'm going to delete dir4 since we won't need that anymore. But it's another option. Instead of copying a file, you may want to move it to another directory or rename it. And you can do that using the files.move method. So let's have a go at doing this. Let's move the examples / file1 copy. That's this one here that we created. Move that to the examples dir1 folder, dir1 folder. So we're going to move it into this folder here. So what we're going to do is comment out the existing code so that's not run each time, because that file of course already exists. We'll comment that out. And let's put this at the top of the try. And we'll put path file to move is equal to file systems dot get default dot get path. Then we're going to go to examples, that's the main folder, and then file1 copy being the file that we want to copy. And obviously capitalization, etc. is important here to get it exactly the same, so you can see it over in the left hand project window. So that's path to move, and the destination, path destination equals file systems dot get default dot get path. We're going to move that into the examples subfolder, and then a dir1 folder, which is a subfolder from the examples folder, and we're going to use the same file name, file1 copy.txt. And then we just do files dot move file to move destination, and we'll leave the exception code in there in case we get an error. Alright, so we should see that that file will appear in the dir1 subfolder of the examples folder. So we'll run that. And we can see over here file1 copy.txt appears in the dir1 folder. And note that you have to specify the full path of the destination, as I've done here on line 13. It's not enough to only specify the directory. Now note also that this was a move, by the way, I didn't make that clear. So file1.copy is now in the dir1 folder, but of course it's also moved from where it was, which was in the examples folder down there when we did the initial copy. So that was a move, but if you wanted to rename a file, then you can just use the new file name in the destination path as follows. So let's actually look at doing that. What I'll do first is comment this out, because we don't want that to run again because the source file no longer exists. So I'll put path file to move. Well, actually what I'll do, let's just undo that change I made, and we'll just change the locations. Now this time I'm going to specify file1.txt, and let's just say I want to rename that. What I'll do is I'll get rid of this second argument, because we're going to keep it in the same folder, and we'll call it file2.txt. So basically in this case what we're doing is we're going to rename file1.txt to file2.txt. We're effectively moving it into the new file name, which is the equivalent of the rename, because it's actually moving, which in essence is actually renaming. Now if we run this, we've now got file2.txt from the examples folder. Now when renaming a file, the source and destination directories have to be the same. And just to confirm that, let's actually just run this again. So I'll just go back and rename that. We can refactor that, rename. Change it back to file1.txt again. And just try running it again. It's sitting here on file1, so let's actually make that file2. And that's what I was trying to do. So file2.txt, so you can see there's been renamed. But what I am going to do though, I'm going to still need to use that file, so I'm going to refactor it again, rename, and move that back to calling it file1.txt again. And I'll just comment out those lines so that that move or that rename doesn't actually happen again. Now, just as with the copy method, you can actually pass the standard copy option .replace_existing as a third parameter if you want to move a file to a file that already exists. An example of when you'd want to do this might be when your application uses temporary files until a user explicitly asks to save. You then want to move the temp file to the permanent file, and that file may already exist if the user is working on a file that they've saved before. Now you can also use the move method with a directory, but depending on the operating system, it might actually only work for empty directories, which of course isn't very useful. Alright, so at this point we don't actually need this file1 copy.txt file anymore. So it's time to delete it. Now as you may have guessed, you can use the files.delete method to do this. So we've commented out all the code, so make sure you do that before we do this. And moving forward for the rest of this video, make sure you do comment out the code before you run it each time, because we're making changes to files or deleting them, etc. So to delete a file, So it's going to be path file to delete is equal to file systems.getDefault.getPath. We'll go for examples as the main folder, subfolder, second argument dir1, third argument being the file name, file1 copy.txt, and you guessed it, files.delete, file to delete. That's literally it. And we should see the file1 copy.txt get deleted. And it's deleted, as you can see there. Now if we run this again at this point, that deleted file, we should get the exception code block showing. So we're getting a message there, which is this stage, the e.get message from the exception is just giving us the name of the file, which in this case doesn't exist because we've already deleted it. But what we can do to avoid an exception if a file doesn't exist, instead of using files.delete, we can put files.delete, but call another method delete if exists. And you can probably guess what that actually does. So if we run that again now, you can see we no longer get an error, but in this case the file doesn't exist. But if we actually just take a copy of this file, we'll call it file1 copy.txt, and if we run this code again, you can see it's deleted the file. So either way, we're not getting an exception anymore. So that's a good method to use if you don't want an exception to be thrown if the file doesn't exist. Now you can use the two delete methods to delete directories, but they have to be empty. Now once again, when dealing with directories, you have to walk the file tree, and again we'll be doing that in a future video in this section of the course. But let's end the video here. In the next video, we're going to actually start looking at creating files, how to go about that. So I'll see you in the next video. So we ended the last video talking about deleting files, but at this point now you might be wondering about creating files. We haven't actually really done that at the moment. So the files class does have methods for creating files and directories, but do keep in mind that you're usually creating a file because you want to write something to it. So more often than not, you want to open a stream or a channel, and doing that will actually create the file. But with that said, let's look at how to use the files class to do it anyway. Now we're going to create a file here called file2.txt in the examples directory. So I'm just going to copy or comment out rather this code, and actually what I'll do is I'll comment that out. I'm going to delete this old code from the previous video. Alright, so to create a file, path file to create is equal to file systems.getDefault.getPath, and we're going to use the examples directory as I mentioned, and the file name, let's go with file2.txt. We can see at the moment looking at the directory structure there's not a file2.txt in the examples folder. Now there's a file1.txt in that folder, and obviously file2.txt in other subfolders from the examples folder, but not actually in the examples folder. Alright, and then to create it, we just do files.create file to create. Pretty straightforward, so let's just run that. And you can see we've now got a file.txt showing up in the examples directory. And if you double click it, you can see that no surprises there, it's actually empty. And if you wanted to write anything to it, you'd have to create a stream or a channel. So again, there's probably no point explicitly creating the file using the create file method, but it is there if for some reason you want to create it that way. And the create file method is an exception to the rule in that you can't use it to create directories. So instead, let's actually create a dir4 directory under examples using the method you need to create directories, which is the create directory method. So we're going to do path dir to create is equal to file systems.getDefault.getPath examples, and then dir4. Then we just do a call to the files.create directory method. We'll actually create directory, which is a single method, to single directory I should say, and that should be in lowercase, but just change that, and dir to create. And actually what I'll do now is I'll comment out the file to create, because that's already been created. Let's just run this. And we can see our dir4 folder got created over there as a subfolder of the examples folder. All right, now let's just try taking this to the next level though. Let's try creating a directory called dir6 that has the following path. So examples /dir2 /dir3 /dir4 /dir5 /dir6. Now, you can probably hear you groaning. You're thinking you're going to have to call create directory multiple times. Now you could do it like that, but there's an easier way, and you probably have got a hint of that when you saw what I was typing when I typed create directory. There is actually a create directories command, or method I should say. So let's just see what that looks like. Path dir to create equals file systems dot get default dot get path examples. And then we type in the path. It's going to be, in the case of a Mac, it's going to be dir2 /dir3 /dir4 /dir5 /dir6. Let's just run that, and then I'll give you the equivalent command for Windows. Files.create. This time it's create directories. dir to create. Let's run that. You can see we've got just dir2, dir3, dir4, dir5, and even dir6. So pretty cool that this particular method not only creates the last entry, the last path of dir6 in this case, but it also creates any non-existent parent directories as well, and basically all in a line of code. Now, if you're running on a PC, you would do something like, I'll just comment this out because I'm not, instead of the forward slashes, you'd put 2 double slashes for each one. Something like that. So that's an equivalent thing on a PC. So again, we're escaping the backslash there, as we've done for all paths in this section of the course. So that was one way of doing it. The other alternative we could have done was also something along these lines. I'll comment that one out now. We could have actually done path dir to create equals file systems dot get default dot get path, and we could put examples, in my case on a Mac, /dir2 /dir3 /dir4 5 6. Let's add one more there, 7. So that will equally work well. And actually try running that to confirm that it works. We should have a dir7 now. And you can see we've now got a dir7. So that works as well, putting it all in one line like that, which is pretty cool. And again, on a PC, change the forward slashes to backslashes. And you'll get the equivalent result on a Windows machine. Alright, so the last thing that we're going to look at in this video is how to get a file's attributes. Things like the file size, when it was last modified, whether a path points to a file or directory, etc. And this data is also referred to as the file's metadata. So file attributes or file's metadata. Now, using the files class, you can get the value of a single attribute, or alternatively, you can retrieve all the attributes at once. So let's actually look at getting a single attribute, the file size. So we're going to just comment out that code now. And let's try and grab the file size for the examples, dir1 /file1.txt. So do path, file path is equal to file systems dot get default dot get path examples, and the second argument is going to be dir1 / because I'm on a Mac, 2 backslashes if you're on a PC, file1.txt. So we're pointing to whatever file that we want to get the attributes from. Then we do a long size is equal to files.size file path. And then let's just print that out. I'll put size is equal to plus size. Let's just try running that. Size equals 151, as you can see there. And again on Windows, 2 backslashes to do the same thing. Alright, so that's the size. Let's try another one. Let's try the last modified date. Let's do that as a shortcut. So I'm going to do a print out here and we'll put last modified equals plus, then we're going to do files dot get last modified time file path. Run that. And you can see we've got a time that particular file was last modified. Noting that it contains both the date and time. Now you may have to adjust that time for your time zone. Now we're not going to cover the code to do that since it's really off topic, but there's certainly lots of good information on the internet for that if you want to do that, to change the time zone to whatever is appropriate for your part of the world. Now you can also check the files class to see what other methods are available for getting the value of a single attribute. So let's just quickly go and open the documentation. Okay, the link's in the resources section that I've just pasted. And you can see that if we scroll down, get owner, get last modified times, which you've just seen, get file store, file attributes, is writable, is same file, as also lots of other ones there that you can use. So check that out if you want to find out a little bit more. But the other thing you can do is you can get all the attributes in a single shot. To do that, you'll retrieve an instance of a class that implements an interface containing methods that can retrieve each individual attribute. Let's go and have a look at how to do that. And it's actually the basic file attributes interface that covers a basic set of attributes that are common to all operating systems. So we're going to use it here to get the attributes for the same file, and consequently we'll be using the same file path. So to do that, we're going to put basic file attributes is equal to files dot read attributes file path, and then the second argument is basic file attributes dot class. Then once we've got that, we can start printing out some things. So start off with size equals plus attributes dot size, last modified equal to plus ATTRS, abbreviation for attributes dot last modified time. Let's try a few more. Created equals plus ATTRS dot creation time. Do a couple more. Is directory equals plus attributes dot is directory, and we'll do one more. Is it a regular file? Is regular file equals plus ATTRS dot is regular file. And if you run that, you can see we've got our outputs there. In this case, that file correctly says it's not a directory, but it is a regular file, because of course we're pointing to file1.txt. So the important part is this read attributes method that we're calling from the files class to get the basic set of attributes. So we tell the method which set you want to retrieve by this second argument, basic file attributes.class in this case. The read attributes method returns an instance that implements the basic file attributes interface, and you have to actually pass the basic file attributes.class because there are system specific subinterfaces of basic file attributes in the java.nio package that can also be retrieved using this method. So you can then call methods, as you can see below that, on lines 33 through 37 to get the values for the attributes that you're interested in. Now, in addition to getting the size and last modified time, you can see here we're also getting the creation timestamp, whether the path points to a directory and whether it points to a file. And this is only a very small subset of what's available for the basic file attributes.class. If you go back to the documentation and check that out, there's the link and it's in the resources section, and you can find out the other methods that you can get access to find out more information if needed. Now, java.nio contains other interfaces for file attributes, by the way, that are operating system specific, in that some of the attributes they retrieve are only available on the operating system they target. Alright, so let's finish the video here now. In the next video, we're going to continue our looking at the file system using java.nio. See you in the next video. In the last video, we learned how to create a directory. We're now going to have a look at how to read an existing directory. Now, a directory's content is the list of files that it contains. So to make sure that we're on the same page, I've created a new project called Directories, as you can see on screen. And inside the project, you can see that I've created this project structure, and I'll get you to do the same so you can follow along. Now, the actual file names here can all be empty or can have any contents. That doesn't really matter so long as they're there. So you can see that I've made a subfolder called File Tree, and starting out a subfolder from File Tree dir1, and it's got two files, file1 and file2.txt. We've got a dir2 folder. The dir2 folder, again, that's a subfolder of the File Tree folder. That's got file1, file2 and file3.txt. It's also got a subfolder, dir3, that's got file1 and file2.txt. And then moving back up, back on the File Tree folder, we've got a dir4 folder or subfolder that's got the file name or the file in it, file3.txt. And then finally, the File Tree folder itself has actually got two files in it, file1.txt, file2.txt, in addition to the various folders. And we can just collapse those, and you can see that we've got those two files as well. So you basically want to create that same directory structure, and you've seen in a previous video how to go about creating the directory structure within IntelliJ. All right, so now that we've actually got that, we're going to read the entries in a directory using the files.newDirectoryStream method. Now, this method actually returns a stream which needs to be closed once it's finished, and consequently we're going to use a try with resources statement to do that. And then we'll catch an IO exception just in case there is one along the way. So to start that, we're going to start with path directory is equal to file systems, accept those imports, .get default, .get path, as we've done in the past. And we're going to use the file tree, which is our subfolder, and in my case on a Mac I'm going to put a /dir2, and I need to change the level to 1.8 here, so I'm just going to go into module settings, project, and make sure that I've got Java 8 specified here. And if I do that, that should fix that error. But again, if you're on a PC, the file path will be file tree /dir2. I'll just put that in Windows. All right, so that's the path, and then we want to do this try with resources that I talked about. So we're going to do a try, then in parentheses, it's going to be directory stream, and path contents is equal to files dot, and that's new directory stream directory, in parentheses, as you can see there. And we'll leave that code for now, but we'll actually catch an IO exception. And if we get one, let's just print out the message, so e.getMessage. So firstly, on line 12, we're actually creating the path to the directory. Now we're using filesystems.getDefault to get the working directory so that we don't have to specify the absolute path. And of course, we've talked about that quite a few times in the past. Now when running the application, the working directory will be the IntelliJ IDEA project directory, and so you have to start at the file directory tree when you get to tack on the rest of the path. So that's why we've cut file tree here in the path. Once we've got our path, after also tacking on dir2, we're going on to line 13. We're creating the directory stream. Now notice that the new directory stream method returns a directory stream of paths. You can see that there. So hover over that, directory stream of paths is getting returned from new directory stream. Now directory stream is an interface that implements the iterable interface. So consequently you can iterate over the returned paths to get the contents of the dir2 folder. So let's actually put that iterable code in, or some code that will iterate through. So we'll do a for, in parentheses, path, file, :contents. Let's just print it out. So print system.out to print line file.getFilename. So if we do that, we should get the output. So let's run that. Let's put this output down the bottom. And ignoring that first line in red, which is the Mac warning, which will probably go away shortly once they fix it in a later version of the JDK. You can see that we've got a dir entry there that's been returned, as well as the file 1, 2, and 3. So basically, we've passed the dir2 folder there, and it's given us an entry for dir3, which is a folder obviously, but also the 3 file names. But notice that only the contents directly within the dir2 directory are within the stream. So in other words, the method only returns the first level of content, also referred to as the directory's direct descendants. So it doesn't go into the dir3 directory in this case and return its files as well. But you will see how to walk an entire directory tree a little bit later on. Now, when iterating over a directory stream, a directory iterator exception may be thrown, so it's actually good practice to explicitly catch that, and we can actually do that by using the pipe character. So here under catch IO exception, we can put the pipe character and directory iterator exception, which is another way to catch both. So we haven't really used that much in the course. We normally use a logical OR. The logical OR has got the 2 pipe characters, but using one like this, well, this is known as a bitwise inclusive OR. So when you're actually chaining together exceptions like this, you can use that to put them all on the same line. So it's just a bit of a shorthand way to avoid you having to create 2 separate catch statements. Now, what if you only wanted to list or work on specific types of files in a directory? So for example, let's say the application works with .dat files. Now sure, you could retrieve everything in the directory and then check each path name, but there's actually a better way to do it. Now the new directory stream method accepts a filter as a second parameter, and only paths that match the filter will actually be included in the directory stream. Now the second filtering parameter is referred to as a glob. Now what a glob is a pattern that's similar to a regular expression, but the syntax is more geared towards the types of things you'd want to do when working with paths. And I've got a few examples up on the screen now, as you can see there. We've got a star character to match any string, which can contain any number of characters. We've got star.dat there as an example, will match any path with the .dat extension. You can see another example there is star dot and then dat comma text in left and right curly braces. Well, that'll match any path that's got the extension .dat or .txt. The question mark matches exactly one character. For example, the glob question mark would actually match any path that contains exactly 3 characters. Another example, my file star matches any paths that begin with the text my file. And the last one, b star.txt, well, that would match any path that has at least 2 characters, that is at least 2 characters long, and begin with the character b. Now the question mark here forces a second character, and the star then matches 0 or more characters. Now there's a lot more that you can do than what I've shown there. Now for the complete glob syntax, you can actually check the documentation for the file system.get path matcher method, and I'll just bring that up on the screen quickly so you can see that. And it's this one here, the get path matcher. Now, if the glob syntax isn't sufficient for you to describe the paths you want to retrieve, what you can also do is pass a regular expression and therefore really take full advantage of the power that they offer. But the majority of the time, I think you'll find that the glob should be enough. Right, so let's go back to IntelliJ. So if we wanted to actually make a change here and say to retrieve only the file names with only the files that have got a .dat extension, on the new directory stream method, as a second argument, we could put star.dat. And what I'll do is, just for that to work, at the moment we've got all these txt files. So let's just change one. I'm going to actually refactor and rename this one in the dir2 folder. Let's refactor that to a .dat file extension. So if we actually run this now, we should find that it will return only the dat file. And you can see only file3.dat is returned now because that's the only file that meets that criteria, including the directories as well. Now I said earlier that when you retrieve the entire contents of a directory, you can use the isDirectory and isRegularFile methods to separate files from directories. I said that in a previous video, but there's actually an easy way to do it. But this time a glob won't help. And that's because globs are used to match patterns against file names. So in other words, they don't operate on file attributes. But there's a third version of the new directory stream method that does accept a directory stream.filter parameter, and that allows you to write your own filters. So let's just have a go at writing a filter that only returns files and not directories. Now the directory stream.filter interface has only got one method called accept, so that's the method that we have to implement. Now when accept returns true for a path, the path will be included in the directory stream results. So let's go ahead and do that. So we'll start this code up above the path directory code here on line 10. We'll do directory stream path filter is equal to, and we'll put new directory stream, and as I'm typing I should be able to select directory stream.filter like so, and then I can type in path here, and I'll have to implement the method myself. So it's going to be public boolean accept path parentheses throws IO exception. Then we're just going to do a return files.isRegularFile path. Just tidy that up a bit. And I need to add that other parentheses there at the start as well. And up here, directory stream path should actually be directory stream.filter, because that's actually what we're working on, and that keeps it happy. Now that I've done that, I can actually change the new directory stream method call. We'll get rid of the star.dat there, and we'll change that instead to filter. And again, what we've done here is with the directory stream.filter, that interface has only got one method called accept, and that's the method that I've implemented, and you'll have to implement that. And when accept returns true for a path, the path is going to be included in the directory stream results. So what we're doing here is we're actually testing to see whether the particular path is a regular file. If that returns true, then that means it's going to be shown in the list when we go down to print it out here on lines 20 or on line 20. Otherwise, it won't be shown. So if we actually run this now, you can see we just get our three files there, file1.txt, file2.txt, and file3.dat. In other words, the dir3 subfolder is now not showing because, of course, that's not a regular file. So basically, that filter has now eliminated the dir directory. And keep in mind that since there's only one method to implement, we could also have used the lambda expression instead. So let's just quickly see how we could have done that as well. So I'm just going to temporarily copy this out, or comment this out rather. So to do the equivalent with a lambda, we would do directory stream.filter, and path filter equals, then we'll write our regular expressions, our p dash greater than sign as we've done before for regular expressions, files dot is regular file, and p in parentheses. And by the way, depending on the order of this course, you may not have actually got up to lambda expressions yet. There's an entire section on lambda expressions in this course. And the reason that it's happened like that is that I've come back to this IO section and started adding new content to it. And I did that because students voted for me to stop working on the IO section at the time and go back and work on the lambda expressions and other sections of the course. And then I've come back here and finished it. So consequently, there's probably a few things that are out of order. So if you're not understanding what a lambda expression is, keep in mind that there's a future section of the course where we go through that in detail. There's a number of videos that explain what it is. But for now, this is just a shortcut, another way of actually achieving the same goal. So if I just do that as I've done there, using a lambda expression, run it again, you should get the same result. Same result as you can see on the screen. So it's basically more concise, but again, you get exactly the same results as before. All right, so let's finish the video here. See you in the next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
All right, so now we know how to read directories. We know how to use globs to retrieve paths within a directory that match a given pattern, and also how to write a filter that allows us to retrieve paths based on attributes other than the name. Now, before we learn how to walk a file tree or a directory tree, let's tie up a few loose ends. Firstly, the file separator. Now, most of you probably know that on Windows, you use the backslash to separate a path segment or path segments, but on Unix and Linux systems, you use the forward slash. When building paths and or writing regular expressions or globs, you may need to know the file separator. Now, unless you're only writing applications for yourself, as you're doing when you're learning, you generally can't assume that you're on a specific operating system when you're writing Java code. So there are actually two ways to get the separator for the file system. Now, firstly, you can use the file separator constant, which is still commonly used, but another alternative is to call the file systems.getDefault.getSeparator method. So let's do that both ways and print out the results. So outside of the try loop, I'm going to do string separator is equal to file.separator. That's using the constant. We can print that out, separator. And we can do separator is equal to file systems.getDefault.getSeparator. We can also print that out. Let's just check that out. Now you can see when I've run this on a Mac, I've got the /, but if you're running this on Windows, you should see the /. And if you're running this on Linux, you should see the / as well, because obviously Mac is based on Unix as well. So the point here is that we've got the option to retrieve the separator, and it's actually good practice to never hard code the file separator. Now we've been doing that so far because we're not going to release our demo applications, and if we had insisted on using the file separator when testing, the code would have been pretty ugly to read. So simplicity is obviously better when you're learning, but in a real world application, you do the following to build the path, which I'm about to type in, rather than hard coding. So let's have a go at doing that. I'm talking about this code up here specifically on line 20, because you can see obviously there, the file separator is hard coded on line 20 and will only work for currently for a Unix derived operating system, Mac or Linux. But we can actually change that. So let's do that. I'm going to take a copy of that line and comment one out. Let's say you've got the old version there. So what we're going to do is change this. So we'll put file tree down here, put plus file dot separator plus, then we'll put the rest of the path that we want. Do it that way. Now that way we're now no longer hard coding the separator character. So if we run this, the code still obviously works on a Mac, but you'll find now that we've done this, this will also work on Windows unmodified. So that's obviously the way to go when you're actually producing applications and releasing them commercially. Now when you're building long paths, instead of doing what I've done there, you'd probably use a string builder. But again, for the purposes of learning and keeping the code readable, I'm going to continue to hard code the separator, but keep in mind that that's how you would do it in a real world application to make sure that you're supporting all operating systems. Right, so the other thing we want to do now is figure out how to create temporary files. Now sometimes an application needs to create files that it doesn't want to keep. Now the files.createTempFile method creates a temporary file in the operating system's default temporary file directory. So let's have a look at an example of doing that. So I'm going to come down here and add another try block for it. Try, and we'll catch an IO exception. And we'll just print e.getMessage if there is an exception. The actual code, let's try path temp file is equal to files.createTempFile, and we'll call it my app as the first argument. The second argument we'll put .appext. Then we'll print out temporary file path is equal to plus temp file dot to absolute path. Alright, so the first parameter in the create temp file method is a prefix. Now the temporary file created will have a name that begins with this prefix, and the second parameter you can see here, well, that's a suffix. So in this case you're passing the file extension, which is usually what's passed for this parameter. Now you can actually pass a third optional parameter of type file attribute that specifies attributes for the file, but for temporary files there's often no reason to do that. So we actually run this, and you can see in my case here I've got the temporary file path being on a Mac is the /var, and we've got this subfolder /folders /rz, and then this long file name, which is still part of the path, and then /t, but then there's this my app, and that's that prefix that I talked about that we specified here in the file, and then it's got a temporary ID that's been added automatically by Java, then the file extension .app.ext. And the location will actually be different depending on the operating system you're running on, obviously. In the case of Windows, it'll probably be something along the lines of your C folder. Let's just type it out just to give you a rough idea. It'll probably be something along this lines, I would suspect. So C:\users, whatever your username is, I'll replace that with the question marks, and it'll be something like appdata/local/temp, and then it would probably be the file name, so you can see here something along those lines will actually be appended. So you'd probably see something like that on Windows, where again the 3 question marks would be the username of the account you're using. But you can see that will be configured and specified automatically. The bottom line is you've got access to this file now, which you can use. One thing to note though is that the resulting path name is always associated with the default file system. Now if you want to store the temporary file somewhere else, you can do that by using another version of the create temp file method that accepts more parameters, including a parent directory path. And there are also files.createTemp directory methods as well, if you want to investigate those at your leisure as well. Now, the other thing I want to talk about is file stores, or what you might be thinking of as drives. Now, on a Unix system, each mounted system is a file store. Now, on Windows, each drive or volume is a file store. For example, the C drive, C:, or the D drive, D:. So how do we get the file stores? Well, we can actually use the file system.getFileStores method for that. So let's go down and write a bit of code for that. Let's try iterable file store stores is equal to file systems dot get default dot get file stores. Again, this code should work on all operating systems for file store stores. Then we can print out store.name. Now the method returns an iterable of file store. This is the get file stores. And I haven't highlighted this, but the file systems.getDefault method, well, that actually returns a file system object. Now some systems can have more than one file system, and when you call getDefault, you're getting the default and often only file system. So if I actually run this, I'm obviously going to get the Mac equivalent. You can see here I've got the various file stores for my Mac, but when you run this on your system, you'll get different results depending on basically the file stores that are on your system. So it's basically system specific, as I mentioned. On Windows, you'll probably see the names of the volumes printed out, not the drive letters, so keep that in mind. And it's probably more useful to get the drive letters, and there's actually 2 ways to get them. So let's have a look at doing that. So I'm going to leave that code there, but what we can also do is I'll just take a copy of that. Well, actually what I'll do is I'll just leave that in that loop, and we'll just also print out here, we'll print out system.out.println, and we'll do store. We'll just print out store. Let's have a look at that. So you can see in my case, we've got there /volume/production, and then we've got dev-disk6. So if you're on a Windows machine, you'll probably see that will be the drive letter. That should actually be the drive letter that's actually showing for your machine. So basically the volume name and the drive letter. So this one will give you the volume name and the drive letter. That's our first option there. But just to be clear, let's actually do that. We'll put volume name, drive letter. And we'll just put file store equals. So let's just run that again so it's a little bit clearer. Volume name, drive letter in my case on a Mac, and then also the file store itself. And what you could do is you can actually parse the string to get the drive letter if you're on a Windows machine. Potentially risky. Some developers will consider that risky in the case of the formatting of the return string if that ever changes, but the likelihood of that happening is probably pretty low. And obviously that's only for Windows that I'm talking about here. If you're not on Windows, you probably don't need to do any parsing for the reasons which you can see on the screen there now. You're not actually getting those drive letters because it's not really applicable for that operating system. Now there's another way of doing things as well. It's not ideal, as you'll see in a minute, but let's actually go through and do that as well. So we could come down here and do something like iterable path root paths is equal to file systems dot get default dot get root directories. for path root paths. Then we could do print out a path. So we actually run that. And perhaps to be a bit more clearer, that is the root directory in the case of my machine. So when you run this on a Windows machine, only the drive letters should be printed, but drive letters for all available drives in your systems will be printed when they're actually available or not. For example, if you had 4 USB ports, but only 2 of them were occupied, drive letters for all 4 would actually still be printed. And again, it's not really very useful me showing you this on a Mac, because you can see here I've really only got this one line, which is a pointer to the root directory on my system. But you'll get different results on a Windows machine. The truth is, though, that you usually don't need to get the root drives, because if you think about it, there aren't many cases for this or use cases for this. And that's because when an application is installed, it remembers or can find out where it lives on the file system. And if it then needs the user to tell it where to save files or where to load them from, the user will usually be presented with a dialog and can then navigate to or type in the path. So in other words, you may never need to get the root directory or directories, but if you do have to, one of these methods that I've shown you will actually work for your application. Alright, so let's finish the video here, but in the next video we're going to start going through learning how to walk a file tree. Now, when I'm talking about walking a file tree, we mean that we're going to visit every file and directory that can be reached from a starting or root directory for the tree. So I'll see you in the next video. Alright, we're ready to start learning how to walk a file tree. Now again, when I talk about walking a file tree, what I mean is that we're going to visit every file and directory that can be reached from a starting or root directory for that tree. For example, if we started in dir2, in the dir2 folder in our project, we'll visit the following files and directories, but again, not necessarily in this order. So it would be the dir2 folder, and within the dir2 folder, we've got the files file1, file2, and file3, 2.txt files and 1 DAT file. But then also we'll have the dir3 folder. We'll go into that subfolder as well, and also the 2 files in there, file1.txt and file2.txt. So in this scenario, because we're going to be starting on the dir2 folder, well, that's considered to be the root of its file tree. So we're never going to move up a level from the root directory. We're only going to be moving down levels. Now you might be wondering, well, why would you actually want to do this? Well, one use case might be when the application has to find a file. But another use case could be that the application is searching all the files in a directory and below for a specific string. Now I mentioned in a previous video that when you want to copy a directory, you have to walk the file tree if you want to copy everything below it as well. Otherwise, only the files directly within the directory itself will be copied. And as you saw earlier, in an earlier video, when we're using the directory stream to get contents of a directory, only the direct descendants are returned by default. Now there are other use cases, but those are a few common ones that you might come across. Right, so I just want to talk briefly about the file visitor interface, as you can see on the screen there now. This is what you need to use to walk the directory tree. So using the methods in file visitor, you can run code at each stage of its traversal process. And here are the methods that you want to implement. Firstly, we've got the pre-visit directory method, and this method accepts a reference to the directory and the basic file attributes instance for the directory, and it's actually called before entries in the directory are visited. We've also got a post-visit directory method, and that accepts a reference to the directory and also an exception object when necessary. And it's actually called after entries in the directory and all its descendants have been visited. Now the exception parameter will be set when an exception happens during the traversal of the entries and descendants. Now there's a way to skip files as you're traversing, so not every file has to have been visited for this method to be called. Every file has to be visited or explicitly skipped. Of course, if an exception is thrown and not handled, the traversal will prematurely end and post-visit directory will be called. Next method, visit file, probably the method that you'll care about most. So this method accepts a reference to the file and a basic file attributes instance. And this is where you run the code that will operate on the file. And it's actually only called for files. And lastly, visit file failed. This method is called when a file can't be accessed for some reason. The exception that's thrown is passed to this method. You can then decide what to do with it. You can throw the method, print it, or anything else that makes sense for the application and operation being performed. And this can be called for both files and directories. So as with most interfaces like this, the JDK's got an implementation that you can use called Simple File Visitor. Now you can extend this class and override just the methods that you require. So let's actually go ahead and create a class that extends this Simple File Visitor and traverses the file tree with dir2 as its root. And what we'll do is we'll print the name of every file and directory it visits. So back to IntelliJ. Let's go ahead and do that. So we'll create a new file, a new class rather, so a new Java class, and we'll call it print names. Okay, we're going to extends Simple File Visitor path and accept that import. And we're just going to override the visit file method. So we're going to just do the visit file method. We're going to change this. Instead of returning the super, let's actually start by printing out file.toAbsolutePath. So I'll print out the file name. We'll actually return continue, which is file visit result.continue. So you can see here that I've implemented a class, print names, extended simple file visitor, and I've overridden the visit file method. Often it's a good idea to override the post visit directory as well as the pre-visit directory methods as well, so that you can print the name of the directories. So let's go ahead and do that as well. I'm going to override pre-visit directory. And we can do something very similar with that code. Let's just copy that code and paste it there instead of the return statement. But instead of file, of course, the argument is dir because it's a directory. We'll change that as well. All right, so you'll notice that you're specifying path as the type of simple file visitor. Now this will also be the type of reference passed to the methods. Now in this case, as you can see from the visit file declaration, a path is passed as the first parameter. When we were describing the method, I said that it accepts a reference to a file. Now we couldn't be more specific than that because the parameter type has to match the type you specify for the file visitor. Now inside the visit file method, you can see that I'm printing the absolute path for the file, and then we're returning the file visit result.continue constant. Now you can also return skip underscore siblings, which means the traversal should skip all the other entries in the same directory as the file. And skip underscore subtree, which you can use when you want to skip a directory, as well as terminate, which means that you want to stop the traversal. For example, you'd return terminate when you've found the file that you're searching for so that the traversal is actually stopped. Now it only makes sense to return skip underscore subtree from the pre-visit directory method. Returning it from the other methods is equivalent to continue. Also, if you return skip underscore siblings from the pre-visit directory, then the directory itself is also skipped and the post-visit directory method is never called for that directory. So basically in that scenario you're saying that you want to completely ignore the directory and all its descendants and siblings. Alright, so you can see that I've got the pre-visit directory method added as well to print the absolute path to the directory or the folder. Once again you can see we're using a path. In this case it's not to a file though, it's to a directory, and all we're doing is just printing out the absolute path for that directory. Alright, lastly let's add the visit file failed method or override it. Now if we don't implement this and an error occurs, then an IO exception will actually be thrown. But instead you can notify the user or handle the error and then return continue if you want the traversal to actually continue on in the case of an error. So to do that, we're going to just print out a message here. Error accessing file plus file dot to absolute path plus space plus e.getMessage. And we can return continue. Alright, so at this point now with the 3 overridden methods, we've got a working file visitor. So now what we need to do is start the traversal, and we're going to do so by using the files.walkFileTree method. So let's go back to our main class. and add some code to do that. So we'll print out a message first just to indicate what we're doing. Walking tree for dir2. We'll start with a path. Path dir to path is equal to file systems dot get default dot get path. Let's go with a file tree, making sure I got the spelling correctly. Let's actually use the separator. I know I said I wasn't going to, but let's just use that to make it easier, and it works on both operating systems. Plus dir2. Then we'll add a try here, so it's going to be a try. We're going to do files dot walk file tree dir2 path being the path. Then we want to do a new print names being the class that we just created. Then we'll need to catch an exception there. It's going to be an IO exception. And we'll just do a print out if we get an error. e.getMessage. Alright, so we've created a path now to a dir2 folder that we want to walk. We're then calling, as you can see here on line 59, the walk file tree method. And you can see that it accepting, in this case, we're passing two arguments to it, dir2 path being the name of the path, and print names being the class that we're using that actually extends the simple file visitor. And we'll just run that to make sure it works. And you can see there, walking tree for dir2. We've got all the files. We've got dir2, dir3. We've got our two files for dir3 in the dir3 folder, and also the dir2 is we've got file1.txt, file2.txt, and file3.dat. So clearly that's worked okay. Now there's actually a second version of the walk file tree that accepts 4 parameters. Now the additional 2 parameters allow you to specify the number of levels to traverse and to pass a set of file visit options. Right now though, the only option available is whether to follow symbolic links. Now when you're printing out the names, it doesn't matter whether we use the pre-visit directory method to print directory names or the post-visit directory method. Now depending on what you want to do, it can matter though. For example, if you wanted to copy a file tree, then you'd want to handle the directory before you handle its entries, because the copy of the directory will have to exist before you can copy entries into it. So in that scenario, you would actually handle the directory using the pre-visit directory method. On the other hand, if you wanted to traverse a file tree to delete it, then you'd actually want to handle the directory in the post-visit directory method, because you have to delete all the entries in the directory and all its descendants before you can delete the directory. So whether to handle directories pre or post will actually depend on what makes sense for the type of processing that you want to do. Alright, just one important note here, you can't make any assumptions about the order in which files and directories are visited, so you shouldn't be making any assumptions with your code in that scenario. Alright, so let's finish the video here, and we'll continue on in the next video and create a copy files method and look at how to start copying files. See you in the next video. Alright, so let's now code the copy case. What we're going to try and do here is copy everything in the dir2 folder to a dir2 directory that's within the dir4 directory. So to do this, we want to override the visit file method, the visit file failed method, and the pre-visit directory methods. Now the visit file failed method will be the same as it is for the print example. Alright, so let's create a new class for this. We'll call this one copy files. Okay, we're going to extend simple file visitor again. So extends simple file visitor path. Accept that import. Alright, we'll start with the visit file failed. And for that one, we're just going to print out error accessing file plus file dot to absolute path plus a space plus e.getMessage. And then we'll return continue, which will be file visit result dot continue. Alright, so that's our visit file failed method. Nothing new there. We will now add the pre-visit directory method, or override that. So let's do that. Pre-visit directory. Now, in order to figure out the path for the copied file, we're going to use the path.relativize method. Now, this method constructs a relative path that resolves to a given path. For example, if the path to relativize against is c:\path1, and the given path is c:\path1/path2/path3, then the relativized path would be \path2/path3, which is the given path relative to c:\path1, if that makes sense. So once we've got the relative path, we then need to resolve it against the copied directory's location by calling the path.resolve method. And that will turn the relative path we got from the relativize method into the full path for the copied file. Now, what I said there may have sounded like gobbledygook, so let's actually look at a concrete example. Now, one of the files that's going to be copied is located over here in the file tree, dir2, then it's in the dir3 subfolder, and it's file1.txt. Now, this file is going to be copied into the file tree into the dir4 folder, and there's going to be a subfolder called dir2 copy. Then we're going to have a subfolder of that called dir3, and then it will be file1.txt. So that ultimately is going to be the destination path. So the root of the source path is the file tree, dir2, that's where we're starting, and the root of the destination path is going to be the file tree, dir4, and that's going to be the dir2 copy folder, which at the moment doesn't exist. So the relative path of the file in both the source and destination roots will be dir3, the subfolder, subdirectory, /file1.txt. So you call the relativize method to get the relative path to the source root. And you can see I've got an example on the screen there now for Windows showing the actual paths, the various paths. Now when doing a copy, this will also be equal to the relative path in the destination root. So you then call the resolve method to get the full path of the copy location. So basically the steps, as you can see on screen, as follows, is the source path. You can see there, file tree /dir2/dir3/file1.txt. And you can see the source root then is going to be the file tree /dir2. The target root, which we've talked about, will be file tree /dir4/dir2 copy. And dir2 copy will be a new folder. The relativized path will be source root.relativize source path. So that will be the call to actually get that path. So that'll give us dir3/file1.txt. And then the resolved path for copy is going to be the target root.resolve the relativized path. And you can see there the path is ultimately going to be file tree /dir4/dir2 copy /dir3/file1.txt. So hopefully that's clearer now, but we're essentially figuring out the relative path to the source root and then appending it to the target root, because when doing a copy, the relative path to both the source and target roots will be the same. Now, as you may have noticed, you need the source root path and destination root path to figure out the path for the copy, but the pre-visit directory method and visit file methods are only passed a reference to the directory or file that's being visited. So you'll have to save the source and destination roots as instance variables in the copy files class. So consequently, we're going to add those fields and a constructor to handle that. All right, so we want, firstly, private path. That's going to be source root. Then private path, target root. Let's create a constructor. And the constructor is going to accept both the source and the target and assign the fields to, or assign the parameters, I should say, to the constructor to the appropriate fields. So now that we've done that, we can add the pre-visit directory method to get this working, and I'm going to include some printlns in there as well. So we started work on the pre-visit directory, or we overrode it at least, but let's actually write the code now. We're going to start by typing path, and it's relativized path is equal to source root dot relativize, that's going to be dir. Then we're going to do, we'll just do a printout for that so we can see what's happening. So relativized path is equal to plus relativized path. Next we want to do the copy directory, so it's path copy dir equals target root dot resolve, and it's going to be relativized path. And let's just print that out as well. So it's going to be resolved path for copy equals plus copy directory or copy dir. Let's add a try to this now. And we're going to do files.copy dir and then copy dir. And we have to catch an IO exception if there is one. And the code for that, we're just going to print out the message, e.getMessage for the exception. Then we'll return if that does happen to skip underscore subtree. But assuming we get past that, we're going to return continue, which will be file visit result dot continue. Alright, so you get the relative path, or we're getting the relative path to the source root using the relativized or relativize method here in line 32. Then we're calling the resolve method to get the path for the copy. This is on line 34. After that, we're calling the copy method to make the copy, line 38. And if an exception occurs, as you saw, we're going to skip the subtree by returning file visit result dot skip underscore subtree. And that means that you stop processing entries for that directory. All right, so that's the pre-visit directory method overridden and working. Or hopefully it'll work when we test it. Let's now override the visit file method. So for this one, just as with directories, we're going to use the relativize and resolve methods to figure out the path for the copied file. And once we've got the resolved destination path, we can call the copy method to do the actual copy. And it's probably just as quick if I just delete that and copy this code from the pre-visit directory and then just change a few things rather than just typing it all out again. So let's go ahead and do that. But we do need to change a few things as I mentioned here. For starters, we're going to change, instead of this being directory, we'll make that file. And this will be file as well. Now in the case of an exception, what we're going to do is just print out the exception. We're not going to return anything at that point. But we will return continue down here once the method's finished. So very similar, as I mentioned, to the pre-visit directory. We're using the relativize method and the resolve methods to figure out the path for the copied file. And once we've got the resolved destination path, we're calling the copy method, as you can see there on line 55, to do the actual copying itself. Alright, so at this point now we need to kick off the copy in the same way we did when we printed the file tree in the previous video. So let's go back to the main method. And we'll come down here. And let's print out a message first. And we'll go copy dir2 to dir4/dir2 copy. So we know what's going on. And path, copy path, is equal to file systems dot get default dot get path, and the path is going to be file tree plus file dot separator. We'll do that so we can do this cross platform, plus, and it's going to be dir4 plus, and we'll do the separator again, file dot separator plus, and the folder name is going to be, or the directory name, dir2 copy. So basically the path that we're going to be copying to is going to be file tree /dir4/dir2 copy. And obviously backslashes if you're on Windows. But by using the file.separator, we can get this working for both platforms. Alright, so that's the path what we're going to be copying to. So let's actually invoke some code. So we'll do a try here. And we'll put a catch in there for any IO exceptions that might be raised or thrown. And we'll print out e.getMessage if we find there is an exception. Then the actual code itself is going to be files.walkFileTree dir2 path. And dir2 path is still assigned from line 57, which is our source folder. And then we're going to do new copy files. Then we're going to do a dir2 path again, which is our source, and our destination, which is copy path. And that should be it. So again, looking at dir4 at the moment, there's no dir2 copy. So let's actually try running this and see if it works. Okay, so you can see that the dir2 copy directory has appeared. If we open that up and have a look, we can see there's a dir3 folder in the dir2 copy. If we open that up, there's file 1 and file 2, and also the file 1, 2, and 3 as well. still sitting there in the dir subfolder. We can close that down and see that that seems to work quite nicely. So yeah, looking back at our path, we had dir2, we had a dir3 folder, we had files file1.txt, file2.txt, file3.dat. That was in the dir2 folder. Then in the dir3 subfolder, we had file1 and file2.txt. So you can see we've got a mirror copy or mirror image of that in our dir4/dir2 copy folder, and the dir3 folder's also got those two files. So that's pretty cool. We've been able to actually copy that entire tree now. Now, in a real-world application, you'd probably want to beef up the code to handle situations, for example, like the destination file or directory already existing. What you could do, perhaps, is prompt the user and ask whether the existing file should be overwritten. For directories, you'd then have to decide if it was an error when the directory you're copying to already exists. In addition, you can pass more parameters to the copy method to specify what should happen if the destination path already exists. So you'd have to consider all these scenarios in a real-world app. Alright, so you've learnt quite a lot about using java.nio with the file system. Alright, so let's finish the video here. In the next video, we're going to actually start talking a little bit about mapping common java.io operations to java.nio. See you in the next video. Alright, so in this section of the course, we've learnt quite a lot about using java.nio with the file system. Now, some developers still use java.io, and many existing Java applications, especially those written before java.nio became available, still use java.io. In addition, many code examples around the web also use java.io. So it is very important that you be able to read java.io code and understand what it's doing. So we're going to finish up this section of the course now by discussing how to map common java.io operations to java.nio. So let's start with paths. Now, I mentioned that rather than using java.io.file, it's better to use java.nio.path. Now, you can use the file.toPath method to convert an old-style file instance to the preferred java.nio.path instance. So let's actually give that a try. So we can type something like file is equal to new file, and I'm just going to have a path, something along these lines for my Mac. This will also work on Linux, file.txt. But you would do something similar on a PC like C:\\examples /file.txt. So I can then convert that by typing path converted path is equal to file.toPath, and I can print that out. Converted path is equal to plus converted path. If I run that, converted path equals /examples /file.txt, which of course is what it was in the file object. Now note that it doesn't matter whether the string that we pass to the file constructor points to an existing file. Just like with paths, the file doesn't have to exist until the code tries to access it, and even then, sometimes it's okay if the file doesn't exist. For example, when opening a stream. If the file doesn't exist, it'll be created at that point. Alright, so once we've got a path object, we can go ahead and use it with all the java.nio classes and methods. Now in the last video, you learned about the path.resolve method that takes part of a path and resolves it relative to another path instance. Now, you can do the same thing using the file class, but you have to do it when the file instance is created using the version of the constructor that accepts a file and a string as parameters, or the constructor version that accepts two strings. So let's have a look at that. So I can start off with file parent equals new file, and I'm going to use /examples for my Mac, but for PC, let's stick with the example there, C:\\examples. And we'll do file resolved file is equal to new file parent, comma, and then the path, and we're going to use dir/file.txt. Again, on a Mac. On Windows, you do something like dir/file.txt. You can print it out, resolved file dot to path. And then we can also do, using the other version of the constructor, resolved file equals new file. So we could pass them separately. So we could do /examples as the first argument, and for the second one, dir/file.txt. And again on Windows, the two arguments would be C:\\/examples, and the second one would be dir/file.txt. And we can print that out, resolved file dot to path. So let's run that. And we can see that we've got that working nicely as well. And in terms of what we've done, so parent, which is on line 78, well, that's the instance we use to invoke the resolve method, and we pass the child part of the path as the parameter. So up here with the first call to the resolved file.toPath, we're passing a file instance as the parent and a string as the child. And you can see that's getting converted to a path, and it's returning a path for us. In the second example, we're passing the parent and the child as strings, and we get the same result. And incidentally, both of these are equivalent to us doing something along these lines. Path, parent path is equal to paths.get. I'm going to do /examples again. But again, on a Windows install, C:\\/examples, or 2 backslashes actually. And path child relative path equals paths.get. Again on a Mac, dir/file.txt, or on Windows, dir/file.txt. And we could print that out, which would be parent path dot resolve child relative path. Run that. You can see that the output's identical there. So basically both of these options, the resolved file.toPath, the example there with passing the file object and the child path as a string, or passing the two strings as the constructor, is equivalent to what we've done there on the code in line 85 through 87. Alright, so we also learned previously in this section how to call the files.move and files.delete methods to move or rename files as well as delete files. Now the equivalent methods in the file class are file.rename2 and the file.delete methods. Now that's pretty self-explanatory, so I won't code an example for those. Now in all the examples we've used filesystems.getDefault to get the working directory for the application, and that actually returns a path. Now when working with many java.io methods, you actually need to use a file instance. Now there are several ways to do this, but some of them have drawbacks. And that's another reason why working with paths and the java.nio classes is better. But here's a hack that is more robust than a lot of other solutions. It's getting the working directory, so let's have a look at doing that. So file, working directory, equals new file, 2 double quotes, dot get absolute file. We can print that out, working directory is equal to plus working directory dot get absolute path. Bit of a hack, but it's one that is more robust than other solutions. Now just run that to confirm that it does work. And you can see that's consistent with the directory you can see at the top of the screen there for the current working directory for this particular project. The reason this works on line 89 is because when you pass an empty string to the file constructor, it actually translates it to the current directory for you. And of course, that's the working directory for the application. Now, one major difference between java.io and java.nio is the way you list the contents of a directory. Now, previously in this section, you learned how to use a directory stream when working with java.nio. But when working with java.io, you use the file.list method and file.listFiles method. Now these methods do the same thing, but the list method returns an array of string, and the listFiles method actually returns an array of file. In addition, you can pass an optional filtering parameter to the list method. So let's just take a quick look at a couple of examples of this. So we can do file. So what we'll do is we'll start printing a message so we know that it's separated. We'll print dir1 or dir1 contents using the list method. So we're going to do file, dir2 file is equal to new file. We're going to use the working directory file object that we created on line 89. It's the first argument. And then we want to pass the actual reference to the subfolder that we want access to. So we're going to use /file tree /dir2, and that's for my Mac. But if you're on a Windows machine, you'll want to do something along the lines of /file tree /dir2. Now that we've got that, we can do a string array dir2 contents is equal to dir2 file dot list to call the list method. Then we'll do for int I equals 0, I less than dir2 contents dot length I plus plus, and then we'll print out dir2 contents for element I. And let's just also, just to be clear there, we'll put I equals plus I plus, we'll do that like so. Alright, so let's try running that. Alright, so you can see that we're printing the dir1 folder. Well, actually I said dir1 in the comments up here, but we're actually using the dir2 folder. So technically that should have been dir2, just to be consistent there. But you notice that it only went one level deep, so it showed us the dir3 folder, but it didn't go into the dir3 folder, but it did give us the other 3 file names as well. So again, it's only returning the first level entries, it doesn't walk the tree down to any sort of subfolders. And we can do something similar using the list files as our method. So we can come down here and we'll do print dir2 contents using list files. We'll do a file array dir2 files equals dir2 file. Again, dir2 file is defined on line 93 dot list files. Then we can do the same thing for, well, let's actually just take a copy of this and just make a few little changes just to save a bit of time. That's going to be dir2 files this time. And it's going to be dir2 files I, but then we want to do dot get name to call the dot get name method, because of course we've got an array of file objects here. I run that. And you can see we've got an equivalent result there using the list files method. And you can see it's walked through the tree there, but again, it's only stuck to the first level entries. It doesn't walk the complete subfolder tree as well. And the only real different thing there is the get name method. When we print the files, that returns the last segment to the file path, which in this case is the file name. Now, I discussed previously how to get a system's root drives or file stores and how it can be problematic. You can actually use the file.listRoots method to get the roots, but it has the same problem as the file system.getRootDirectories method. So in other words, it lists drive letters for drives that actually aren't available. Now, there are many more java.io versus java.nio operations, but the differences are straightforward in that the method names are usually a close match. You should now know enough to be able to read code that accesses and modifies the file system using java.io and java.nio methods. So that's actually it for the IO section. If you can take away only one thing from this section, it's to use java.nio when working with the file system. But when it comes to reading and writing file contents, sometimes java.io streams are still the better choice. You should really run benchmarks and decide what's best for your application though, but my advice is to do as I mentioned, use java.nio when working with the file system and when reading and writing file contents. Often the java.io streams are the better choice. Alright, so let's move on now to the next section in this course. So we're going to start this section on Java concurrency by defining a few key terms that you need to know as they relate to Java. So I'm going to start off using the term a process, and that's a unit of execution that's got its own memory space. Now each instance of a Java virtual machine, the JVM, runs as a process. I guess that's not strictly true for all JVM implementations, but really for most of them. And when we run a Java console application, which we've been doing a lot of this course, what we're doing is we're kicking off a process. When we run a JavaFX application, we're kicking also off a process as well. Now, many people will use the terms process and application interchangeably, and we will, in fact, have done that in this course, and we'll do that in this section as well. So if one Java application is running and we run another one, each application's got its own memory space, also known as the heap. So the first Java application can't access the heap that belongs to the second Java application. So in other words, the heap isn't shared between two applications or two processes. They each have their own. Let's talk about a thread. So a thread is a unit of execution within a process. So each process can have multiple threads, and in Java, every process or application has at least one thread, and that's the main thread. For UI applications, this is just called the JavaFX application thread. In fact, just about every Java process also has multiple system threads that handle everyday tasks like memory management and input-output. We, as the developers of Java applications, don't explicitly create and code those threads. Our code runs on the main thread, which is created automatically by your Java program, or in other threads that we explicitly create. And in this section of the course, you're going to be learning how to create these threads. So creating a thread doesn't require as many resources as creating a process. And the thing to remember is that every thread created by a process shares that process's memory and files. And this can cause big problems with your applications, and you'll find out about that in a later lecture. Now, in addition to the process's memory or heap, each thread's got what's called a thread stack. And the thread stack is memory that only that particular thread can access. And we're going to look at what's stored in the heap versus what's stored in the thread stack in a later lecture in this section as well. So every Java application runs as a single process, and each process can then have multiple threads within it. So every process has a heap, and every thread has a thread stack. So I guess at this point you might be asking, why would we want to use multiple threads in our application? Why not just stick with the main thread as we've been using, in the course? What are the advantages? Well, there's two main reasons why you'd want to do this. Firstly, we sometimes need to perform a task that's going to take a long time. Now, for example, we might want to query a database, or we might want to fetch some data from a website on the internet. So we could do this on the main thread, but the code within each thread executes in a linear fashion. So the main thread wouldn't be able to do anything else while it's waiting for that data to come back, or from the database or from the internet. So another way of putting this is that the execution of the main thread will be suspended. So it has to wait for the data to be returned before it can execute the next line of code. And to the user, this could appear as if the application has died or is frozen, especially when we're dealing with a UI application. And if you've already been through the JavaFX section of this course, I did show you a simulation of locking up a UI application where it appeared to be frozen, waiting for a particular thread to finish. So these are big problems that we need to avoid as developers. So instead of tying up the main thread, what we can do is create another thread and execute the long running task on that thread that we've just created. And what happens there is that frees up the main thread so that it can continue working and executing, and it can report progress or accept user input and perform those other tasks on the screen or in other parts of the program, while that long running task that we kicked off in another thread continues to execute in the background. So that's the first reason you might want to do it. But the second reason we might want to use threads is because an API requires us to provide one. Now, sometimes we have to provide the code that will run when a method that we've called reaches a certain point in its execution. So in this particular case, we usually don't create the thread. We pass in the code that we want to run on the thread. And we'll see examples of this later in this section as well. So that now brings us to concurrency, which refers to an application doing more than one thing at a time. Now, that doesn't necessarily mean that the application is doing more than one thing at a time or at the same time. What it means is that progress can be made on more than one task. So let's say that an application wants to download data and draw a shape on the screen. So if it's a concurrent application, what it can do is it can download a bit of data, then switch to drawing part of the shape, then switch back to downloading some more data, then switch back to drawing more of the shape, and so on. So what concurrency really means is that one task doesn't have to complete before another one can start. And the good thing here is that Java provides thread-related classes so that we can create Java concurrent applications. So that's a very short explanation of some of the terminology. So don't worry if you're having trouble grasping these concepts. Concurrency is something that's best learnt by example. So we're going to move on in future videos to creating some threads so you can see how these work by analysing the Java code itself. But before we do, we really have to understand that when working with threads, we're at the mercy of the JVM, the Java Virtual Machine, and the operating system when it comes to when the threads are scheduled to run. And as a result, or because of that, output can vary from run to run, and you might not see the exact same output that someone else sees when they run an application on their computer that uses concurrency. As an example, we can't guarantee in which order lines will be printed to a console because of the very nature of threading itself. But that's it in a nutshell. Let's start in the next video going through some practical examples of how threads work. See you in that next video. So I've created a new IntelliJ project and called it Threads. So go ahead and do that. And of course, this is just a basic console application. So we just put in a simple printout here. Hello from the main thread. And we run that. Of course, you've seen something similar a million times so far in the course. And we see the output. And this is the application running our code on the main thread. And obviously that includes the code in the main method that we've just added to with our system.out.println. So let's make this a little bit more exciting. Let's go ahead and create a thread. So we can do this in two ways. The first way is to create an instance of the thread class. But let's think about what we want to do first. What we're trying to do here is to kick off a thread that's going to run some code. So we need a way to tell the thread what code we want to run. And we're going to do that by creating a subclass of the thread class and then overriding the run method. So rather than creating a thread instance, we're going to create an instance of our subclass. So let's create the subclass first. So we're going to come over here to our source folder. I'm going to right click that and create a new class, and we're going to call that one another thread. So we need to override the run class, but before I do that, I need to extend from the thread class so we get access to those methods. So we type extends thread being the superclass, and now we can override. We get the additional option, so we're going to select the run method. That's the one that we want to override. And we're going to remove the super.run because what we want to do is put the code that we want executed. So in this case, we're just going to print out another console message. Hello from another thread. Really basic. So now that we've done that, let's switch back to our main class. So after the main thread writes the console, we're going to now create an instance of the another thread class based on the class we've just created. So to do that, we type thread, another thread, is equal to new, another thread. I'm going to put a space there so we can see it a bit easier. And when we do that and run it, we still only see the output from the main class, and that's because we've defined a thread, but we haven't invoked the run method yet. So we need to actually invoke the run method so that it executes for us. Now you might be thinking, okay, how do we execute this? Do we use the run method? Well, in actual fact, we use the start method. So to another method .start, and what that does is enables the JVM to run the run method for the thread. And if we run that, we can see hello from another thread. So clearly the thread has now run and executed the code that we defined in the run method. So again, it's important here to remember that we have to create an instance of a thread, which we did on line 8, but then we also have to start the thread independent of that, which we did on line 9. So let's now print something from the main thread after we've started the other thread. So after line 9, we want to print out a message, hello again, from the main thread. So let's run that. And you can see we've got the output on the screen. But remember at this point that when we run, we might see the second line from the main thread printed before the line of the other thread. And this is going to vary, so we might have to run it a few times to see that this happens. But if we run it again, run it a few more times, we can never assume it's going to run in the same order. And it really does depend on the timings, how long a particular thread takes to run. So in this case, it's fairly consistent given that it's just outputting. But what we can do here is when we're dealing with threads is keep in mind that it's up to the system to schedule when the threads will run. And in relation to that, we can influence the order of execution by setting a particular thread's priority. But even with that said, we can never assume that threads are going to run in a particular order. So keep that in mind that although here it seems to be very consistent with I'm running it each time and we're getting the same output each time, that isn't guaranteed because ultimately the decision for the priority in terms of which threads are running, even though we can influence it to a degree by setting a thread's priority, it's up to the system itself to schedule when those threads will ultimately run. Now, rather than creating a named class for the other thread, we could also have created an anonymous class. And this is useful if you're only ever going to want to run the code once. In that situation, an anonymous class would work and is probably easier to configure. But if you intend to run the same code several times, then creating a class for the thread, like we did with the another thread class, would make more sense and be a better result. But notice here that I said run the code several times and not start the thread several times. The thing to keep in mind here is we're not allowed to start the same instance of a thread more than once. So in other words, if you create a subclass of thread and you want to execute the code in the run method more than once, then what you have to do is create a new instance of the subclass every time you want to run its main method to execute. You can't start a thread instance that is already run, in other words. So let's try starting the instance of another thread again just to show that it won't work. We should actually see an exception if we try and do that. So we'll go ahead and add the code to do that. So we type another thread, .start again. We should see there's an exception when we do that. And you can see we have got an exception on the screen, illegal thread state exception. So again, using a subclass of thread means that we have to define the run method once, but we can't reuse the same instance. So we'll delete the second start so we don't see the exception again. So let's do that now, delete line 13. But getting back to anonymous classes, when we use an anonymous class, we have to start the thread immediately. So that's another consideration when deciding whether to use a named or an anonymous class. And of course, the named class is the one that we've already defined using the another thread class here. So let's create another thread as an anonymous class and have it print a line to the console before the main thread prints its hello text again, or hello again text. So I'll come down here after the first start and we'll type new thread. And this is the way to create an anonymous class. And it's going to be public void run. And the output is going to be hello from the anonymous class thread. And then after the closing brace, we do start and select it that way. So if we run that now, you can see that's now working with the anonymous class. And again, just to note that the only thing we know for sure is that the first line we see in the console will be the first line printed by the main thread. We can't guarantee that execution order. So if we try running it again, and you can see what's happened here, hello from the anonymous class thread, that's outputted after the hello again from the main thread. And this is what's happening with the thread. So we've created a thread and we've used .start to run it immediately, but because it's a thread that runs in the background, the way that the system, my computer, has scheduled things is that it outputted the hello again from the main thread before the new thread from the anonymous class got to execute. And that will depend on your computer. You may get a similar result or you might get a different result altogether. So basically I'm saying is that may vary from time to time, even though it seems to be pretty consistent with I'm running it here now. It's likely that on other computers you'll get different results. And obviously in this case it's a short, very trivial example. And it's possible as a result, because we're really not doing much in the way of processing in these threads that we're creating, that the order is pretty much going to be the same each time you run it on your computer. But the point is, it may not be the order in which we created the threads, and indeed that is the case here, because in my example we created the anonymous class on line 11, and yet that code was executed after the system output was printed out on line 17. And again, this may be completely different when it runs on your computer. So we can't guarantee the order that the threads are going to be executed, or in which the print statements ultimately appear here. Again, I'm hammering on this a little bit, but I want to hammer home that we can't guarantee the order in which threads will execute. And that's one of the main reasons why working with threads can be tricky for you to work with, especially initially, to get your head around the concepts here. So let's now adapt what we've done to make it a little bit easier to see at a glance where the outputs in the consoles are coming from. A good way to do that is to give each thread its own color. Now, the method we're going to use works with the IntelliJ console, but it might not work with another IDE console or within the Windows native console, because we're going to be using Unix escape code. So if you're using something other than IntelliJ, you may not see the coloring. But just try it and see what happens anyway. But in any event, you'll see the colors on the screen in this video anyway. So I'm going to create a new class here. I'm going to call this class thread color. And I'm going to paste in some code. Now, I'm not going to type this code in because it's really only some constants. And you can grab this text file in the resources section of this video and be able to do the same thing. And you did see something similar in the file input-output section in any event. So in order to use these colors, we need to append the color code that we want to use before the text that we're outputting. And once we've set a color, that color will remain in effect until we use another color escape code. So if we want to return to the default code, we append the ANSI_reset, which will set it back to the default color. So let's have the main thread use purple, the named one use blue, and the anonymous thread to use red. And if you want to, you could change that to black, but bearing in mind, depending if you're using the dark theme or not, you might find that it's not viewable. So I'm choosing colors that should work on whether you're using the dark theme or just a regular theme that comes with IntelliJ. So looking at the another thread coloring first, we'll click into that, and I'm going to add here ANSI_blue plus and hello from another thread. You can see that's automatically added the import there for the class we just created. So go back to our main class again, and we're going to add, again, depending on whether you're running a white background or the dark background. If you're running the white background, you might want to do it in black, but I'm running the dark one, so I'm going to use purple. So ANSI_purple plus, you can see that was added automatically. And then with the anonymous class, we're going to use ANSI_red. Perhaps we'll use green, it will look a bit better. Doesn't really matter which ones you use, so long as you've got a different one for each of the sections. So again, we've defined, looking back in another thread, we've defined blue for our regular named thread. And for the regular main method, we're using purple, and we're using green for our anonymous class thread. So if we run that, we can now see the outputs. We've got blue. So you might be wondering, why have I got blue twice there? Well, what I didn't do is down here, I didn't specify a color. And by not specifying a color, it's used the color of the last thing that was outputted. So this was hello from another thread. If we go back to another thread, that was in blue, as you can see up there. So consequently, it used that because that was the next thing that happened to execute in order. So what I should really be doing here is making that ANSI, it's called purple as well, to guarantee that it's going to be outputted in the right colors. So now we should see the right result. So you can see that we've got now purple showing for our main method, the output from there, blue from the other thread, the named thread, and then a yellow from the anonymous class thread. Well, it's actually green, but to me it looks a bit more yellowy than green. The bottom line here is it's now a lot easier to see which statements are coming from which thread. So we don't have to read the thread, we can just look at it at a glance and look at the colors and know that that output has come from that particular thread. So change those colors as appropriate if they're a little bit hard to read. So long as you've chose a different color for each section, you'll be good to go. Okay, so I'm going to finish the video here now. In the next video, we're going to talk about implementing Runnable, which is a way to create threads using another method. So the Runnable interface is another way of creating a thread which really only requires us to implement one method. But in any event, we'll look at doing that in the next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
So I mentioned there's a second way of creating a thread, and that's to use the runnable interface. And the advantage of using that is it only requires us to implement a single method. Just wondering, can you guess what the name of that method would be if we're using the runnable interface? Well, very similar to the previous way of creating threads, we need to implement the run method. So instead of implementing the run method of a class that subclasses thread, we can have any class implement the runnable interface, and then all we have to do to is add a run method to that class. Of course, we'll then want to write the code in the run method to execute on a thread that we've created. But we'll get to that in a minute. So first, let's create a new class that's going to implement the runnable interface. So I'm going to go over and do that and call the class myRunnable. And this time we're going to do an implements instead of an extends. So we're going to implements the runnable interface. Runnable. And you see it's complaining because it's saying it must be declared abstract or implement the abstract method run. So we obviously need to do just that. We're going to override or implement that method. So come down here to implement the method, which is going to be run. We're going to use another color, but let's use red for this one. So ANSI underscore red plus, maybe make a bit of space so it's a bit nicer, easier to read. Hello from myRunnables, implementation of run. So we go back to main now. So to run this code on a new thread, we create an instance of the thread class, not a subclass, but this time we pass an instance of the myRunnable class to the thread constructor, and we then call the thread instance's start method just like we did before. So let's add this code just before the second output here. So we'll do it on line 20. So we type thread. So should be myRunnable thread. myRunnable thread is equal to new thread, and this time we pass a parameter of the new object, which we create by typing new runnable. So we've now created a new thread based on the myRunnable class that we just created a short while ago. Then from there we can type myRunnable thread dot start. So if we run that, and we get hello for myRunnable's implementation of run, which obviously was in red, which we selected for that class. So just as when creating threads by subclassing the thread class, we can also have an anonymous class implement runnable and pass an instance of it to the thread constructor. So let's change the code that we just wrote on line 20 to do something like that. So I'm going to leave the new runnable in there, and I'll just delete this, so I'll leave that there. So new runnable, and then let's create the anonymous class. So we do that by putting a left brace there, and then we can override. So I can do an override, and notice how it's come up with com.timbercharcoal.myrunnable, so it knows we're overriding that particular run. Select that, close off the brace, and instead of the super.run, need another bracket there, then we can leave the myRunnable thread.start there. First of all, if we do that and run that, notice how we still get the same output because we've used super.run, so it's running the run method from the myRunnable class. So we close that down, and instead if we get rid of the super, and we put something like, and we'll do an ANSI red again to be consistent, plus hello from the anonymous classes implementation of run. When we do that, we should see that we get the output from the anonymous class this time because we've overridden the run method. Hello from the anonymous class implementation of run. So a question now you may have is, why should we use runnable versus subclassing the thread class? In other words, when should we use either way? Well, most of the time developers use the runnable way of doing things. The reason is that it's more convenient, and there's also many methods in the Java API that want a runnable instance passed to them. For example, since the introduction of Lambda expressions, it's become even more convenient to use anonymous runnable instances. So when we have a choice, because we're not calling a method that requires one or the other, there isn't really a right or wrong answer, but most developers use a runnable because it's more flexible. So that would be my recommendation, is to consider doing that. But when we read code written by others, you'll probably see that more often than not, that they'll be using a runnable version. So one thing we haven't mentioned is that a thread will terminate when it returns from its run method, either implicitly because it reaches the method's end, or explicitly because it executes a return statement. Now, a common mistake when creating and running threads is to call the thread's instance run method instead of the start method. So remember that we have to implement the run method, but we don't call it directly. The JVM will actually call that for us. But what happens if we make this mistake? Well, our application won't crash, but instead of running the code in the run method on a new thread, the code's going to be run on on the same thread that called the run method. That sounds a little bit confusing, but let's show this in action. And another good thing that we can do is we can set the name of a thread by using the setName method. So let's do that for the thread that we created earlier to distinguish it from another, so we know exactly where our code's running. So we'll change the another thread here on line 12. And let's set it to another name. So it's going to be another thread dot set name, and we'll call that something like another thread, just so it's clear. You'll see why shortly. And if we go back to the another thread class, hello from another thread, but instead of putting from another thread, let's change this and put hello from plus, and we'll use it plus current thread dot get name. So it's going to return the name of the current thread that's being executed. So if we run the code now back in main, you can see hello from another thread, and because we set the another thread instance to set name to another thread there. So that's doing as we thought it would. It's creating and running the code in that thread. So if we close this down, but if we make the common mistake now of calling the run method directly rather than the start method, we'll see something different pop up. So we'll change now on line 14 dot start to dot run, like so. And now when we run it, you can see we've got an entirely different result there. We've got hello from main. So clearly it's now not running in the same thread, it's running on the main thread, which the main method is actually running on. So that's a very important reason why you don't want to be calling the run method directly, and why you want to be calling the start method instead. So let's change that back now to start and run it again, and we should see the blue output is now running, which it is on the other thread. So now that we know how to create and start threads, let's look at what else we can do with threads when they're running. Now we can ask them to sleep or to stop executing for a specific amount of time. Now you might want to do that to give other threads the opportunity to run, and you might also want the thread to do something every time a specific amount of time has passed. For example, we might want to write something to a file every 15 seconds, or we might want to check for data we've requested every 2 seconds. We might also want a thread to sleep when we know that it's got to wait for another thread to do something, and we know that the other thread only does it every 10 seconds, for example. So what we could do is put the first thread to sleep for 10 seconds rather than having it continue to run when we know it's going to be at least 10 seconds before it gets any results from the second thread. So that all sounds a little bit like hocus pocus. Let's go back to the another thread and put some code in practice. So we're going to put some code in the run method for the another thread. So let's add a try block and get it to sleep for 3 seconds. So we're going to type try, and we're going to do thread.sleep. And notice how the input, the argument it's looking for is milliseconds. So 3 seconds will be 3000 milliseconds. Then we need to catch the exception here, which is interrupted exception, which is the exception we need to catch when we're using a thread.sleep. And I'm going to put out a message there, ANSI blue plus another thread woke me up, because that will be executed if another thread did just that. Then after that we can put in some message here to say ANSI blue again, blue plus 3 seconds have passed and I'm awake. Okay, so you can see what we've done there. We've added a try catch, and we've got the thread, or told the thread to sleep for 3 seconds, and the exception will only be thrown if another thread did wake us up. So if that's the case, we're printing out a message just to indicate that. If that doesn't happen, we come down here after 3 seconds have elapsed to say that we're now awake. So to see this, let's just have a look at main. We're going to run main and just watch the output when we run this. And notice that it printed the initial message, and that's because we had the initial message going back to our another thread. The first message was printed out immediately, then there was a pause there for 3 seconds, and then it finally come back and said 3 seconds have passed and I'm awake. And just out of interest, if you go just go back and have a look where we added the .sleep. We looked at this, I think I showed that briefly before. Sleep has got 2 options there. We've got the first method we used was just had a parameter of milliseconds, so we used that for 3000. But the overloaded method also accepts the milliseconds, but also nanoseconds. So in that second scenario, it adds the 2 together to determine what the sleep interval is. If you want to be a bit more precise, in other words. But in our case, we just used the first method and just specified exactly 3 seconds or 3000 milliseconds. So as I alluded to, it's possible for a thread to wake up prematurely because another thread interrupts it, which we'll be talking about in a moment. And of course, when that happens, as I mentioned, the interrupted exception is thrown. Now, if the thread isn't interrupted, as you saw, it woke up after 3 seconds and then printed the line about being awake. And that worked, obviously, because at this stage, none of the other threads we've created has got any code that interrupts this thread. And so, of course, we didn't get the exception thrown. But it's important here to note that it's never guaranteed that the thread will sleep for the interval we specified. It could be interrupted, just as we've discussed. Also, the JVM has to call the underlying operating system to put the thread to sleep, and it's possible that the operating system may not support the granularity that it's asking for. So, for example, it may not support nanoseconds. So it's really operating system dependent, operating system and JVM independent as to how long that will be. So again, as you saw, there was clearly a delay there. If I run it again, see the first message is output and we wait for 3 seconds, and then we'll see the second one come on the screen after the 3 seconds had elapsed. So just before we finish this video, let's talk a bit more about interrupts. So we interrupt a thread when we want it to stop what it's doing and to do something else. Now, more often than not, when you do that, you'll interrupt a thread because we want it to terminate. So as an example, suppose we've got a thread that's monitoring a buffer for data that another thread's fetching. So when the other thread determines that there will never be any more data to fetch for whatever reason, we can interrupt the monitoring thread and then it will terminate. So there's 2 ways for threads to notice that they've been interrupted. The first way is to catch the interrupted exception, and we wrote the code for that in the run method for the another thread class. We saw that will be thrown with the sleep method there. When the run method doesn't call any methods that throw interrupted exception, it should call the interrupted method periodically to check whether it's been interrupted. And that method will return true when another thread has interrupted it. But how does one thread interrupt another? Well, it calls the interrupt method on the thread instance that it wants to interrupt. Now, of course, that means that it'll need a reference to the thread instance to be able to do that, to be able to call the interrupt method on that other thread. So I'm going to end the video here. In the next video, what we're going to do is we're going to modify our code to have one of our other threads interrupt the another thread instance when it's sleeping, just to see how that works. So let's work on that in the next video. Okay, so we're talking about getting another thread to interrupt another thread, and we talked about using the interrupt method to do that. So it means that we need to have a reference to the thread instance, and the easiest way that we can test this is to go back to our main class and interrupt the another thread class because we've got a reference to the another thread instance there. So let's go back and do that. And what we'll do is, so we'll call the interrupt method just before printing the second line from the main thread. So just after the myrunnableThread.start, come down here and we'll put another thread dot interrupt, like so. And then on line 32, we've got our regular second printout from the main thread. But let's also go back and change the run method in another thread because we want it to terminate if it does get interrupted. And to do that, it's quite simple. All we really need to do is return from the run method. So we want to do a return straight after we've printed out the message to say another thread wake me up. So we had the return there, which should immediately terminate the another thread instance. So let's go back to the main method and run this and see what happens. And you can see that it finished quickly, and we got the message here, another thread woke me up. And of course that message came from the interrupted exception that was thrown, the message there on line 17, and that came about because we used another thread.interrupt on line 30. And just to confirm, let's delete that line again now and just check that it still does do the interrupt correctly. So run that again now, and we should find that it works as it did before. Pause there for 3 seconds. 3 seconds have passed and we see the regular output because this time it didn't get interrupted and didn't terminate, at least up until the point of printing that second message. Then of course it terminates because it's finished the run method. So we've seen that we can put a thread to sleep, and it's possible to get it to wake up periodically to see if there's any work for the thread to do. So let's say we've got a situation where we know that a thread can't continue to execute until another thread's terminated. Now, for example, we might know that there won't be any data to process until the thread that's fetching the data has completed executing. So in that scenario, rather than waking up the thread periodically to see if there's any data, we can join the thread to the thread that's fetching the data. And when we join a thread to a second thread, what happens is the first thread will wait for the second thread to terminate, and then it will continue to execute. So let's join the thread that we assigned to the myRunnableThread variable in the main class to the another thread instance. So the thread will then stop executing until another thread's terminated, at which point it's going to wake up and continue executing. Now the code that runs on the myRunnable threads contained in an anonymous runnable object, and that's perfectly okay. It doesn't matter whether we join from a thread instance we created using a runnable or a thread instance we created using a subclass of the thread class. All we really need is a reference to the thread that ultimately we want to join with. So if we come back here and in the myRunnable thread, and after the first printout, we need to add a try catch. So it'll try, and we're going to type in here another thread dot join. Then we need to catch interrupted exception again. So catch interrupted exception, and we're going to print out in the same color for this particular thread, which is ANSI red, plus I couldn't wait after all. I was interrupted. And of course that will only happen if indeed it was interrupted for some reason. So again, what we're doing here is we're calling the join method of the thread that we want to join the current thread to. In this case, we want to join to another thread, so we call the join method using the another thread instance, and you saw me do that on line 27. And we'll notice that, again, as I mentioned, join can throw the interrupted exception, and that's because just like with the sleep method, join can terminate prematurely if this thread's interrupted by another thread. So when working with threads, we already know we can't guarantee in which order threads will execute. We also can't make assumptions about how long threads will sleep or wait. So really what I'm getting at here is there's really never any guarantees. Now when we run this code, which we're about to shortly, another thread will put itself to sleep. Because of that, we should see the code running in the myRunnable instance print hello. Then we won't hear from it again until another thread's woken up, which should be around 3 seconds. At that point, the myRunnable thread's going to wake up and continue execution, and we'll see that it'll print that it's running again. And of course, what I need to do to print that message is output it, which I haven't done yet. So I'm going to do that. ANSI red plus, and we'll put another thread terminated. So I'm running again. So again, what should happen is when we run the main method, another thread's going to put itself to sleep. Because of that, we'll see the code running on the myRunnable thread instance print hello, the first part before the try. Then we won't hear from it again until another thread's woken up, which should be around 3 seconds. At that point, then hopefully the myRunnable thread will wake up and continue execution. Then we'll see that print that I've just added on line 28 showing on the screen. So let's run this now. And we can see that that did work. We can see that we have obviously had the 3 seconds where another thread was sleeping, and we also had the myRunnable thread printed out the first message, hello, from the anonymous classes implementation. It then paused, and you notice that it didn't then continue and show the second message on line 28 up until we had seen that the another thread's 3 seconds had elapsed. So in other words, it did correctly wait for that to terminate before it finished itself off. And obviously this is quite a simple scenario, so we didn't really have any problems running this because we're not interrupting any of the threads. But what would happen if we join thread A to thread B and thread B never terminates? Well, what would happen is our application wouldn't terminate, and it would probably look as if it had actually died or crashed. So to prevent this situation, we can pass a timeout value to the join method. And you may have seen when I was typing in this method here, method here on line 27, there was an overloaded method there. So when you add a timeout value, thread A is going to wait for thread B to terminate or for the timeout period, whichever happens first. So in other words, if thread B hasn't terminated, when the timeout period's passed, then thread A will stop waiting for that to happen. So let's try this. We're going to go back and we'll put another thread to sleep for 5 seconds. So we'll go back and make that change. So I'll make that 5,000 milliseconds now, so 5 seconds. Then go back to the main. And in the join method on line 27, we'll use the overloaded method and we'll get it to wait for 2 seconds. And it uses milliseconds just as the sleep method does. So again, 2,000 being 2 seconds. And just to be consistent, if I close down the run window, it probably wouldn't hurt to put here another thread terminated or timed out, comma, so I'm running again. So if we do that, we'll run that, we'll see what happens. And we saw that another thread terminated or timed out, and so it finished early, and then we didn't actually change the text for this, but 5 seconds have passed, then I'm awake. So remember when we changed that to 5 seconds in the another thread. But if we go back there again now, and change that back to 3,000, and go ahead and remove the parameter from the join again, we should find it operates like it did before. 3 seconds have passed and I'm awake, and then another thread's terminated or timed out, which is what we expect to happen. So obviously when we join one thread to another thread and the join times out, we have to handle that case in a real world application. For example, if the thread was waiting for data and the join times out, then we wouldn't have any data to process, and we'd have to somehow report that to the user, like error downloading or something like that. Now there are other methods in the thread class we can use, but we've covered the ones that we'll use the most. The only other one I want to mention is the set priority method, and we can use that to try and influence the order in which threads are run. But you should really regard setting a thread's priority as more of a suggestion to the JVM and the operating system rather than a command. In fact, some operating systems don't support this set priority at all and will ignore it. As usual, never assume that setting priorities will force threads to run in a particular order. It's really ultimately up to the JVM and the operating system as to how that runs. And just out of interest, to learn more about the set priority method and the other methods available in the thread class, check out the documentation, and I'm just going to bring that up on the screen so you can have a look. Paste that in. A little bit bigger so we can see it. And there's a link on the screen there. So do check that out to find out more about some of these other methods and also about the set priority method. Quite useful information there for you to find out a little bit more about the thread class. Okay, so that ends our introduction to threads and concurrency. In the next video moving forward, we're going to look at how working with threads can lead to nasty bugs that can be very difficult to debug, and ultimately show you how to get around those as well. So see you in the next video. So far, the threads we've created don't use any variables. All they do currently is print text to the console. So let's create a couple of threads that do something a little more interesting. So we'll start by creating a new console project, clicking on Create New Project, as we've done probably hundreds of times now, selecting Java, Next, and creating a command line app, and I'm going to call this one Counter. Okay, and let's move this over a little bit so we've got a bit more space for our source code. So what we're going to do is have two threads counting down from 10 using a countdown object. So we'll add two more classes to our application, countdown and countdown thread. Now we could put them in their own files, but since this is just a simple demo, we're going to add them to the main Java file. So let's write the code to do that, and then we'll discuss it as we work through it. First, we're going to copy the thread color class we used in the last lecture in this project. So I'm just going to copy that, and I'm going to create the new class. And if you recall, it was called thread color. Thread color, and I'm just going to paste that code in. Save a bit of typing. Like so. So it's just the very basic codes that we used in the previous lecture. So let's now go back to our main class and in our main method, and we'll put some code in there. So we'll come down, actually what we'll do first is we'll create these classes. And I mentioned we're just going to do that because this is a simple demo. We're going to create these classes in main.java. So the first one is going to be class countdown. And we need a public method, public void. We'll call this one do countdown. And we need a string for the color. Then we need to introduce a switch statement. So switch, and it's going to be thread dot current thread dot get name. And if you get this error here, what that means is we haven't got JDK8 set up. So we need to go back into preferences, into the project, right click the project and click on open module settings. And we need to make sure under project that our project language level, I think I said JDK, but project language level is set to 8. And if we do that, the error then goes away because we're able to use a string in a switch statement, which was only introduced in a later version than our default, which was set to 6. So the first one here now is we're going to do case thread1. Thread 1 being the name of the thread, and we're going to be having 2 threads running. So if that's the case, we're going to change the color. So color is equal to thread color dot ANSI, and let's just go for cyan. Should look okay. We can always change these if we run it and it doesn't look correct. Then we'll break out of that. And the second case will be for thread 2. And for color, we'll put thread color dot, let's try a purple. Let's see what that comes out like. And do a break as well. And then the default is going to be, if we do get down to there, we'll change the color to something different. So thread color dot ANSI, let's go for a green. Okay, so all that has done is set the color. So now we want to do some output. So put something on the screen. So we're going to put a for loop. So for int I equals 10, I greater than 0, I minus minus, so we're counting down from 10. We're going to do a print out color, which sets the color when we're printing it out, plus thread dot current thread dot get name. And then we need to add the number as well, so it's going to be plus, we'll put a colon there to separate it, I equals in double quotes plus I. So that should be all we need for countdown. Now we're going to create a second class, and this class will be will extend the thread. So it's going to be class countdown thread extends thread. So we want a private field, which is going to be the countdown class we created on line 12. So private countdown, and it's going to be, we'll call that thread countdown. Thread countdown. Then we want a constructor, so it's going to be public countdown thread, and we're going to pass a parameter which will be the countdown object, and we'll just call it countdown. And all of the constructor will do is assign the value to our field. So thread countdown equals the object passed, which was countdown. And then we need a run method. So it's going to be public void run. Give me a space here. Thread countdown dot do countdown, which is executing that method that we created on line 13. And then the other thing we'll do is we'll come back over here to the main method now that we've created those 2 classes, and we'll put some code in here to set the names and to start the threads. So to do that, we'll create a new object first. We countdown is equal to new countdown. Then we'll create the 2 threads. So we'll call them countdown thread, and we'll just call it T1. It can be anything you like. So equals new countdown thread, and we'll pass countdown to it. Once we've created that, let's assign the name, .set name, and we'll call that thread 1. Bearing in mind that these need to be identical to what we've defined on line 21 and 23 below, and 24 below rather. And the second one, countdown thread T2, thread 2 equals new, countdown thread, and we'll use the same object, countdown, but we will change the name. So T2.setName, thread 2. And all that's left for us to do now is to execute it, so, or to start it to be more correct. So T1.start and T2.start. Okay, so that's the code. Whoops. Clean that up a little bit. So let's just go through what we've typed in. So looking at the countdown class first, which we've got defined on line 18, there's one method there, the doCountdown method. When this method's called, the code counts down from 10 to 1, at which point the for loop then exits because it's obviously finished. We're using the color trick that we've used in previous videos, and we can see from the switch statement that we've got one thread named thread 1, which will print the text in cyan, and a second thread called thread 2, which is going to print the text in purple. And we also have a countdown thread class that we created on line 39. And that extends thread, obviously, because we need to do that so that we can execute it, we can start it. So when an instance of that class is started, the run method will call the doCountdown method in the countdown class, so all instances of this thread will count down from 10 to 1. So we create the threads in the main method, as you saw at the top here. We gave each of them a name and pass the same countdown object to both threads, and lastly we start the threads. So let's now run this and see what happens. So you can see what happened there. There was thread 1 running, which countdowns from 10 to 1 in cyan, and thread 2 did the same thing but in purple. And you can see now by looking at this how the system's switching between the two threads. So we can't predict when each thread is run and will be suspended. So every time we run, we're going to see a different result here. So let's run it a few times just to see what I mean. So if we run this again, noting the order that was showing in there, you can see that one was entirely different. We actually got the complete results in cyan for thread 1. Running it again. And there's another result. Sometimes it's the same, but as you can see, if I keep running it, it does change, and we can see we've got purple there for thread 2 coming up a couple of times. So we really can't guarantee the order, or can't predict when each thread will run and then when it will be suspended so that the other thread can run, because that's based on the operating system and what it's doing. So now that we've done that, let's make a small bit of change to the code. Instead of using a local variable in the for loop, let's use an instance variable. So to see what I mean, we're going to come back up here to our countdown method, and we're going to introduce an instance variable or field for this class. So private int I in the countdown class. And then for the for loop, instead of creating the variable, we're going to use the instance variable instead. So I'm going to get rid of the initial definition and just put I equals 10, which is now going to obviously use the instance variable. So all we've really done here is change the local variable to an instance variable. So you'd think that the code should still count down from 10 to 1. And if we run it, we should expect the same thing. Well, probably you would expect the same thing, each thread counting down from 10 to 1. But let's just run the application to confirm that. And notice how we've got something different this time. We didn't see what we expected to see. Instead of each thread counting down to 10, both threads seemingly have seemed to skip numbers. So it's possible that some numbers here are even duplicated, and you can see that in the case of 10, for thread 2 and thread 1, the numbers are duplicated. Now, since every time we run the application we get a different result, we're going to discuss the following results that I got for one run of this application. So here's an example image just to make it easier so that we're all on the same page, as you can see there. And just make that a little bit bigger. So we can see in this particular example, the number 10 is duplicated, and we got that when we run this live as well. But after that, in this particular example, each number only appears once. So thread 2 skips all the numbers that thread 1 prints, and vice versa. And also, interestingly enough, thread 1 prints 3 after thread 2 prints 2. So what's going on here? So mean, after all we did was change the local variable to a private variable. Other than that, we didn't really touch the code, but as you can see, the results have now changed drastically compared to when we originally ran it, when both threads were happily printing out the full numbers. So let's talk about what's going on and gain an understanding of that in the next video. So continuing on from the previous video, and we went through an example showing how by just changing the instance variable, we got a completely different result with our multiple threads. And probably at first glance, you'd think that it wasn't doing what it should be doing. So when I introduced terminology relating to threads, I briefly mentioned the heap, and that's the application's memory that all threads share. Now, I also said that every thread has a thread stack, and that's memory that only that thread can access. So in other words, thread 1 can't access thread 2's thread stack and vice versa. But they can both access the heap. Now, local variables are stored in the thread stack. That means that each thread has its own copy of a local variable. In contrast, the memory required to store an object's instance value is allocated on the heap. In other words, when multiple threads are working with the same object, they in fact share the same object or share that object. So they don't have their own copy as such, and so when one thread changes the value of one of the object's instance variables, the other threads will see the new value from that point forward. So how does that relate back to our application? Well, we're passing the same countdown object to both threads, and you saw that defined on line 8 and 10 on the screen. When we used a local variable for I, that was okay, because when the JVM allocated the space for the local variable, it used each thread's stack. Consequently, each thread had their own copy of I on their respective thread stacks. However, when we switched to using an instance variable, the JVM allocated the space for I when it created the countdown object, and it did so at that point on the heap. Now, threads share the heap, so in that case, or in this case, the two threads don't then have their own copy of the variable I. They in fact share the variable that's on the heap. So what that means is that when thread 1 executes and changes the value of I and then gets suspended so that thread 2 can execute, thread 2 will then see the new value of I as it has been updated from thread 1. It won't see the value of I that it had when it was last suspended. And that's why each thread is sometimes skipping a number and why numbers can appear out of order. So let's take a close look at the output above in the screenshot that I've got there and try and make some sense of it. Now, we have to keep in mind that a for loop is actually several statements. I'm talking about the for loop on line 36. The first time it's executed, it assigns the initial value to the variable. It then checks to see whether the for condition is met. If it is, the code within the loop is executed, and I'm sure you understand that because we've been using for loops throughout this course. But when we return to the for statement, it will then decrement I in this case and then check the condition again. So basically a for loop consists of several steps, and a thread can be suspended between each step. This is the key point I'm making here. So a thread can be suspended between steps. As an example, a thread could be suspended after the for has decremented the I variable, but before the condition has been checked again. Another example, it could also be suspended after executing all the code associated with the for loop, but before executing the print line. So let's, thinking about that, let's list out some potential suspension points here. So in the for loop, a thread could be suspended just before decrementing I, just before the condition, or just before printing out the value. So 3 spots there. And thinking about it, there's actually more suspension points than this because the println statement involves concatenation and IO and effectively calls multiple things. But this is really a good, really good enough understanding of what's happening. The point here is that there's multiple points where the current thread could be suspended. So when we analyze the output, all we can really be sure of is what the value of I was when each thread printed it at that point in time. So both threads thought the value of I was 10 the first time they executed the print statement. That means that thread 1 was suspended before it could decrement I from 10, in other words reducing it to 9, because when thread 2 printed the value, it still had the value of 10. Now when thread 1 gets the chance to print the line again, the value is 9. So from this we can guess that thread 1 decremented the value from 10 to 9. So how do we know that? Well, if thread 2 had beaten thread 1 to it and decremented the value from 10 to 9, when thread 1 had the chance to run again, it would have decremented the value from 9 to 8. So it would never have printed the value 9 at all. But because it does, we know that thread 1 decremented it. And by the same reasoning, we know that thread 1 was suspended before it could decrement the value from 9 to 8. Thread 2 then decrements the value from 9 to 8 and then prints 8. So the two threads go back and forth like this for a bit, with thread 1 decrementing the value, printing it and suspending, and then thread 2 decrementing the value, printing it and suspending. Now rather than each thread being able to count down from 10 to 1, they keep skipping numbers because of the interference from the other thread. In fact, when problems arise because threads are interleaving and accessing the same resources, the situation has a name. It's known as thread interference. And we can see why it's called that now from what we've shown here on the screen. These two threads keep interfering with each other because whenever they get a chance to run, the other thread has changed the value of I, and as a result, each thread can no longer count down from 10 to 1 and hit all the numbers. We'll also see this situation referred to as a race condition, which is the more common term for when two or more threads are writing a shared resource. It is important to note that there wouldn't be a problem if both threads were only reading the shared resource. Problems will only arise when at least one of the threads is writing or updating the resource. So let's think about what might have happened when the numbers 2 and 3 were printed out of order. From the pattern we've seen before, we could guess that each thread was decrementing the value, checking the for condition, executing the print statement, and then suspending. So they're going back and forth, except when the numbers 4 and 2 were printed by thread 2. So we can guess from the output that the two threads still interleaved, but thread 1 didn't get a chance to print the value 3 before it was suspended. So you might wonder, why it printed the value 3 when it got the chance to run again. After all, wouldn't thread 1 have decremented the value to 2? So why didn't thread 1 print the value of 3? So in this case, our oversimplification of the possible suspension points don't work. Now I mentioned that there are potential suspension points within the print statement itself, and that's what's actually happening here. So let's take a stab at how these threads are executed. Thread 2 prints the value of 4 and is then suspended. Thread 1, which has printed the value 5 previously and then suspended, decrements the value to 3. Thread 1 starts to execute the println statement. It builds the string that it's going to print, and at that point in time the value of I is still 3. Thread 1 calls println and then is suspended while the println method is executing, but before the string is output to the console. Thread 2 decrements the value to 2 and prints it, and then it suspends. Thread 1 continues to execute the println method and prints out the string it created when the value of I was still 3, then suspends. Thread 2 decrements the value of I to 1, then prints it out. Now that the value of I is 1, both threads at this point exit the for loop and terminate. Now I know that is a bit of a mouthful or a little bit to get your head around, but you can see that every time we run this, we're going to get a different result, and there really is just no way to predict which thread is going to print out which numbers. And obviously in the case when I ran this previously, we've got a completely different result to my example image here. So hopefully you can see now that threads are deceptively simple to work with. We just have to create an object, subclass from thread, and call the start method, or create an instance of the thread class with a runnable object, which we've done in this section. But even when we have only 2 threads that are doing something, really simple, like in this case, you can see how problems can come about because object instances are stored in the heap, which is shared across threads in an application. So I'm going to finish the video here now. In the next video, we'll continue our discussion about race conditions. See you in the next video.
This video is over. Go to starfreelance.eu to download these videos, materials, and sources. Watch more videos to get premium videos and ebooks. We'll be a Starfreelancer.